to Sleepy Facts with Justin. Tonight, we are going to travel somewhere very close, and yet impossibly far. We are going to look up. We are going to let our eyes grow soft and heavy, and together we are going to explore the science of the night sky. Find a comfortable position now. Let your shoulders drop. Let your hands rest gently wherever they fall. There is nowhere you need to be tonight. There is nothing you need to do. The only thing asked of you is to listen and to let the darkness around you become a little more beautiful. The night sky has been above us for as long as there has been an us, long before cities, long before roads, long before anything we might call civilization. Human beings lay on their backs and looked up at the stars. They watched. They wondered. They felt something deep and quiet stir inside them. Something that had no name, but that felt a little like peace. That feeling is ancient. It lives in all of us. Science tells us that the universe is approximately 13.8 billion years old, that the light reaching your eyes on a clear night may have traveled for thousands of years just to find you. That the atoms in your body were forged in the hearts of stars that exploded long before our sun was born. These are facts, and yet somehow they feel less like facts and more like something you might hear in a dream. Tonight, we are going to hold those facts very gently. We are not going to rush through them. We are going to let them drift over you, the way a soft breeze drifts through an open window on a warm evening. The sky above us is not empty. It never has been. It is filled with light that has traveled impossible distances, with worlds we may never visit, with forces so vast and quiet they make a sound that no instrument has ever fully captured. And yet here you are, made of the same material as all of it. You are not separate from the universe. You are a part of it, resting tonight beneath its endless ceiling. Each section of tonight's journey will take you a little deeper. We will talk about why the sky goes dark and what darkness really means. We will talk about stars, what they are, how they are born, how they live for millions and billions of years, and how they die in ways that seed the next generation of suns. We will talk about the moon, steady and silver above us, pulling at the oceans and the tides. We will talk about planets, about galaxies, about the invisible forces that hold everything together. And along the way, if you find yourself drifting, that is perfectly all right. That is, in fact, exactly what this journey is for. Let your thoughts become slow. Let your breath become even. Let the words wash over you like gentle water. Astronomy is one of the oldest sciences. Long before we had telescopes, long before we had mathematics, people were studying the sky simply by watching it. The ancient Babylonians tracked the movements of planets across the stars with remarkable accuracy, recording their observations on clay tablets thousands of years ago. The ancient Egyptians aligned their pyramids with the stars of Orion's belt. Indigenous peoples around the world built entire calendars, navigation systems, and ways of understanding the seasons from careful, patient observation of the sky above them. Looking up was not merely a pastime. It was survival. It was navigation. It was the way our ancestors knew when to plant and when to harvest. It was how sailors crossed open oceans without ever seeing land. The night sky was the original map, the first clock, the earliest record of time passing. Tonight, science gives us something even richer. It tells us not just where the stars are, but what they are made of. It tells us how gravity bends space itself. It tells us that some of the objects we see in the sky are so far away that the light leaving them tonight will not reach us for another 1,000,000 years. The universe is not static. It is alive and moving, expanding outward in every direction, carrying galaxies apart from one another on a tide of space itself. All of this, and yet the sky above you looks much the same as it did to your great-grandparents and their great-grandparents and the earliest human beings who sat beside fire and tilted their heads upward and felt that nameless, quiet peace. Let yourself feel it now. You are lying still in the middle of a spinning world, beneath a sky full of ancient light. Your breathing is slowing. The edges of the day are softening. everything that felt urgent is becoming a little more distant, a little more quiet. This is the gift of the night sky. It has always had the ability to make human concerns feel small in the most comforting of ways, not small in the sense of meaningless, but small in the sense of held. When you look up at the stars, you are reminded that you exist inside something enormous and ongoing, that the universe was turning long before tonight, and it will be turning long after. That you are here now, small and warm and breathing, and that is enough. So settle in. Let your eyes grow heavy. Let the sound of this voice become something soft and steady at the edge of your awareness. We are going to spend the night together beneath the stars, and we are going to begin at the very beginning with the simplest question of all. Why does the sky go dark? There is a question so simple that children ask it, and yet so deep that it puzzled scientists for centuries. Why is the night sky dark? You might think the answer is obvious. It is dark because the sun has gone down, because it is nighttime, because that is simply the way things are. And in the most immediate, practical sense, that is true. The earth turns slowly on its axis, and the side facing away from the sun falls into shadow, and we call that shadow night. But there is a deeper version of this question, one that keeps the curious mind gently turning, the way a leaf turns slowly on the surface of still water. If the universe is infinite, if it goes on forever in every direction, filled with stars beyond counting, then no matter which direction you look, your line of sight should eventually land on a star. The sky should be blazing. Every point of darkness between the stars should be filled with the light of some distant sun. And yet the sky at night is dark, deeply, peacefully, beautifully dark. This puzzle has a name. Scientists call it Olber's paradox, named after the German astronomer Heinrich Wilhelm Olbers, who wrote about it in the early 1800s. Though the question had been quietly circling through the minds of astronomers for much longer than that, the poet and writer Edgar Allan Poe, of all people, came remarkably close to the correct answer. In an essay he wrote 1848, long before the mathematics had fully caught up. The resolution to this beautiful paradox lies in the nature of the universe itself. The universe is not infinitely old. It had a beginning. Approximately 13.8 billion years ago, everything that exists, all matter, all energy, all space, all time, emerged from an unimaginably small, hot, dense point in an event we call the Big Bang. Because the universe has a finite age, light has only had a finite amount of time to travel. The light from stars and galaxies beyond a certain distance simply has not had enough time to reach us yet. The universe is vast, yes, but it is not infinitely old, and light is not infinitely fast. There is a boundary around us called the cosmic horizon. Beyond that boundary, the universe may well continue forever, but its light cannot reach us. It is traveling toward us, even now, but it has not arrived. And so, the darkness between the stars is not an absence of sources. It is simply an absence of time. Let that idea rest with you for a moment. The darkness above you is not emptiness. It is patience. It is the universe waiting for light that has not arrived yet. There is something deeply soothing about that thought. The darkness is not a void. It is a conversation that is still in progress, a message sent from unimaginable distances, traveling toward us across the slow, quiet ocean of space, still making its way home. But Olber's paradox is only one piece of this story. The other piece has to do with something called the expansion of the universe. When we look at distant galaxies, we see something remarkable. They are moving away from us. Not just a few of them, all of them, in every direction. The galaxies of the universe are receding, carried apart from one another by the expansion of space itself. And as they move away, something happens to their light. Light is a wave, and when a source of light moves away from you, the waves of that light are stretched. They become longer. They shift toward the red end of the visible spectrum. And then, if they are stretched far enough, they shift beyond visible light entirely. They become infrared, then microwave, light from the most distant galaxies has been stretched so far that it is no longer visible to the human eye at all. It passes through us unseen, carrying its ancient message in a language our eyes cannot read. This is called redshift, and it is one of the most profound and quietly beautiful concepts in all of astronomy. The universe is speaking to us in a frequency we cannot see, and the darkness we perceive is, in part, that conversation happening just beyond the edge of our perception. Now, let us bring this closer to home. Let us talk about the darkness that falls each evening here on our small and beautiful planet. The Earth is tilted on its axis at an angle of approximately 23.4 degrees relative to its orbit around the Sun. This tilt is the reason we have seasons. As the Earth moves around the Sun over the course of a year, different parts of the planet receive more or less direct sunlight at different times. In summer, your part of the world leans toward the sun. The days are long and the light is warm and direct. In winter, your part of the world leans away. The days are short and the light arrives at a shallow angle, spreading thin across a wider area. But every single day, regardless of the season, the Earth completes one full rotation on its axis. One rotation takes approximately 24 hours. And as your part of the planet turns away from the sun, the light fades, the sky shifts through extraordinary colors, the deep oranges and soft pinks and purples of twilight. And then gradually, gently, it darkens. First, you see the brightest stars. Then more appear, one by one, as your eyes adjust. The sky deepens from pale blue to indigo to the deep, soft black of true night. And if you are somewhere away from city lights, somewhere quiet and open, the Milky Way becomes visible. A pale river of light arching across the darkness, so faint and so vast that it seems almost like a dream. The atmosphere plays a role in all of this. During the day, the molecules of our atmosphere scatter the sun's light in all directions. Blue light scatters more easily than red light because blue light has a shorter wavelength, and so the sky appears blue. When the sun is near the horizon at dawn or dusk, its light must travel through a much greater thickness of atmosphere to reach you. The blue light scatters away entirely, and what remains are the longer wavelengths, the reds and oranges and golds of sunrise and sunset, and then the sun dips below the horizon. The scattering fades, and the sky, freed from the overwhelming brightness of our nearest star, becomes transparent. What was hidden behind that blue veil all day is revealed. The ancient light of distant suns filters through at last. Astronomers distinguish between different stages of twilight. Civil twilight is the period just after sunset, when there is still enough light to see objects clearly on the ground. Nautical twilight is deeper. The horizon is still faintly visible, useful for navigation at sea. And then there is astronomical twilight, the deepest stage, when the sky is dark enough for serious observation, and the faintest objects become visible. Beyond astronomical twilight lies full night, the sky at its darkest, softest, most receptive. In a world without artificial light, full night would be remarkable. Truly dark skies show somewhere between 2,000 and 5,000 stars to the naked eye on a clear night, depending on your eyesight and your location. The Milky Way would be bright enough to cast faint shadows. Meteors would streak through the dark with startling regularity. The eye, given enough time to fully adjust, a process that takes approximately 30 minutes, would become extraordinarily sensitive, able to detect a single candle flame from an enormous distance. Your eyes have two types of light detecting cells: cones, which are concentrated near the center of your vision and allow you to see color, require relatively bright light to function well. Rods, which are spread more widely across your retina, are extraordinarily sensitive to low light, but they do not detect color. In dim conditions, your vision shifts from cone-based to rod-based, which is why colors fade at night, and everything becomes shades of silver and gray. There is a technique that experienced stargazers use called averted vision. Rather than looking directly at a faint object, you look slightly to the side of it. This brings the image onto the rod-rich outer part of your retina, making the object appear brighter. It is a small, quiet trick, and it works beautifully. The science of human vision is woven into the science of the night sky. We are not passive observers. We are part of the equation. Our eyes, shaped by millions of years of evolution, are exquisitely tuned instruments, not perfect, not always reliable, but capable of remarkable sensitivity when we give them time and darkness. And perhaps that is a gentle thought to carry with you now. You too, like the eye adjusting slowly to the dark, become more perceptive in stillness, in quiet, in the slow, unhurried space of rest. The darkness is not something to be resisted. It is something to settle into. Something that, given a little time, reveals more than the light ever could. The night sky is dark because the universe is young, and because light takes time, and because our world turns gently on its axis, carrying us through the shadow and back again. And tonight, you are in the shadow. You are in the quiet place. You are exactly where you are meant to be. Let your breathing slow a little more now. Let the darkness around you feel soft rather than empty. Let it feel, if you can, like a sky full of light that simply has not arrived yet. It is on its way. Look up on a clear night, away from the glow of any city, and you will see them. Thousands of them, scattered across the dark like embers from an ancient fire, or like light caught in still water, or like something so familiar and so foreign at the same time that your mind simply goes quiet in the presence of them. Stars. We have always known they were there, but it is only in the last few centuries that we have begun to understand what they truly are. And what they are is both stranger and more wonderful than any story anyone ever told about them. A star is, at its heart, an enormous ball of gas held together by gravity and powered by nuclear fusion. That sentence is scientifically precise, but it does not quite capture the scale of what we are talking about. So let us slow down and feel our way through it. Our own sun, the star at the center of our solar system, the one that warms your skin lights your days is a sphere of mostly hydrogen and helium gas, approximately 1,390,000 kilometers in diameter. If the sun were hollow, you could fit approximately 1,300,000 Earths inside it. It is not a small thing. And yet, by the standards of the universe, our sun is a perfectly ordinary, middle-sized, middle-aged star. There are stars so much larger that if you placed them at the center of our solar system, they would extend beyond the orbit of Jupiter. There are stars so small and dim that they glow only faintly red, emitting so little light that they are nearly invisible even to powerful telescopes. The universe contains an estimated 2 trillion galaxies. Our own galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars, and there are 2 trillion galaxies, each with their own vast populations of suns. The total number of stars in the observable universe is estimated to be somewhere around 200 sextillion. That is a 2 followed by 23 zeros. Though even that number is almost certainly an underestimate. There are more stars in the universe than there are grains of sand on all of Earth's beaches and deserts combined. Let that be a slow thought. Let it drift through you without needing to be fully grasped. Stars are born in clouds of gas and dust called nebulae. We will talk more about nebulae in a later section, but for now, it is enough to know that these vast clouds, drifting through the spaces between stars, are the raw material from which all stars are made when a region of a nebula becomes dense enough. Gravity begins to pull the gas inward. The cloud contracts. As it contracts, it heats up. The center grows hotter and hotter and hotter over the course of tens of millions of years, until the temperature and pressure at the core reach an extraordinary threshold at approximately 10 million degrees Celsius. Something remarkable happens. Hydrogen atoms, moving at tremendous speeds, begin to collide with enough force to overcome the electrical repulsion between them. They fuse. 2 hydrogen nuclei combine to form helium. And in that fusion, a tiny amount of mass is converted directly into energy. This is the process described by Einstein's famous equation. Energy equals mass multiplied by the speed of light squared, because the speed of light is such an enormous number. Even a tiny amount of mass yields a staggering amount of energy. The star ignites. That outpouring of energy pushes outward against the force of gravity pulling inward, and for as long as there is fuel to burn, these two forces balance each other in a state of dynamic equilibrium. The star shines steadily, consistently, for millions or billions or even trillions of years, depending on its size. This is one of the gentle paradoxes of stars. Larger stars burn hotter and brighter, but they exhaust their fuel far more quickly. A star 10 times the mass of our sun may live for only a few tens of millions of years before its fuel runs out. Our own sun, a more modest star, has a lifespan of approximately 10 billion years, and it is currently about 4.5 billion years into that journey. A middle-aged star, burning steadily, with roughly 5 billion years still remaining. The smallest stars, called red dwarfs, burn so slowly and so dimly that they can live for trillions of years. Since the universe is only 13.8 billion years old, no red dwarf star has ever died of old age. They are all still burning, slowly and patiently, their lifespans so vast they make our sun seem brief. Stars come in an extraordinary range of sizes, temperatures, and colors. Temperature determines color in a way that is deeply intuitive once you understand it. The coolest stars glow red or orange. Medium temperature stars like our sun appear yellow-white. Hotter stars burn blue-white, their surfaces reaching temperatures of 20,000, 30,000, even 50,000 degrees Celsius. The color of a star is a direct readout of its surface temperature, written in light across the darkness. Astronomers classify stars using a system of letters: O, B, A, F, G, K, M, running from the hottest and bluest to the coolest and reddest. Our sun is a G-type star. The mnemonic that astronomy students have used for generations to remember this sequence is, with gentle humor, OB, be a fine girl, kiss me. Or in more modern versions, oh, be a fine guy, kiss me. A small human moment in the vast cold machinery of the cosmos. When you look at the night sky, you are seeing stars at many different distances. The nearest star to our sun, apart from the sun itself, is Proxima Centauri, a small red dwarf approximately 4.2 light years away. A light year is the distance light travels in 1 year, approximately 9.5 trillion kilometers. To put this in perspective, the fastest spacecraft ever launched by humanity would take approximately 73,000 years to reach Proxima Centauri. The stars you can see with the naked eye range from a few light years away to a few thousand light years away. When you look at a star 1,000 light years distant, you are seeing light that left that star 1,000 years ago. You are not seeing the star as it is now. You are seeing it as it was in the past, when that light began its journey. The night sky is a time machine. Every point of light is a message from the past, arriving now, carrying information about a moment that is already gone, and yet there is something comforting about that. Those stars were there. They existed. They burned, and their light set out across the darkness, and it has traveled faithfully across unimaginable distances and unimaginable time, and tonight it is reaching you, whatever those stars are doing right now. In this moment, you will not know for another 1,000 years, but the light they sent long ago has found its destination at last. You are the destination. The ancient light of distant suns is falling on you right now as you rest. Certain stars have names that carry the weight of thousands of years of human attention. Sirius, the brightest star in the night sky, burns blue-white and fierce approximately 8.6 light years from our sun. The ancient Egyptians watched for Sirius on the horizon each year because its annual rising just before the sun heralded the flooding of the Nile, the event that made their civilization possible. They called it the Dog Star, and its heliacal rising marked the beginning of their new year. Betelgeuse, the reddish star at the shoulder of Orion, is a red supergiant so enormous that if it replaced our sun, it would swallow Mercury, Venus, Earth, Mars, and extend toward Jupiter. It is in the late stages of its life. At some point, perhaps tomorrow, perhaps in 100,000 years, astronomical time being wonderfully vague, Betelgeuse will explode in a supernova, briefly outshining the full moon, visible in daylight. When it does, the light from that explosion will take approximately 700 light years to reach us. Rigel, blue-white and blazing at the opposite corner of Orion, is approximately 65,000 times more luminous than our sun. A massive star burning through its fuel with extraordinary profligacy, brilliant and brief on the cosmic scale. Vega, Aldebaran, Arcturus, Polaris. The names of stars are a kind of poetry in themselves, most of them Arabic in origin, given by the astronomers of the Islamic Golden Age, who mapped the sky with such care and precision that their work formed the foundation of modern astronomy. Polaris, the North Star, sits almost exactly above Earth's North Pole, making it appear nearly stationary in the sky, while all other stars appear to wheel slowly around it over the course of a night. Travelers, sailors, and navigators have relied on Polaris for thousands of years. It is not the brightest star in the sky, far from it, but it is perhaps the most practically important star that human civilization has ever known. But Polaris will not always be the North Star. The Earth wobbles very slowly on its axis, like a spinning top that has begun to lean, in a motion called axial precession that completes one cycle approximately every 26,000 years. Over this long, slow wobble, the Earth's pole traces a wide circle among the stars. About 5,000 years ago, during the time of the ancient Egyptians, a star called Thuban was the North Star. In about 14,000 years, the brilliant Vega will hold that position. The stars are patient. They have seen many North Stars come and go. They will see many more, and you, lying still in the turning of this small world, beneath this ancient light, are part of that slow and extraordinary story. Your body is made of elements forged in stars. The iron in your blood was created in the core of a massive star that lived and died before our sun was born. The calcium in your bones, the oxygen in each breath you take, the carbon that forms the backbone of every molecule in your body. All of it was cooked in stellar furnaces, scattered across space in stellar explosions, gathered into clouds, condensed into planets, and assembled over billions of years of patient chemistry into the form of you. You are not merely looking at the stars. You are the stars looking back at themselves. Let that be a quiet thought held loosely as your breathing slows and the night grows deeper around you. There is no need to hold onto anything right now. The stars have been burning for billions of years without any help from us. They will continue to burn long after tonight. And you are made of the same substance as all of them, ancient, patient, and at rest. Everything that lives must also, in some form, come to an end. This is not a sad thought when you hold it gently. It is simply the shape of things, the way a wave rises and falls and returns to the sea it came from, the way a breath is drawn in and then released, the way a day opens slowly in light and closes again in darkness. Stars are no different. They are born. They live for extraordinary lengths of time, and they die. And in their dying, they give rise to everything that comes after them. The life cycle of a star is one of the most beautiful stories in all of science. It is a story that takes place across millions and billions of years, in spaces so vast they have no human equivalent, and yet it is also, in its deepest structure, a story about transformation, about how nothing is ever truly lost, about how endings are almost always also beginnings. Let us follow a star from the very beginning, somewhere in a galaxy, perhaps our own, perhaps another. There is a nebula. A nebula is an enormous cloud of gas and dust, mostly hydrogen and helium, drifting slowly through the space between existing stars. These clouds are not uniform. They have regions of slightly higher density, places where a little more gas has gathered together, pulled by gravity's patient hand. Over millions of years, those denser regions begin to contract. Gravity draws the gas inward. The cloud begins to collapse under its own weight, slowly at first, and then with increasing speed. As the gas falls inward, it heats up. The center of the collapsing cloud grows warmer and denser and brighter, glowing faintly at first in the infrared spectrum. A kind of warmth invisible to the eye, but real nonetheless. This glowing core is called a protostar. It is not yet a true star. It has not yet begun the nuclear fusion that will define its life, but it is on its way. For hundreds of thousands of years, sometimes millions, the protostar continues to gather mass from the surrounding cloud, growing hotter and denser at its core, and then, when the temperature at the center reaches approximately 10 million degrees Celsius, the threshold is crossed. Hydrogen nuclei begin to fuse. The first light of a new sun pours outward. The surrounding cloud of gas and dust is illuminated and then blown away by the pressure of this new radiation, revealing the young star at the center, burning for the first time. A star is born. The young star enters what astronomers call the main sequence, a long, stable phase of life during which hydrogen fusion at the core powers a steady outward pressure that balances the inward pull of gravity for stars like our sun. This main sequence phase lasts approximately 10 billion years. For the most massive stars, it may last only a few million. For the smallest red dwarf stars, it stretches on for trillions of years. During the main sequence phase, a star like our sun burns with remarkable consistency. It does not flash or flicker in any way perceptible to us. It simply shines day after day, year after year, century after century, converting approximately 600 million tons of hydrogen into helium every single second, and releasing the energy of that conversion as light and heat that crosses the void of space and arrives here, warming everything it touches for billions of years. This continues, but nothing lasts forever, and eventually the hydrogen in the core begins to run out. as the core's hydrogen is depleted, the balance between fusion pressure and gravity begins to shift. The core contracts slightly, heating up further. This increased heat causes hydrogen in the shells surrounding the core to begin fusing as well. The outer layers of the star respond to this increased energy by expanding dramatically. The star swells outward, growing enormously larger and cooler at its surface. Its color shifts from yellow-white toward orange and red. The star has become a red giant. Our own sun will become a red giant in approximately 5 billion years. When it does, it will expand to perhaps 100 times its current diameter. The inner planets, Mercury and Venus, will almost certainly be consumed entirely. The fate of Earth is less certain. Some models suggest Earth will be engulfed as the sun expands. Others suggest the sun will lose enough mass that Earth's orbit will drift outward just fast enough to escape. Either way, by the time our sun reaches its red giant phase, Earth will long since have been rendered uninhabitable by the gradually increasing brightness of the sun over the coming billions of years. But this is not a thought for tonight. Tonight, the sun is steady, and 5 billion years of life remain. Back to our red giant. In the core of a red giant, once the hydrogen is exhausted, helium fusion can begin. Helium nuclei fuse together to form heavier elements, carbon and oxygen. This phase of helium fusion is shorter than the hydrogen-burning main sequence phase, but it sustains the star for a further period of hundreds of millions of years. Eventually, for a star of our sun's size, the helium in the core runs out as well. The core contracts into a dense, hot remnant. The outer layers of the star, no longer supported, drift away into space in a slow, expanding cloud of gas and dust, illuminated by the radiation of the cooling core at the center. This expanding shell of gas is called a planetary nebula, a name that has nothing to do with planets, given by early astronomers who thought these glowing rings resembled the disks of distant planets when seen through small telescopes. They are in fact the gently dispersed outer layers of a dying star, expanding outward at speeds of around 20 to 30 kilometers per second, carrying with them the carbon and oxygen and other elements created inside the star during its long life. These elements, this stellar material, will drift through space, perhaps for millions of years, until they encounter other clouds, other regions of collapsing gas, other forming stars. They will be incorporated into new nebulae, new protostars, new solar systems. The carbon that was forged in the heart of a dying star will find its way into the atmosphere of a new world, into the chemistry of life, into the structure of organisms that look up at the sky and wonder where they came from. The answer, in a very real sense, is from a star that died before the sun was born. At the center of the planetary nebula, the contracted stellar core glows hot and white. This remnant is called a white dwarf. It is incredibly dense. A white dwarf containing roughly the same mass as our sun, compressed into a sphere approximately the size of Earth. A teaspoon of white dwarf material would weigh approximately several tons on Earth. The white dwarf is no longer powered by fusion. It is simply cooling, slowly radiating away the heat it accumulated over billions of years. Over trillions of years, timescales so vast that no white dwarf in the universe has yet reached this stage. A white dwarf will cool completely and go dark, becoming what astronomers call a black dwarf, a cold, dead, dark remnant of a star that once shone for billions of years. This is the quiet ending of stars like our sun, a gentle dispersal, a slow cooling, a long, patient darkness, but for more massive stars, stars several times the mass of our sun or more. The ending is anything but quiet. Massive stars burn through their fuel so much faster than smaller stars that they exhaust their hydrogen in millions rather than billions of years. They go through successive stages of fusion, each stage powering the star for a shorter time than the last. Hydrogen fuses to helium. Helium fuses to carbon. Carbon fuses to neon and oxygen. Oxygen fuses to silicon and sulfur. And finally, silicon fuses to iron. Iron is where everything stops. Unlike every lighter element, iron does not release energy when fused. Fusing iron actually consumes energy rather than producing it. When a massive star builds up an iron core, the nuclear fires that have sustained it suddenly go out. There is nothing left to burn. The outward pressure of fusion disappears in a fraction of a second. Gravity, which has been held at bay for millions of years by the pressure of nuclear fire, takes over instantly. The core collapses in less than a second. In a fraction of a second, the iron core, which may be the size of Earth, collapses to a sphere only about 20 kilometers across. The material falling inward reaches a significant fraction of the speed of light. The density becomes so extreme that protons and electrons are forced together to form neutrons. The collapse halts abruptly, bouncing outward in a shock wave of almost incomprehensible energy. The outer layers of the star, which have been falling inward, meet this shock wave and are blasted outward into space with tremendous force. The star explodes in an event called a core collapse supernova for a brief period, days to weeks. A supernova can outshine the entire galaxy it belongs to. The light of a single exploding star can be visible across hundreds of millions of light years. It blazes into the darkness like the ignition of a new sun, carrying within that blaze the heavy elements created in the star's core, scattering them outward into the galaxy to seed the next generation of worlds: gold, silver, platinum, uranium. Many of the heaviest elements in the universe are not forged in stellar fusion at all, but in the extraordinary conditions of a supernova, or in the collisions of neutron stars, the dense remnants left behind when massive stars explode. Every gold ring, every silver necklace, every piece of precious metal on Earth was created in a cataclysm of unimaginable violence. Long before our solar system existed, scattered across the cosmos, and eventually gathered here. The remnant left at the center of a supernova is either a neutron star that extremely extraordinarily dense sphere of neutrons, spinning rapidly, sometimes emitting beams of radiation that sweep the sky like a cosmic lighthouse. Or, for the most massive stars, a black hole, an object of such extreme density that not even light can escape its gravitational pull. We will spend time with black holes in their own section later tonight. For now, let us simply hold the arc of this story, a cloud of gas drifting in the dark, a slow contraction, a kindling of fire, billions of years of steady burning, a swelling, a dispersal, a quiet fading. Or, for the largest stars, a blazing, violent death that seeds the next generation of worlds with the elements needed for chemistry and life and wonder. Every star that has ever existed has been part of this cycle. The atoms in your body have passed through at least one stellar generation, possibly more. You are, in the most literal scientific sense, the recycled material of ancient suns, and now those ancient suns, transformed beyond recognition, are resting, just as you are resting now. Let the story of the stars settle around you like warmth. Let your thoughts slow. Let each breath be easy and unhurried. You do not need to hold onto any of this. Like the outer layers of a dying star, you can let things drift gently outward, softly, into the dark. The universe will not mind. It has been letting things drift for 13.8 billion years. And it is very, very good at it. There is something the human mind does instinctively and without effort that no other known mind in the universe does quite the same way. It finds patterns. Show a person a scattered arrangement of dots, and within moments they will find a shape, a face, an animal, a figure reaching across the dark. This tendency is so deep, so automatic, so woven into the fabric of how we perceive the world, that scientists have given it a name. Pareidolia, the perception of meaningful patterns in random arrangements. And nowhere has this tendency expressed itself more beautifully or more enduringly than in the night sky. The constellations are perhaps the oldest collaborative art project in human history. They were not made by one culture or one civilization or one moment in time. They were made by thousands of generations of human beings, all across the world, all independently looking up at the same stars and drawing different lines between them, finding different shapes, telling different stories, the same stars, different stories. There is something quietly wonderful about that. The word constellation comes from the Latin word meaning a collection of stars. In modern astronomy, a constellation is not just a pattern of stars, but an officially defined region of the sky, a territory, like a country on a map, with borders and a name. The entire sky is divided into 88 official constellations, a system formalized by the International Astronomical Union in 1922 and finalized with precise boundaries in 1930. These 88 regions cover the entire celestial sphere, from pole to pole, leaving no part of the sky unclaimed. But the constellations as patterns, as pictures drawn between stars, are far older than any formal classification. The oldest known star catalogs come from ancient Babylon, dating back approximately 3,000 years, though the observations they recorded were almost certainly much older still. The Babylonians identified and named many of the constellations that we still use today, including patterns that would later be inherited by the ancient Greeks, and from the Greeks passed down through centuries of Islamic astronomy, and from there into the European Renaissance, and so into the modern world. The ancient Egyptians saw different shapes in some of the same stars. What we call Orion, the hunter, the Egyptians associated with Osiris, their god of the afterlife and resurrection, the belt of Orion, 3 bright stars in a nearly perfect straight line, was deeply significant to them. The 3 pyramids at Giza are arranged in a pattern that mirrors, with remarkable precision, the arrangement of those 3 stars. Whether this was intentional is a question that archaeologists still discuss, but the correspondence is striking and beautiful. The ancient Greeks gave us much of the constellation mythology that remains most familiar in the Western world. Orion the hunter chasing the Pleiades across the sky. Cassiopeia, the vain queen, seated on her throne, circling the celestial pole. Perseus with his sword, and Andromeda chained to her rock, and the great winged horse Pegasus rising nearby. The stories are connected, interwoven, playing out across the dome of the sky in a kind of slow, eternal theater. Scorpius, the scorpion, and Orion, the hunter, are never in the sky at the same time. Scorpius rises in the south as Orion sets in the west. Ancient Greek myth explains this as the result of their enmity. Orion boasted that he would hunt and kill every animal on earth. Gaia, the earth goddess, sent the scorpion to sting him. The gods placed them on opposite sides of the sky so that they would never meet again. Whether or not you believe in the myth, there is a certain elegance to the fact that the sky itself seems to honor it. The Pleiades, a small, tight cluster of stars in the constellation Taurus, appear in the mythologies and astronomical traditions of cultures that had no contact with one another. Indigenous Australians, whose astronomical traditions are among the oldest in the world, saw the Pleiades as a group of young women. The ancient Japanese called them Subaru, a name now more familiar on the roads of the world than in the sky, though the car manufacturer's logo is in fact a stylized image of these 6 stars. The ancient Greeks called them the 7 sisters, daughters of the Titan Atlas and the ocean nymph Pleione. Most people see only 6 stars in the cluster with the naked eye, and many cultures around the world have stories that explain the apparent absence of one sister, she who hides, or she who weeps, or she who has gone away. The fact that so many cultures, separated by oceans and centuries, noticed the same thing about the same cluster of stars, the mysterious missing 7th sister, is one of the most quietly astonishing coincidences in all of human history. We were all looking at the same sky. We were all counting the same stars. We were all wondering the same thing. In the southern hemisphere, the sky presents a completely different face. The constellations of the northern sky sink below the horizon, replaced by others that northern observers rarely or never see. The Southern Cross, Crux, is the smallest of the 88 official constellations, but among the most recognizable. Its 4 bright stars forming a compact cross that has guided sailors and navigators across the southern oceans for centuries. It appears on the national flags of Australia, New Zealand, Brazil, Papua New Guinea, and Samoa. A constellation so woven into the identity of the southern world that it has become a symbol of belonging to a particular part of the earth. The Magellanic Clouds, visible in southern skies, appear to the naked eye as detached fragments of the Milky Way. 2 soft, hazy patches of light hanging in the darkness. They are in fact 2 irregular dwarf galaxies, gravitationally bound to the Milky Way, companions to our galaxy in the vastness of intergalactic space. The Large Magellanic Cloud is approximately 160,000 light years away. The Small Magellanic Cloud is approximately 200,000 light years distant. They are so close, cosmically speaking, that they are among the most studied objects in all of astronomy. Indigenous Australian astronomical traditions recognize dark constellations as well as light ones, shapes defined not by stars, but by the dark patches of dust and gas that obscure the stars behind them, creating dark rivers and animal shapes within the Milky Way. The Emu in the sky, for example, is a constellation traced not in points of light, but in the dark nebulae of the Milky Way. The head near the Southern Cross, the body and legs stretching across the galaxy when the emu is lying flat on the horizon. The emus on the ground are beginning to lay their eggs. The sky is a calendar, an almanac, a guide to life on the earth below. This is true of indigenous astronomical traditions around the world. The Lakota people of North America saw the Milky Way as the spirit road, the path taken by souls after death. The ancient Polynesian navigators used the rising and setting points of stars to navigate thousands of kilometers across open ocean, reaching islands scattered across the vast Pacific with an accuracy that modern GPS might envy. The stars were not merely beautiful, They were useful. They were a technology. And this is, perhaps, the deeper meaning of constellations. They were not mistakes or superstitions or primitive attempts at science. They were a filing system, a way of organizing the overwhelming complexity of the sky into something navigable, memorable, and meaningful. By grouping stars into shapes and attaching stories to those shapes, ancient astronomers gave themselves a way to remember where everything was, to track the passage of the seasons, to know when to plant and when to sail, and when to expect the rains. The story of Orion rising in the east in late autumn, for instance, told farmers in the ancient Mediterranean that winter was approaching. The return of the Pleiades to the evening sky in spring was the signal to begin planting. In many ancient agricultural cultures, the constellations were a clock, a calendar, and a compass, all written in the sky. Modern astronomy has kept the names of the ancient constellations while redefining them as regions of sky rather than patterns of stars. Within those regions, astronomers map the positions of stars, galaxies, nebulae, and other objects, using the constellation names as a convenient address system. When an astronomer says that a particular galaxy lies in the constellation Virgo, or that a supernova has appeared in Andromeda, they are using a system that traces its roots back thousands of years to people sitting around fires in the dark, drawing lines between stars. The stars within a constellation are not actually close to one another. They merely appear to be, from our perspective here on Earth, two stars that appear side by side in the sky might be separated by hundreds of light years in actual space. If you could travel to one of those stars and look back at our sun, you would see it in a completely different part of the sky. The constellations are a perspective, a view from one particular place, our solar system, at one particular time in 100,000 years, as the stars slowly move through the galaxy. The familiar shapes will have drifted and distorted beyond recognition. Orion will not always look like Orion, but right now, tonight, from where you are, he is there. Rising or setting or crossing the sky depending on the season and your location. The same Orion that ancient Egyptians associated with Osiris, that ancient Greeks gave a name and a story to, that billions of human eyes have followed across the sky throughout all of recorded history and long before. There is a kind of comfort in that continuity, in the knowledge that the pattern above you is a pattern that has been recognized and named and storied by countless generations of human beings across the full span of human existence. You are not alone under these stars. You never have been. Every human being who has ever lived has looked up at them, has found shapes in them, has told stories about them, has felt in their presence something that goes beyond words, that quiet, deep, nameless feeling that the darkness and the light together seem to reliably produce in the human heart. Call it wonder, call it peace, call it the recognition of belonging to something vast. Let it move through you now, gently, like the slow drift of light across a still floor. The constellations are not scientific objects. They are human objects. They are the places where science and story meet, where the measurable and the meaningful become, for a moment, the same thing. And they are up there right now, whether you can see them or not, patiently holding their shapes, carrying their ancient names, waiting for anyone who takes a moment to look up. You do not need to look up tonight. Tonight, you can simply rest and know that they are there. Of all the objects in the night sky, there is one that feels closest, not just in distance, though it is by far the nearest substantial body to our world, but in feeling, in the way it has accompanied human life, for as long as there have been human lives to accompany, in the way it pulls at the oceans, and some say at something deeper than the oceans, in the way it changes night by night, in a slow and utterly reliable rhythm that our ancestors used to measure time long before any clock was ever made. The moon. It hangs in the sky with a presence that no other celestial object quite matches, large enough to show a disk to the naked eye, bright enough when full to cast shadows, close enough that its surface features, the dark plains, the bright highlands, clusters of craters are visible without any instrument at all if you simply take the time to look, and human beings have been looking at it and thinking about it and telling stories about it for at least as long as we have been human. The moon is Earth's only natural satellite. It orbits our planet at an average distance of approximately 384,000 kilometers, a distance that sounds large, but is, in cosmic terms, a stone's throw. Light takes approximately 1.3 seconds to travel from the moon to Earth. By comparison, light from the sun takes approximately 8 minutes. Light from the nearest star beyond our sun takes more than 4 years. The moon is, cosmically speaking, right next door. It is also, by a remarkable and improbable coincidence, almost exactly the same apparent size in our sky as the sun. The sun is approximately 400 times larger in diameter than the moon, and it is approximately 400 times farther away. These two factors cancel each other out almost perfectly, with the result that both the sun and the moon appear roughly the same size when viewed from Earth. This coincidence is what makes total solar eclipses possible. The moon fitting almost perfectly over the face of the sun, blocking its light and revealing the ghostly corona that surrounds it. No other planet in our solar system has a moon that produces this effect. It is a coincidence so precise that it feels, in quiet moments, almost like it was arranged. How did the moon form? For a long time, this was one of the great unanswered questions of planetary science. Several competing theories were proposed: that the moon formed alongside the Earth from the same cloud of material, that the Earth captured it from elsewhere in the solar system, that the Earth somehow spun off the moon from its own material early in its history. The theory that now has the strongest scientific support is called the giant impact hypothesis, and it is a story of extraordinary violence from the very early days of our solar system, approximately 4.5 billion years ago, when the solar system was still young and chaotic. A body roughly the size of Mars. Scientists call it Theia, collided with the young Earth in a glancing blow of almost incomprehensible force. The impact melted and vaporized enormous amounts of material from both bodies. A vast cloud of molten rock and vapor was thrown into orbit around the Earth. Over time, a few tens of millions of years, this debris coalesced under its own gravity into the moon we know today. The evidence for this theory comes from multiple sources. The moon's composition is remarkably similar to Earth's outer layers, suggesting it formed from material that was already differentiated, separated by density. As the Earth was, the moon is also unusually large relative to its parent planet. Earth's moon is the fifth largest moon in the solar system, and the ratio of moon size to planet size is larger for Earth and its moon than for any other planet-moon pair in the solar system, with the possible exception of Pluto and its moon Charon in the immediate aftermath of its formation. The moon was much closer to Earth than it is today. Tidal forces between the Earth and the newly formed moon were enormous. The young Earth's days were only a few hours long. The moon, close and massive relative to its current distance, raised tides of extraordinary height, and the friction of those tides gradually slowed Earth's rotation and pushed the moon slowly outward. The moon is still moving away from us. It recedes from Earth at a rate of approximately 3.8 centimeters per year, roughly the rate at which human fingernails grow. We know this with extraordinary precision because Apollo astronauts left laser reflectors on the lunar surface, and scientists on Earth regularly bounce laser beams off these reflectors to measure the distance to the moon with centimeter-level accuracy. In a billion years, the moon will be far enough away that total solar eclipses will no longer be possible. The moon will be too small in the sky to fully cover the sun. Future inhabitants of Earth, whatever form they take, will experience only annular eclipses, where the moon passes in front of the sun, but leaves a ring of sunlight visible around its edges. But that is a billion years away. Tonight, the moon is exactly where it has always been, keeping its ancient and faithful company. The moon rotates on its axis in almost exactly the same time it takes to orbit Earth, approximately 27.3 days. This synchronization, called tidal locking, means that the moon always presents the same face toward Earth. The near side, familiar and mapped and storied, faces us always. The far side, not the dark side, which is a common misconception, as both sides receive equal amounts of sunlight, was completely unknown to humanity until the Soviet spacecraft Luna 3 photographed it in 1959. The near side of the moon is dominated by large dark plains called maria, from the Latin word for seas. Early astronomers, seeing these dark flat regions through early telescopes, believed they might be actual bodies of water. They are not. They are ancient lava plains formed when massive asteroid impacts in the moon's early history cracked its crust and allowed molten rock to flow up and fill the impact basins, cooling into the flat, dark plains we see today. The Sea of Tranquility, the ocean of storms, the Sea of Serenity. The names are poetic remnants of a misunderstanding, and they have a beauty that the correct explanation does not diminish. The bright highlands between the maria are older, more heavily cratered terrain. The original crust of the moon, battered by billions of years of impacts. When you look at the full moon with the naked eye, you are seeing the contrast between these two types of terrain. The dark maria and the bright highlands together form the pattern that different cultures have interpreted as a face. A rabbit, a woman, a toad, a man carrying sticks. The moon has no atmosphere. This means several things that shape its character profoundly. Without an atmosphere, there is no weather, no wind, no rain, no erosion in the conventional sense. A footprint left in the lunar soil, the fine, gray, powdery regolith that covers the surface, will remain undisturbed for millions of years, preserved in perfect stillness, with nothing to erase it. The footprints left by Apollo astronauts are still there, right now, exactly as they were left. 12 human beings walked on the moon between 1969 and 1972. marks they left are as fresh today as the morning they were made, because nothing on the moon has the power to erase them. There is something profoundly moving about that. Those footprints in the gray dust, perfectly preserved, waiting in the silence of the airless plain. Without an atmosphere, the moon also experiences temperature extremes that Earth's blanket of air protects us from entirely. In direct sunlight, the lunar surface reaches approximately 127 degrees Celsius. In the lunar night, the temperature plummets to approximately minus 173 degrees Celsius, a range of 300 degrees between day and night, with no atmosphere to moderate it. The moon's gravity is approximately 1/6 of Earth's. An astronaut weighing 80 kilograms on Earth weighs approximately 13 kilograms on the moon. The famous footage of Apollo astronauts bounding across the lunar surface in their bulky suits. Those long, floating strides, the slow arc of each step, is a direct result of this reduced gravity, even encumbered by the weight of their life support equipment. The astronauts moved with an effortless, dreamlike grace that you simply cannot replicate on Earth. The tides of our oceans are the most immediate way that the moon makes itself felt in daily life. The gravitational pull of the moon acts slightly differently on the near side of Earth than on the far side, because the near side is closer. This difference in gravitational pull stretches the oceans very slightly in the direction of the moon, creating a bulge of water on the side of Earth facing the moon, and a corresponding bulge on the opposite side as Earth rotates beneath these bulges. Most coastal locations experience 2 high tides and 2 low tides each day. Tides shape coastlines, drive ocean circulation, influence the behavior of marine life, and have profoundly affected the course of human history. Tidal inlets and estuaries are among the most biologically productive environments on Earth. Some theories of the origin of life suggest that tidal pools, shallow areas alternately flooded and exposed by the tides, may have been the crucible in which the first complex organic molecules formed, sheltered from ultraviolet radiation concentrated by the repeated evaporation and refilling of the pool, the moon may have helped create the conditions for life on Earth. And beyond science, beyond tides and orbital mechanics, beyond the chemistry of early life, the moon has given humanity something that cannot be measured in any laboratory. It has given us a rhythm. The roughly 29.5-day cycle of the moon from new to full and back to new is the origin of the word month, and it has been used as a unit of time by virtually every human culture that has ever existed. The Islamic calendar is still a purely lunar calendar, with months beginning at the first sighting of the crescent moon. The dates of Easter, Passover, the Hindu festival of Diwali, the Chinese New Year, and many other religious and cultural celebrations around the world are all determined by the phases of the moon. The moon synchronizes human time. It always has. And on a quieter, more personal level, the moon has been a companion, a light in the darkness for travelers walking at night, a presence for the sleepless, looking out of a window at 3 in the morning, a marker of time passing for those separated from someone they love, knowing that the same moon they see is visible to the person they are thinking of somewhere else in the world. This idea that two people separated by distance can look at the same moon has appeared in poetry and song and letter and story across every culture and every century. It is such a simple and universal comfort that it must touch something very fundamental in us. The moon is shared. It belongs to everyone who has ever looked up at it, and to everyone who ever will. Tonight, wherever you are, the moon is somewhere in its cycle. Perhaps it is above the horizon right now, casting its silver light across rooftops and trees and the still surface of water. Perhaps it is below the horizon, making its way through the dark half of its journey. Perhaps it is new, invisible, a dark disk against the darker sky. Whatever phase it holds tonight, it is keeping its faithful orbit, moving through the darkness at just over 1 kilometer per second, pulling at the oceans, reflecting the light of the sun, quietly accompanying this small world as it has done for 4.5 billion years. You do not need to see it to feel its presence. Let it be there, somewhere beyond the walls and the ceiling and the night, steady and pale and patient. Let its slow rhythm be part of your breathing. The long inhale of the waxing moon, the long exhale of the waning, the deep, still pause of the new moon resting in the dark. You are resting now too. The moon understands. The ancient Greeks had a word for them. Planets, wanderers. While the stars held their positions night after night, tracing the same slow arcs across the sky, season after season, year after year, there were certain points of light that moved, slowly, deliberately, tracing their own paths against the fixed background of the stars. They were brighter than most stars. They did not twinkle the way stars do, and they wandered. The Greeks identified 5 of them with the naked eye. We know them today as Mercury, Venus, Mars, Jupiter, and Saturn. To the Greeks, they were the homes of gods: Hermes, Aphrodite, Ares, Zeus, Poseidon. To the Romans, who inherited Greek astronomy and renamed the planets in their own divine language, they became Mercury, Venus, Mars, Jupiter, Saturn, the names we still use today. 2,000 years later, there is something deeply human about naming the wandering lights after gods. These were the most dynamic, most changeable objects in the sky. They moved. They had presence. They seemed, in a way that the fixed stars did not, to be going somewhere. And of course, they are. Our solar system is a family of 8 planets, all orbiting the same star, all moving in the same general direction around the sun, all lying in roughly the same flat plane, the remnant of the spinning disk of gas and dust from which the solar system formed approximately 4.5 billion years ago. Within this family, the 8 planets are extraordinarily diverse. They range from small rocky worlds to gas giants so large that thousands of Earths could fit inside them. They have surfaces of solid rock, oceans of liquid metal, atmospheres of crushing pressure, and rings of ice and dust. Each one is a world unto itself. Each one is strange and beautiful in its own way. Let us wander through them, one by one, moving outward from the sun. Mercury is the innermost planet, and in many ways the most extreme. It is the smallest of the 8 planets, only slightly larger than our moon. It orbits the sun every 88 Earth days, moving faster in its orbit than any other planet. And yet, because it rotates on its axis so slowly, one Mercury day lasts approximately 59 Earth days. A single solar day on Mercury, from one sunrise to the next, lasts approximately 176 Earth days. Mercury has almost no atmosphere to moderate its temperatures. The side facing the sun reaches approximately 430 degrees Celsius. The side in darkness plunges to approximately -180 degrees. These are among the most extreme temperature swings of any planet in the solar system. And yet, in permanently shadowed craters near Mercury's poles, where sunlight never reaches, scientists have found evidence of water ice preserved for billions of years in the deep cold of permanent shadow, just a few hundred kilometers from a surface that would melt lead. Venus is the second planet from the sun, and in size and mass, it is the most similar to Earth of all the planets, sometimes called Earth's twin. But the similarity ends there. Venus is wrapped in a thick atmosphere of carbon dioxide, with clouds of sulfuric acid drifting in layers through its upper atmosphere. The greenhouse effect on Venus is so extreme that its surface temperature is approximately 465 degrees Celsius, hotter than Mercury, despite being farther from the sun, hot enough to melt lead, hot enough that the spacecraft we have managed to land on Venus have survived for only minutes before being destroyed by the heat and pressure. The atmospheric pressure at Venus's surface is approximately 90 times that of Earth's surface, equivalent to the pressure nearly 1 kilometer beneath Earth's oceans. Standing on Venus, if such a thing were possible, would feel like standing at the bottom of a very deep sea, in air hot enough to incinerate you, beneath a sky of thick yellowish cloud, through which the sun would be only a dim, diffuse glow. Venus rotates on its axis in the opposite direction to most other planets. A retrograde rotation. That means the sun rises in the west and sets in the east. It rotates so slowly that a Venusian day is longer than a Venusian year. The reasons for this unusual rotation are still debated, though a massive ancient collision is among the leading hypotheses. And yet Venus, for all its hostility, glows in our sky with breathtaking beauty. It is the brightest object in the sky after the sun and the moon, sometimes visible in broad daylight if you know where to look. Ancient astronomers called it the morning star when they saw it rising before the sun, and the evening star when it followed the sun below the horizon. For a time, some cultures believed these were two different objects. The recognition that they were one and the same was an early triumph of careful astronomical observation. Earth, our home, the third planet, we will spend tonight on it, and so we know it more intimately than any other world. But seen from space, it is remarkable. A small blue sphere wrapped in white cloud, lit by a steady yellow star, carrying on its surface liquid water and living things. And for the moment, us, the only world in the solar system where liquid water exists stably on the surface. The only world where life is known to exist. A thin layer of atmosphere. Atmosphere so thin that if you compressed Earth to the size of a basketball, the atmosphere would be no thicker than a coat of varnish. We live inside that varnish, and it is enough. Mars is the fourth planet and the most explored beyond Earth. Red and dusty, it is a cold, dry world with a thin atmosphere of carbon dioxide, swept by dust storms that can engulf the entire planet for months at a time. Its surface is a landscape of ancient volcanoes, vast canyon systems, polar ice caps, and plains of rust-colored dust. Olympus Mons, the largest volcano in the solar system, rises approximately 22 kilometers above the Martian surface, nearly 3 times the height of Mount Everest. The Valles Marineris Canyon system stretches approximately 4,000 kilometers across the Martian surface, roughly the width of the continental United States. ancient riverbeds and lake basins, in minerals that only form in the presence of water, in the layered sediments that planetary scientists read like pages in a very old book. Something changed approximately 3 to 4 billion years ago. Mars lost most of its atmosphere. Its magnetic field weakened, and its liquid water either froze, evaporated, or retreated underground. What was once, perhaps, a habitable world became the cold red desert we see today. Beyond Mars lies the asteroid belt, a region between the orbits of Mars and Jupiter, populated by millions of rocky and metallic bodies ranging in size from tiny pebbles to the dwarf planet Ceres. Approximately 945 kilometers in diameter, the asteroid belt is not the dense, dangerous field of rocks depicted in science fiction films. In reality, the average distance between asteroids is enormous, and spacecraft pass through the belt with ease, but it is a region of leftover material, the raw ingredients of a planet that never quite assembled itself, kept in a perpetual state of orbital fragments by the gravitational influence of Jupiter. Jupiter is the 5th planet and the king of the solar system in terms of size. It is so large that more than 1,300 Earths could fit inside it. It is a gas giant, a world with no solid surface, composed mostly of hydrogen and helium, with a possible small rocky core deep in its interior, under conditions of almost incomprehensible pressure. Its atmosphere is divided into bands of different colors and compositions, driven by winds that can reach speeds of several hundred kilometers per hour, and punctuated by storms of extraordinary scale. The most famous of these storms is the Great Red Spot, an anticyclonic storm system that has been observed continuously for at least 350 years. At its largest, the Great Red Spot was wider than 2 Earths. In recent decades, it has been shrinking, and its eventual fate is unknown. But for now, it persists, rotating slowly in Jupiter's southern hemisphere, a storm older than any nation currently existing on Earth. Jupiter has at least 95 known moons, 4 of which are large enough to have been discovered by Galileo in 1610 with one of the earliest telescopes. These 4, Io, Europa, Ganymede, and Callisto, are worlds in their own right. Io is the most volcanically active body in the solar system. Its surface constantly reshaped by hundreds of active volcanoes, driven by the tidal heating of Jupiter's immense gravity. Europa has a smooth, icy surface beneath which a global ocean of liquid water is believed to exist, heated by the same tidal forces. Europa is one of the most compelling candidates in the solar system for the possible existence of extraterrestrial life. Saturn is the 6th planet, and perhaps the most visually extraordinary object in the solar system. Its ring system, a vast, flat disk of ice and rock particles extending outward for hundreds of thousands of kilometers from the planet's equator, is visible even in a small telescope, and it never fails to produce a particular kind of quiet astonishment in anyone who sees it for the first time. The rings are extraordinarily thin relative to their width. In most places, only about 10 to 30 meters thick, despite being hundreds of thousands of kilometers across. If you scaled Saturn's rings to the size of a sheet of paper, the paper would be thousands of times thicker than the rings are relative to their width. Saturn itself is the least dense of all the planets. Its density is less than that of water, meaning that if you could find an ocean large enough, Saturn would float in it. It is a world of extraordinary lightness. Its golden banded atmosphere streaked with winds and storms, its poles topped by a mysterious hexagonal cloud pattern, a 6-sided jet stream, unlike anything in the atmosphere of any other known world. Uranus is the 7th planet, a pale blue-green ice giant with a peculiarity unlike any other planet in the solar system. It is tilted on its side. Its axis of rotation is tilted approximately 98 degrees from the vertical, meaning that Uranus essentially rolls around the sun on its side, with its poles alternately pointing toward and away from the sun over the course of its 84-year orbit. Each pole experiences approximately 42 years of continuous sunlight, followed by 42 years of continuous darkness. The reason for this extreme tilt is believed to be an ancient collision with a large body early in the solar system's history. Another echo of the violent, chaotic period of planetary formation 4.5 billion years ago. Neptune is the 8th and outermost planet, a deep blue world of freezing temperatures and the strongest winds in the solar system. Wind speeds on Neptune can reach approximately 2,100 kilometers per hour, supersonic by Earth standards. Neptune was the first planet to be predicted mathematically before it was observed. In the mid-19th century, astronomers noticed that Uranus was not following exactly the orbit that Newtonian gravity predicted. They calculated that an unknown planet must be exerting a gravitational pull on it, and determined where that planet must be. When telescopes were pointed at the predicted location, Neptune was there. This was one of the great triumphs of theoretical physics, the discovery of a world by mathematics alone, before any human eye had seen it. Our solar system is our neighborhood, these 8 worlds circling the same star, each one profoundly different from the others, each one carrying its own ancient history of formation and collision and slow geological change. They have been circling the sun for 4.5 billion years. They will continue to circle it for billions more. And from this small, quiet planet, third from the sun, wrapped in its thin and precious atmosphere, we look outward at our neighbors with curiosity and wonder. The wandering lights of the ancient sky are still wandering tonight. Mercury moving swiftly close to the horizon. Venus blazing in the west or the east. Mars perhaps a faint red point among the stars. Jupiter steady and bright, Saturn golden and patient. They are all out there right now, moving through their ancient paths, going somewhere, as they always have been, as you tonight are going somewhere too, drifting gently and unhurried toward the soft country of sleep. Let the planets turn. Let their orbits curve slowly through through the dark. Let everything that is moving continue to move without any help from you. You can rest now. The solar system does not need your attention tonight. It has been managing beautifully for 4.5 billion years. On a clear night, far from city lights, if you give your eyes enough time to adjust to the darkness, something extraordinary becomes visible. A band of soft, diffuse light stretching from horizon to horizon, arching across the sky like a river of pale smoke, or like someone has brushed a wide stroke of luminous watercolor across the darkness. It is not bright. It does not announce itself. It rewards patience and stillness, appearing gradually as your eyes become more sensitive, growing richer and more detailed the longer you look. This is the Milky Way, not a cloud, not a reflection, not an atmospheric effect, but the combined light of hundreds of billions of stars, so distant, so numerous, so densely packed along our line of sight, that their individual points of light blur together into this soft, continuous glow. You are looking at your home galaxy from the inside. The Milky Way is a barred spiral galaxy. If you could somehow lift yourself far above it and look down, you would see a flattened disk of stars with a bright, dense central bulge and sweeping spiral arms curving outward from a central bar of stars. The disk is approximately 100,000 light years across and roughly 1,000 light years thick, though the edges are not sharp, but fade gradually into the emptiness of intergalactic space. The central bulge is denser and more spherical, containing older, redder stars packed more closely together. The spiral arms, where most of the galaxy's active star formation takes place, are rich in gas and dust, and young, hot, blue-white stars. Our solar system sits in one of these spiral arms, a minor arm called the Orion arm, or sometimes the local arm. Approximately 26,000 light years from the galactic center, we are not in the crowded heart of the galaxy, nor in the sparse outer reaches. We occupy a relatively quiet suburban position, well placed to observe much of the rest of the galaxy without being overwhelmed by the density and radiation of the galactic core. The Sun, along with our entire solar system, orbits the center of the Milky Way. This orbit is not a quick journey. It takes the Sun approximately 225 to 250 million years to complete one full orbit of the galactic center, a period sometimes called a cosmic year or a galactic year. In the approximately 4.5 billion years since the solar system formed, the Sun has completed somewhere between 17 and 20 orbits of the galaxy. The last time we were in this same position in our galactic orbit, the most complex life on Earth was single-celled organisms. Dinosaurs had not yet appeared. Flowers did not exist. The supercontinent Pangaea would not form for another 100 million years. One galactic year ago, the Earth was unrecognizable. The Milky Way contains somewhere between 100 billion and 400 billion stars. The uncertainty reflects the difficulty of counting them. Since much of the galaxy is hidden from our view by clouds of dust that absorb visible light, many of these stars are like our Sun. Many are smaller and dimmer. Some are vastly larger and more luminous. A significant fraction of them are believed to host planetary systems. The sheer number of potentially habitable worlds implied by these numbers is one of the reasons the question of extraterrestrial life is taken seriously by scientists. At the very center of the Milky Way, approximately 26,000 light years from Earth, lies one of the most extraordinary objects in the galaxy. A supermassive black hole. It is called Sagittarius A*, named for the constellation Sagittarius, in the direction of which it lies from our vantage point. It has a mass approximately 4 million times that of our Sun, compressed into a region of space smaller than our solar system. Stars orbit it at extraordinary speeds, some completing full orbits in only a few years, moving at thousands of kilometers per second. The observation of these stellar orbits, tracked patiently over decades by astronomers, provided some of the most compelling evidence for the existence of this enormous dark mass at the heart of our galaxy in 2022. The Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, a blurry but unmistakable ring of glowing gas surrounding the dark silhouette of the black hole's event horizon. It was a moment of profound scientific achievement, the culmination of years of work by hundreds of scientists around the world, and it showed us the heart of our own galaxy in a way no human being had ever seen before. The Milky Way is not alone in space. It is the dominant member of a small group of galaxies called the Local Group, which contains more than 50 galaxies of varying sizes. Most of these are small dwarf galaxies, many of them orbiting the Milky Way or the Andromeda galaxy, the other large spiral galaxy in our neighborhood. The two Magellanic clouds we mentioned in our section on constellations are among the most prominent of the Milky Way's satellite galaxies. The Andromeda galaxy lies approximately 2.5 million light years from Earth. The most distant object visible to the naked eye under dark skies. It appears as a faint, elongated smudge of light in the constellation Andromeda, easy to overlook, astonishing to contemplate. That faint smudge contains approximately 1 trillion stars. The light reaching your eyes from it tonight left Andromeda 2.5 million years ago, when our own ancestors were early hominids walking the plains of Africa, not yet fully human, looking up at the same galaxy whose light is reaching you now. The Andromeda galaxy and the Milky Way are approaching each other. Gravitational attraction is drawing them together across the void. In approximately 4.5 billion years, they will collide and merge in a slow-motion cosmic event that will unfold over hundreds of millions of years, producing a new, larger galaxy, sometimes called Milkomeda or Milkdromeda by astronomers. A great elliptical galaxy born from the merger of our two spirals. The collision will not be violent in the way we usually imagine. Galaxies are mostly empty space. The stars within them are so far apart that the chance of any two stars actually colliding is extremely small, but the shapes of both galaxies will be profoundly distorted. Their spiral arms flung outward in long tidal streamers, their stars scattered into new orbits, their gas and dust compressed into regions of intense new star formation. The night sky, for any beings on Earth fortunate enough to witness this event, will be transformed beyond recognition, filled with streams of stars, new star clusters blazing into life, the galactic center blazing with activity, but again, 4.5 billion years. Tonight, the Milky Way is exactly where it has always been, arching overhead or below the horizon, carrying us slowly around its ancient center. The structure of the Milky Way was not always understood. For most of human history, the band of light across the sky was a mystery. The ancient Greeks called it galaxies kyklos, the Milky Circle, from which we get the word galaxy. Various cultures saw it as a river of milk, a path of souls, a river in the sky. The Lakota people called it the Spirit Road. Aboriginal Australians traced shapes within it, using its dark lanes as well as its light. It was the Italian scientist Galileo Galilei who, in 1610, first turned a telescope toward the Milky Way and discovered that it resolved into individual stars, countless stars, too numerous and too faint to see individually with the naked eye, but unmistakably there. The soft glow was not a cloud or a vapor. It was stars, billions of them. This realization that the Milky Way is made of stars was one of the most significant perceptual shifts in the history of human understanding of the universe. It transformed the sky from a dome with painted lights into a three-dimensional space of extraordinary depth, populated with suns beyond counting. But it took much longer to understand our place within it. For most of the 19th and early 20th centuries, astronomers debated whether the Milky Way comprised the entire universe, or whether the fuzzy patches of light called nebulae, some of which we now know to be other galaxies, were objects within the Milky Way, or separate systems far beyond it. This question, sometimes called the Great Debate, was largely resolved in the 1920s when the American astronomer Edwin Hubble used a newly completed telescope at the Mount Wilson Observatory in California to measure the distance to the Andromeda Nebula, demonstrating that it was far too distant to be within the Milky Way. The universe was suddenly, staggeringly larger than anyone had imagined. The Milky Way was not the universe. It was one island among an ocean of islands, each one vast, each one containing billions of stars, each one separated from its neighbors by distances that beggar comprehension. This moment, the recognition of the scale of the universe, is one of the great intellectual shifts in human history, and it happened less than 100 years ago. Our species has known the true scale of the cosmos for less than a century. We are very new to this understanding, and yet, somehow, it feels right. It feels like something we have always sensed, in the way we feel small beneath the stars, in the way the night sky produces that particular quality of awe that seems to reach below thought and touch something more fundamental. We sensed the enormity long before we could measure it. When you look up at the Milky Way, or simply imagine it above you now, arching through the dark, you are looking at your home, a structure 4.5 billion years old, 100,000 light years across, carrying you in its slow rotation through the even vaster darkness of intergalactic space. You are inside it. You are part of it. You are, in the most literal sense, a resident of the Milky Way galaxy. And the Milky Way, for its part, carries you with perfect reliability. It has been doing so since before the Earth existed. It will continue to do so long after tonight. Through its slow rotation, through its gradual drift through the local group, through its eventual merger with Andromeda billions of years from now, it will carry every atom of everything that is here, transforming and redistributing and continuing. Nothing is lost. Everything is carried. You can feel that perhaps in the weight of your body resting right now. The sense of being held, supported, carried by something larger than yourself. The galaxy is turning beneath you. You do not need to do anything about that. Simply rest and let it turn. Imagine standing at the edge of a great ocean on a still night. The water stretches out before you in every direction, dark and vast. Its surface catching the faint light of the stars above. You cannot see the far shore. You cannot see the bottom. You can only see as far as the darkness allows. And beyond that, you simply know, you feel that it continues. That the water goes on and on, far beyond the reach of your eyes, carrying within it a depth and a complexity that no single moment of looking could ever fully reveal. This is something like what astronomers feel when they contemplate the universe of galaxies. Not stars, galaxies. Each one a vast city of stars, gas, dust, and dark matter, each one containing hundreds of billions to trillions of individual suns, each one separated from its neighbors by distances measured not in light years, but in millions of light years. And there are, in the observable universe alone, an estimated 2 trillion of them. 2 trillion galaxies. Let that number rest with you without asking you to understand it. Some numbers are not meant to be understood. They are meant to be felt like the ocean, not computed, but sensed with a kind of quiet and grateful astonishment. The study of galaxies as objects in their own right is surprisingly young, as we touched on in our previous section. It was only in the 1920s that Edwin Hubble demonstrated that the fuzzy patches of light astronomers had been cataloging for centuries were not clouds within the Milky Way, but entire separate galaxies, each one an island universe in its own right, separated from us by distances that had previously seemed almost unthinkable. Hubble's method relied on a particular type of star called a Cepheid variable. Cepheid variables are stars that pulsate. They expand and contract in a regular rhythm, brightening and dimming with a period that is directly related to their intrinsic luminosity. The brighter the star truly is, the longer its pulsation period. This relationship, discovered by the American astronomer Henrietta Swan Leavitt in 1912, provided astronomers with what is called a a standard candle, an object of known brightness that can be used to measure distance. If you know how bright something truly is, and you measure how bright it appears from where you are standing, you can calculate how far away it must be. The dimmer it appears relative to its true brightness, the farther away it is, by identifying Cepheid variables in the Andromeda Nebula and measuring their pulsation periods. Hubble was able to calculate that Andromeda was nearly 1,000,000 light years away, far beyond the boundaries of the Milky Way. We now know the distance is closer to 2.5 million light years, but the principle was correct, and the conclusion was revolutionary. The universe was vastly larger than anyone had imagined. Galaxies come in a remarkable variety of shapes and sizes. The most visually striking are the spiral galaxies, flattened disks with sweeping arms of stars, gas, and dust curving outward from a central bulge. Our Milky Way is a barred spiral galaxy with a bar of stars crossing its center, from which the spiral arms extend. The Andromeda Galaxy is also a spiral, slightly larger than the Milky Way, its disk tilted at an angle toward us, so that we see it as an elongated oval of soft light. Elliptical galaxies are rounder and smoother, lacking the dramatic spiral arms. They range from nearly spherical to elongated footballs, and they tend to be found in the denser regions of galaxy clusters. The largest known galaxies in the universe are giant ellipticals, some containing trillions of stars. Their vast halos of old, reddish stars, extending for millions of light years into the surrounding space. These giants sit at the centers of massive galaxy clusters, having grown large through billions of years of mergers with smaller galaxies. Irregular galaxies have no clear shape at all. They are the result of gravitational interactions with other galaxies, collisions, near misses, tidal disruptions that have distorted their original forms into chaotic tangles of star formation, glowing nebulae, and asymmetric swirls. The two Magellanic Clouds, companions to our Milky Way, are examples of irregular galaxies, their shapes distorted by the gravitational influence of our much larger galaxy over billions of years. There are also lenticular galaxies, which share characteristics of both spirals and ellipticals, disc-shaped like spirals, but lacking the prominent spiral arms, smooth and featureless like ellipticals, but retaining the disc structure that ellipticals do not have. They are thought to represent a transitional stage, spiral galaxies that have lost their gas and dust, and therefore can no longer form new stars, their arms fading as their stellar populations age. The variety of galaxy shapes is not random. It reflects the history of each galaxy, the mergers it has experienced, the gas it has consumed or lost, the environment in which it has spent its billions of years of life. A galaxy's shape is its biography. Galaxies do not exist in isolation. They cluster together under the influence of gravity, forming structures on scales that dwarf anything we have discussed so far. Our local group, the Milky Way, Andromeda, and their assorted smaller companions, is itself part of a larger structure called the Virgo supercluster, a vast assemblage of galaxy groups and clusters stretching approximately 110 million light years across. But even the Virgo supercluster is dwarfed by the largest structures in the known universe. In 2014, astronomers mapped an even larger structure, of which the Virgo supercluster is merely a small component. A supercluster of superclusters called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans approximately 500 million light years and contains the mass of approximately 100 million billion suns. The Milky Way sits near the outer edge of this vast cosmic structure, one small galaxy in an almost incomprehensibly large family, and Laniakea itself is just one of many such superclusters in the observable universe. When astronomers map the large-scale structure of the universe, they find something that resembles, with eerie beauty, the structure of the human brain, or the structure of a spider's web. Galaxies and galaxy clusters are not distributed evenly through space. They form long filaments and sheets, the cosmic web, with vast, empty regions called voids between them. The filaments intersect at dense nodes called galaxy clusters. The voids between the filaments are almost completely empty, stretching for hundreds of millions of light years, with very little matter inside them. The cosmic web is the largest known structure in the universe. It was not designed. It emerged naturally from the tiny fluctuations in density that existed in the very early universe, amplified over 13.8 billion years by gravity into the vast, intricate architecture we see today. Some of the most distant and luminous objects in the observable universe are quasars. A quasar is the extraordinarily bright core of a distant galaxy, powered by a supermassive black hole actively consuming enormous amounts of material. As gas and dust fall into the black hole, they form a swirling accretion disk that heats up to extreme temperatures and radiates energy across the entire electromagnetic spectrum with a luminosity that can exceed that of an entire galaxy of hundreds of billions of stars, all from a region smaller than our solar system. The most luminous quasars are so bright that they can be seen across billions of light years, and they shine with the light of trillions of suns. Because they are so distant, we see them as they were billions of years ago, in the early universe, when black holes were younger and more actively feeding, and the universe was a denser, more turbulent place than it is today. Quasars are windows into the past, snapshots of conditions that no longer exist in our cosmic neighborhood. One of the most profound observations in the history of astronomy was made in 1995 when the Hubble Space Telescope was pointed at a small, apparently empty patch of sky in the constellation Ursa Major, a region no larger than a grain of sand held at arm's length. The telescope collected light from this tiny patch of darkness for 10 consecutive days. The image that emerged is called the Hubble Deep Field. It revealed nearly 3,000 galaxies in that tiny sliver of sky, each one a vast system of billions of stars, each one at a different distance, showing us different eras of cosmic history. Subsequent deep field images, the Hubble Ultra Deep Field, the Hubble E Extreme Deep Field, have probed even deeper, revealing galaxies so distant that their light has been traveling for more than 13 billion years to reach us. There is no empty sky. Every direction we look, as far as our instruments can see, the universe is full of galaxies. This image, the Hubble Deep Field, is perhaps the single most perspective-altering image ever taken. A grain of sand-sized patch of apparently empty darkness turned out to be full of entire universes of stars, each galaxy home to billions of suns, each sun potentially hosting worlds, stretching back almost to the beginning of time. The universe is not sparsely populated. It is overwhelmingly, staggeringly, almost absurdly full. And here you are, in one small corner of it, on one small planet, orbiting one ordinary star, in one arm of one spiral galaxy among 2 trillion. This could feel diminishing, and sometimes it does. The scale of it presses in, but there is another way to hold it. You are here. You exist. You are the part of this vast, full, extraordinary universe that is aware of itself. Every galaxy in the Hubble Deep Field has no knowledge of its own existence. Every quasar blazing across billions of light years carries no awareness of its own luminosity. Every filament of the cosmic web, spanning hundreds of millions of light years, has no sense of its own extraordinary architecture. But you do. You, lying still on this small world, breathing slowly in the dark, carry within you the capacity to comprehend, however imperfectly, however partially, the scale and beauty of the whole. That is not nothing. That is, perhaps, everything. The universe is full of galaxies, and in one of them, on one of its worlds, something woke up and looked outward and said, "How extraordinary." That something is you. Rest now in that knowledge. Let it be soft and warm rather than overwhelming. Let the 2 trillion galaxies drift through the dark on their ancient courses, carrying their billions of stars, weaving their cosmic web yourself be small and quiet and aware at the center of it. You do not need to hold all of it. You only need to rest. There are places in the universe where the ordinary rules of space and time simply stop working. Not in a dramatic way, not with any sound or announcement, just a boundary, invisible and absolute, beyond which the physics that governs everything we know and everything we experience no longer applies in any way we can fully describe or imagine. These places are black holes, and they are among the most fascinating, most mysterious, and in their own way, most quietly beautiful objects in all of science. A black hole is a region of space where gravity is so extreme that nothing, not matter, not energy, not light itself, can escape once it crosses a certain boundary. That boundary is called the event horizon. It is not a physical surface. You would not see it or feel it as you crossed it. It is simply the point of no return, the place beyond which escape becomes impossible, not because of any barrier, but because to escape would require traveling faster than light, and nothing in the universe can do that. Inside the event horizon, all paths through space and time lead inward. There is no direction that is outward anymore. The concept of escape becomes meaningless in the same way that the concept of traveling north becomes meaningless once you are standing at the North Pole. Every direction is the same direction, and that direction is deeper in. The idea of black holes emerged from the mathematics of general relativity. Albert Einstein's theory of gravity, published in 1915, Einstein showed that gravity is not a force in the traditional sense, but a curvature of space and time caused by the presence of mass. Massive objects warp the fabric of space-time around them, and other objects follow the curves of that warped space-time. What we perceive as gravitational attraction, the more massive the object, the more it warps space-time. Einstein's equations allowed for solutions in which the warping becomes so extreme, the concentration of mass so great, that space-time curves in on itself completely, a point of infinite density, infinite curvature, mathematicians call a singularity, surrounded by the event horizon, beyond which even light cannot escape. Einstein himself was not sure such objects could actually exist. He believed the universe might have some mechanism that prevented matter from collapsing to such extremes. He was wrong. We now know that black holes are real, abundant, and in many ways essential to the structure of the universe as we know it. How does a black hole form? The most common pathway is through the death of a massive star. As we discussed in our section on the life cycle of stars, when a very massive star exhausts its nuclear fuel, its core collapses with extraordinary speed. If the collapsing core is massive enough, more than approximately 3 times the mass of our sun, not even the pressure of densely packed neutrons can halt the collapse. The core continues to shrink past the neutron star stage, past any known form of matter, down to a singularity. The black hole is born. These stellar mass black holes range from approximately 3 to a few tens of times the mass of our sun, compressed into regions just a few kilometers across. The event horizon of a black hole with the mass of our sun would be approximately 3 kilometers in radius. An object the mass of Earth, if somehow compressed into a black hole, would have an event horizon smaller than a marble, but stellar mass black holes are not the only kind. At the centers of most large galaxies, including our own Milky Way, there are supermassive black holes containing millions to billions of times the mass of our sun. The supermassive black hole at the center of the Milky Way, Sagittarius A star, contains approximately 4 million solar masses. The black hole at the center of the giant elliptical galaxy Messier 87, the first black hole ever directly imaged in 2019, contains approximately 6.5 billion solar masses. Its event horizon is so large that our entire solar system would fit comfortably inside it. How supermassive black holes formed is one of the great open questions in astronomy. They must have grown to their enormous sizes somehow, through the consumption of gas, dust, and stars over billions of years, through mergers with other black holes, perhaps through the collapse of enormous clouds of gas in the very early universe. The details are still being worked out, the evidence still being gathered, the models still being refined. There is also a class of black holes called intermediate mass black holes, with masses between a few hundred and a few 100,000 solar masses. They are the hardest to find, sitting between the well-studied stellar mass and supermassive varieties, and their existence and properties are an active area of research. And in recent years, theorists have proposed the existence of primordial black holes that may have formed not from collapsing stars, but directly from density fluctuations in the very early universe, fractions of a second after the Big Bang, before any stars existed. Some of these primordial black holes, if they exist, might be very small, even smaller than an atom in diameter, though containing the mass of a mountain. Their existence has not been confirmed, but they have not been ruled out, and they remain one of the more intriguing speculative corners of modern cosmology. What happens near a black hole, not inside, but near, is strange and beautiful in ways that have no everyday equivalent. As you approach the event horizon of a black hole, time itself slows down relative to a distant observer. This is not a metaphor or a mathematical abstraction. It is a real physical effect predicted by general relativity and confirmed in various forms by experiment. The stronger the gravitational field, the more slowly time passes. Near the event horizon of a black hole, this effect becomes extreme. A clock placed near the event horizon would appear, from a safe distance, to run slower and slower, its ticking stretching out, its hands approaching stillness. The light from that clock would be increasingly redshifted, stretched toward longer and longer wavelengths, becoming first red, then infrared, then microwave, fading and dimming as the clock approaches the horizon, until it seems to freeze at the boundary from the perspective of the clock itself, or of an astronaut falling toward the black hole. nothing unusual would happen at the moment of crossing the event horizon. You would cross it without any particular sensation, without any visible boundary. You would simply find yourself in a region of space from which return was impossible. The strangeness would make itself felt later as you approached the singularity and the tidal forces of gravity. The difference in gravitational pull between your head and your feet became extreme. This stretching effect, the elongation of an infalling object by tidal forces near a black hole, has been given the wonderfully evocative name spaghettification. The word sounds playful, but the process it describes is absolute and inescapable. Black holes are black in the sense that they emit no light of their own, but the regions around them can be among the brightest places in the universe. Gas and dust falling toward a black hole forms an accretion disk, a swirling, flattened structure of superheated material spiraling inward, heated by friction and compression to temperatures of millions of degrees, radiating energy across the entire electromagnetic spectrum with extraordinary intensity. The most powerful black hole feeding events produce jets, narrow beams of material and energy shot outward along the black hole's rotation axis at close to the speed of light, extending for thousands or even millions of light years into the surrounding space. These relativistic jets are among the most energetic phenomena in the universe, capable of influencing the evolution of entire galaxies by heating the gas that would otherwise cool and collapse into new stars. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made one of the most extraordinary detections in the history of science. It detected gravitational waves, ripples in the fabric of space-time itself, produced by the merger of two black holes approximately 1.3 billion light years away. The two black holes, each several tens of times the mass of the sun, had been spiraling toward each other for billions of years. In the final fraction of a second before they merged, they released more energy in the form of gravitational waves than all the stars in the observable universe radiate as light during that same fraction of a second. The ripple in space-time produced by this event was so small that by the time it reached Earth, it had shrunk to a distortion of space less than 1,000th the diameter of a proton. And yet, LIGO detected it. The instruments were sensitive enough to measure a change in distance less than 1,000th the width of a proton across a detector several kilometers long. This detection opened an entirely new window on the universe. We had previously observed the cosmos through light in all its forms: visible, infrared, radio, X-ray. Now, for the first time, we were hearing it. Gravitational waves are not light. They are vibrations in space-time itself, and they carry information about events that produce no light at all, like the merger of two black holes in the dark. The universe had been speaking this language for billions of years. We have only just learned to listen. And then there is the question that sits quietly at the edge of everything we know about black holes. What is inside? The singularity, the point of infinite density at the center of a black hole, is not really an answer. It is a symbol that our equations have reached their limit. Infinite density, infinite curvature. These are not physical descriptions of something real. They are mathematical indications that our current theories break down at this point, that we need a deeper understanding, a more complete theory that unifies quantum mechanics and general relativity. Physicists have been working on this unification for a century. It remains unfinished. The singularity at the heart of a black hole is one of the places where the incompleteness of our understanding is most starkly visible. We do not know what is inside a black hole. This is not a failure of science. It is an invitation. One of the most profound open questions in all of physics, waiting patiently in the dark for someone, perhaps someone not yet born, to find the key. Black holes are not destroyers, not in the cosmic sense. They are recyclers, collectors, transformers. The material they consume does not disappear, according to Stephen Hawking's theoretical work. on what is now called Hawking radiation. Black holes very slowly leak energy over astronomical timescales, a quantum mechanical effect that causes them to gradually evaporate, returning their mass to the universe in a different form. A stellar mass black hole would take an almost incomprehensibly long time to evaporate through Hawking radiation, far longer than the current age of the universe. But the principle stands. Even black holes are not permanent. Even the most absolute seeming boundaries are, on the longest of timescales, temporary. Everything changes. Everything continues. Right now, somewhere in the Milky Way, stellar mass black holes drift silently through the galaxy, invisible unless they happen to have a companion star close enough to feed from. At the center of the galaxy, Sagittarius A star sits in relative quiet. It is not actively feeding at the moment. Its accretion disk dim compared to the blazing quasars of other galaxies, but it is there. 4 million solar masses of compressed space-time, patient and permanent and dark. And the gravitational waves from black hole mergers in distant galaxies are passing through you right now, through the room you are in, through the earth beneath you, stretching and compressing the very fabric of space by an amount too small for any instrument to measure at this distance. You are being gently rippled by the mergers of black holes in other galaxies. The universe is touching you in ways you cannot feel, with information you cannot read, in a language you are only beginning to learn. Let that be a soft thought. Let it move through you like the gravitational waves do, without friction, without resistance, without leaving a trace. The universe is vast and strange and full of darkness that is not empty. And you, small and warm and breathing, are right at the center of your own small corner of it. Rest now. The black holes are doing their work without you. The gravitational waves are passing through. The fabric of space-time is gently, imperceptibly rippling, and you are still, held perfectly at rest. There are places in the galaxy where the darkness is not empty, but full. Not full of stars. Those stars may be forming there, or may have already been born there and moved on, full of something softer and more diffuse, vast clouds of gas and dust, drifting through the spaces between stars, glowing in colors so vivid and so otherworldly that the first time a person sees a true image of one, they sometimes find it difficult to believe they are looking at something real. These are nebulae, and they are among the most beautiful structures in the known universe. The word nebula comes from the Latin word for cloud or mist. It is an appropriate name. A nebula is, at its most basic, a cloud, an enormous accumulation of gas and dust, mostly hydrogen and helium, scattered through the interstellar medium with trace amounts of heavier elements and complex molecules. Some nebulae are the birthplaces of stars, regions where gravity is slowly pulling material together into the dense cores that will eventually ignite as new suns. Others are the remnants of stars that have already lived and died, their outer layers dispersed into space in the final stages of stellar life. Still others are simply clouds, vast, cold, dark structures drifting through the galaxy, waiting for conditions that will allow them to begin the long process of star formation. Nebulae come in many types, each one shaped by different physical processes, each one glowing or not glowing for different reasons. Emission nebulae are perhaps the most visually striking. These are clouds of gas that have been energized by the radiation of nearby hot young stars. The ultraviolet light from these stars strips electrons from hydrogen atoms in the surrounding gas, a process called ionization. When those electrons recombine with the hydrogen atoms, they release energy as light, producing the characteristic deep red glow of hydrogen alpha emission. This is the red that dominates so many of the iconic images of nebulae. The Orion Nebula, the Eagle Nebula, the Lagoon Nebula. That red is the color of hydrogen recombining, of energy being released in the form of visible light, of a cloud of gas responding to the heat of the stars it has just given birth to. Other elements contribute other colors. Doubly ionized oxygen produces a vivid blue-green. Singly ionized sulfur produces a deep red, somewhat different from hydrogen. By imaging nebulae in different wavelengths and assigning different colors to each, astronomers have created images of extraordinary beauty that are not arbitrary artistic choices, but genuine representations of the chemical and physical processes happening within the cloud. The Orion Nebula is one of the most studied and most photographed objects in the sky. It lies approximately 1,344 light years from Earth in the constellation Orion, just below the 3 stars of the Hunter's Belt. On a clear, dark night, it is faintly visible to the naked eye as a hazy star in the middle of Orion's sword. A smudge of softness among the sharper points of the surrounding stars through binoculars or a small telescope. It reveals itself as a glowing cloud surrounding a tight cluster of hot, young stars called the trapezium. Through powerful telescopes and space observatories, it becomes a landscape of extraordinary complexity. Dense, dark globules where new stars are forming, jets of gas shooting from young protostars, shock waves where stellar winds collide with the surrounding cloud. The Orion Nebula is an active stellar nursery. Stars are being born there right now. Some of the young stars in and around the nebula are only 1,000,000 years old. Infants by astronomical standards, still surrounded by the disks of gas and dust from which planetary systems may be forming. In a few million years, the intense radiation of those young stars will have blown away the remaining nebula entirely, and what is now a glowing cloud will be a cluster of naked young stars, brilliant and new in the dark. Reflection nebulae are a different kind of beauty entirely. These clouds do not emit light of their own. They shine by reflecting the light of nearby stars, scattering it the way our atmosphere scatters sunlight to produce the blue sky. The Pleiades star cluster is surrounded by a reflection nebula. A faint, wispy glow visible in long exposure photographs. The cloud through which the cluster is currently moving, lit up by the blue-white light of the young stars within it. The color of a reflection nebula tends toward blue. For the same reason our sky is blue. Shorter wavelengths scatter more efficiently than longer ones. Dark nebulae are perhaps the most dramatic in their simplicity. They do not glow at all. They are simply cold, dense clouds that block the light of the stars behind them, appearing as dark shapes, silhouettes of absence, against the bright background of an emission nebula or the star-rich backdrop of the Milky Way. The Horsehead Nebula in the constellation Orion is one of the most iconic dark nebulae. A pillar of dense, cold gas and dust rises from a larger molecular cloud, its top eroded by the radiation of nearby hot stars into a shape that, from our perspective, resembles a horse's head and neck in profile. The reddish glow of the emission nebula behind it provides the contrast that makes the dark silhouette visible. It is a structure approximately 5 light years tall, shaped by the interplay of gravity, radiation, and stellar winds over hundreds of thousands of years. The pillars of creation are another beloved dark structure. Tall columns of dense gas and dust within the Eagle Nebula, lit on their surfaces by the radiation of nearby young stars, while their interiors remain dark and cold enough for new stars to be forming within them. The Hubble Space Telescope's image of the pillars of creation, first released in 1995, became one of the most recognized astronomical images ever taken. 3 vast columns of cosmic cloud, their surfaces sculpted into fantastical shapes by the forces acting upon them. Their interiors perhaps sheltering the beginnings of new solar systems. Planetary nebulae are among the most exquisitely beautiful objects in astronomy. Their name a historical misnomer. They have nothing to do with planets. As we discussed in our section on stellar life cycles, when a star like our Sun exhausts its nuclear fuel and swells into a red giant, it eventually sheds its outer layers into space. These expelled layers of gas expand outward from the dying star's core over thousands of years, forming shells and rings and bubbles of glowing material, illuminated by the intense ultraviolet radiation of the hot, newly exposed stellar core. The white dwarf. At the center, the variety of shapes that planetary nebulae take is extraordinary. Some are nearly perfect spheres of glowing gas, like soap bubbles drifting in the dark. Others are bipolar, pinched at the center, and flaring outward in two lobes, like an hourglass or a butterfly. Some show multiple shells, evidence of several episodes of mass loss during the star's final evolution. Others have asymmetric shapes produced by the influence of a binary companion star or the magnetic field of the dying star. The ring nebula in the constellation Lyra is one of the most famous planetary nebulae. It appears through a telescope as a small, bright ring of glowing gas with a faint central star. The white dwarf that was once the core of a sun-like star. The ring is actually a cylinder of gas seen nearly end-on. The outer edge of a shell of expelled stellar material, glowing in the radiation of the remnant star. It lies approximately 2,500 light years from Earth. The star that created it was probably similar to our own sun. Its death created this. The Helix Nebula in the constellation Aquarius is one of the closest planetary nebulae to Earth, approximately 650 light years away. It spans approximately 2.5 light years across and is sometimes nicknamed the Eye of God, a name that, however unscientific, captures something of the feeling one gets when looking at its image, a vast, glowing eye of cosmic gas, with the faint white dwarf at its center like a pupil, surrounded by rings of color, reds and blues and golds, gradually fading into the surrounding darkness. In a few billion years, our own sun will create a nebula like this. Its outer layers will be cast off into space, forming perhaps a ring or a bubble or a complex asymmetric shell of glowing gas, illuminated by the exposed white dwarf at the center. The final form of the star that once warmed our world, the material of that nebula, will eventually disperse into the interstellar medium, mixing with other clouds, contributing its carbon and oxygen and nitrogen to the raw material of the next generation of stars and exoplanetary systems, supernova remnants are the most energetic kind of nebula. The expanding shells of gas blasted outward by the death of a massive star in a core collapse supernova, the Crab Nebula in the constellation Taurus, is the remnant of a supernova observed and recorded by Chinese and Arab astronomers in the year 1054. At its brightest, the supernova was visible in broad daylight for approximately 23 days and remained visible to the naked eye for nearly 2 years. Today, nearly 1,000 years later, the expelled material is still expanding outward at approximately 1,500 kilometers per second, forming a tangled web of glowing filaments spanning approximately 11 light years. At the center of the Crab Nebula lies a pulsar, a rapidly rotating neutron star, the collapsed remnant of the exploded star's core, spinning approximately 30 times per second and emitting beams of radiation that sweep the surrounding nebula like a cosmic lighthouse. The Crab Nebula is one of the most studied objects in the sky, a laboratory for extreme physics that cannot be replicated on Earth, a glowing monument to a stellar death observed and recorded by human eyes almost 1,000 years ago. Beyond these individual nebulae, the galaxy is threaded with diffuse clouds of gas and dust, the interstellar medium that fills the spaces between stars. This medium is not uniform. It ranges from extremely hot, thin plasma in the aftermath of supernova shock waves to warm neutral gas to cold molecular clouds where the temperature drops close to absolute zero, and complex molecules, including organic molecules like formaldehyde, methanol, and even amino acids, have been detected. The interstellar medium is not empty space. It is a thin but continuous presence, connecting the nebulae, the stars, the stellar remnants, the dust. It is the medium through which the material of dead stars travels on its way to becoming the raw material of new ones. It is the sea in which the islands of stars and planetary systems are embedded, and it is full of chemistry, full of the building blocks of complexity drifting through the cold dark between the stars, waiting for the right conditions, a cloud that collapses, a star that ignites, a planet that forms and cools and gathers water to become something more. Nebulae are not just beautiful objects to photograph and admire. They are the mechanism by which the galaxy recycles itself, by which the material forged in stellar cores is dispersed and redistributed, by which the chemical complexity of the universe grows, generation by generation, as each cycle of star formation and stellar death adds new elements to the interstellar medium, enriching it for the next generation. We are downstream of this process. The atoms in your body have passed through nebulae. They were part of the interstellar medium before they were incorporated into the cloud that formed our solar system. They were dispersed by a stellar death before they were gathered by a new stellar birth. You are made of recycled cloud, of dispersed starlight and drifting chemistry, and the patient accumulation of billions of years of cosmic process. Let that rest with you now softly. You are the temporary local form of material that has been part of many things before and will be part of many things after. Right now, it is gathered here, in this shape, breathing quietly in the dark. The nebulae are out there, forming and dispersing and glowing in colors the naked eye can barely perceive. New stars are being born in their dense cores right now. Old stars are shedding their outer layers into new clouds. The galaxy breathes in and out in its slow, billion-year rhythm. And you are breathing too. Slowly, gently, in and out, part of the same great cycle. Imagine something that has been traveling through the dark for 4.5 billion years. Not a star, not a planet, something smaller and stranger, and somehow more poignant, a frozen wanderer, a remnant of the earliest days of our solar system, drifting through the cold outer reaches of space in a long, slow orbit that brings it close to the sun, perhaps once in a human lifetime, or once in 1,000 human lifetimes, or perhaps only once in all of recorded history. And when it finally arrives, after all that time and all that distance, it does something extraordinary. It glows. This is a comet, one of the most ancient and storied objects in the night sky, a visitor from the very beginning of the solar system, carrying within its frozen heart material that has been preserved, almost unchanged, since the solar system itself was new. Comets have been observed and recorded by human beings for as long as there have been human beings capable of keeping records. Every culture that left any written or pictorial record of the sky left records of comets, and for most of that history, comets were not seen as beautiful. They were seen as omens. The sudden appearance of a bright comet in the sky, unexpected, unexplained, blazing with its luminous tail across the familiar backdrop of the stars, was deeply unsettling to ancient observers who understood the sky as a fixed and ordered place. Comets broke the rules. They appeared without warning, moved in ways that no planet or star moved, displayed tails that seemed to point away from the sun like an accusing finger, and then faded and disappeared just as mysteriously as they had come. Nearly every culture interpreted comets as portents of war, of plague, of the death of kings, of great upheavals in the affairs of humanity. Julius Caesar was assassinated shortly after a comet appeared in the Roman sky. The Norman conquest of England in 1066 was preceded by the appearance of Halley's comet, which was recorded with evident anxiety in the Bayeux Tapestry as a fiery star, and a crowd of fearful onlookers pointing upward. Chinese court astronomers kept detailed records of comets for centuries, correlating their appearances with earthly events in the belief that the sky was communicating something of urgent importance. We now understand that comets are not omens. They are travelers, ancient, frozen, beautiful travelers from the outer solar system, carrying within them some of the oldest material in our cosmic neighborhood. A comet in its quiet state, far from the sun, drifting through the cold outer reaches of the solar system, is called a nucleus. It is a small, irregular body, typically a few kilometers to a few tens of kilometers across, composed of ice, dust, rock, and frozen gases water ice, carbon dioxide, carbon monoxide, methane, ammonia. The surface is dark, darker than coal, covered in a crust of organic material and dust that absorbs rather than reflects sunlight. Comets originate in two main regions of the solar system: short-period comets, those that return to the inner solar system within 200 years, are thought to originate in the Kuiper Belt, a disc-shaped region of icy bodies beyond the orbit of Neptune, extending from approximately 30 to 50 astronomical units from the Sun. 1 astronomical unit is the average distance from Earth to the Sun, approximately 150 million kilometers. The Kuiper Belt is the outer suburb of the solar system, home to Pluto and thousands of other icy bodies, relics of the solar system's formation. Long-period comets, those with orbital periods of thousands or even millions of years, are thought to originate in the Oort cloud, a vast, roughly spherical shell of icy bodies that surrounds the solar system at distances of between approximately 2,000 and 100,000 astronomical units from the Sun. The outer edge of the Oort cloud marks the practical boundary of the Sun's gravitational influence, the farthest reach of our solar system. It has never been directly observed. Its existence is inferred from the properties of the long-period comets that arrive from all directions of the sky, their orbits tracing paths back to these immense distances. The Oort cloud is thought to contain trillions of icy bodies, the scattered remnants of the original protoplanetary disk that surrounded the young Sun. These bodies were flung outward to enormous distances by gravitational interactions with the forming giant planets early in the solar system's history. There they have remained in the cold and dark for 4.5 billion years, barely disturbed, their chemistry preserved almost perfectly from the time of the solar system's formation, when a gravitational disturbance, perhaps a passing star, perhaps the tidal forces of the galaxy itself, nudges one of these distant objects from its stable orbit. It begins a long, slow fall inward toward the Sun. This journey can take millions of years. journey, the comet remains frozen and dark, indistinguishable from any other small icy body in the outer solar system. But as it draws closer to the sun, something begins to change. The sun's heat penetrates the comet's dark outer crust and begins to warm the ices beneath. Frozen gases sublimate, converting directly from solid to vapor without passing through a liquid phase. This process is called outgassing, and it is what transforms a dark, frozen nucleus into one of the most spectacular objects in the solar system. The outgassing creates a cloud of gas and dust surrounding the nucleus, called the coma. The coma can grow to enormous sizes, sometimes larger than the planet Jupiter, hundreds of thousands of kilometers across. Even though the nucleus at its center may be only a few kilometers in diameter, the comet is mostly a very large cloud of vapor surrounding a very small frozen core. As the comet approaches the sun and the outgassing intensifies, the solar wind, the continuous stream of charged particles flowing outward from the sun, pushes the gas and dust of the coma away from the nucleus, forming the comet's distinctive tail. Actually, most comets have two tails, and they always point in slightly different directions. The ion tail, or gas tail, is formed from the ionized gases of the coma. Electrically charged molecules that are pushed almost directly away from the sun by the solar wind. The ion tail is typically straight, narrow, and faintly blue, pointing almost exactly in the direction opposite the sun. The dust tail is formed from the larger dust particles released by outgassing. These particles are not pushed by the solar wind as efficiently as the ions, and they lag behind the comet's motion, curving gently away from the sun in a broad, yellowish arc. The dust tail reflects sunlight, giving it its characteristic warm glow. As a result of these two tails pointing in slightly different directions, a bright comet can display a striking forked or curved tail structure, a shimmering spectral fan of light trailing behind the nucleus as it moves through the inner solar system. The most famous comet in history is Halley's Comet, formally designated 1 Halley, a short period comet that returns to the inner solar system approximately every 75 to 76 years. Its most recent perihelion, its closest approach to the Sun, was in 1986. Its next perihelion is expected in 2061. The English astronomer Edmund Halley, working in the early 18th century, analyzed historical records of bright comets observed in 1682, 1680, 1682, 1622, 1682, 1680, 1682, and earlier dates, and recognized that several of them had similar orbital characteristics. He proposed that these were not different comets, but the same comet returning repeatedly, and he predicted its next return. When the comet appeared on schedule in 1758, 16 years after Halley's death, it was named in his honor. Halley's comet has been observed by human beings for at least 2,200 years. Every 75 to 76 years, it makes its appearance, blazing across the inner solar system, visible to the naked eye, trailing its tails across the sky. Julius Caesar may have seen it. William the Conqueror's soldiers saw it and flinched. Mark Twain was born in 1835 during one of its apparitions, and died in 1910 during the next. He noted the coincidence with characteristic wit. When Halley's comet last swept through the inner solar system in 1986, a small fleet of spacecraft was waiting for it. The European Space Agency's Giotto probe flew within 600 kilometers of the nucleus, close enough to return the first images of a comet's nucleus ever taken. What it revealed was a dark, irregular, potato-shaped object approximately 15 kilometers long and 8 kilometers wide. Its surface blacker than charcoal, with bright jets of gas and dust erupting from active regions where the sun's heat was penetrating the crust. The most intimate encounter with a comet in the history of space exploration came in 2004, when the European Space Agency launched the Rosetta spacecraft on a decade-long journey to rendezvous with comet 67P slash Churyumov-Gerasimenko, Rosetta reached the comet in 2014 and spent the next 2 years orbiting it, mapping its surface, analyzing its chemical composition, and watching it become increasingly active as it approached the sun. In November 2014, Rosetta released a small lander called Philae, which became the first spacecraft to land on a comet nucleus. Philae bounced twice on the comet's surface before settling in the shadow of a cliff. Its solar panels receiving too little light to keep it fully operational, but in the brief period before its batteries faded, it returned scientific data of extraordinary value. The composition of comet 67P revealed by Rosetta was rich in organic molecules, complex carbon-based compounds, including glycine, one of the amino acids that are the building blocks of proteins in all living organisms on Earth. This finding added to a body of evidence suggesting that comets may have played a role in delivering organic molecules to the early Earth, perhaps contributing to the chemical inventory from which life eventually emerged. The water in comets has also been compared to Earth's water. If the water delivered by comets to the early Earth had a chemical signature similar to Earth's ocean water, it would support the hypothesis that a significant fraction of Earth's oceans arrived from space, carried by comets, impacting the early Earth during a period called the Late Heavy Bombardment, approximately 3.9 billion years ago. The results from Rosetta's water analysis were complex. The water in comet 67P had a different isotopic composition from Earth's ocean water, containing more of a heavier form of hydrogen called deuterium than Earth's oceans do. This suggests that at least for this particular type of comet, they were not the primary source of Earth's water. Other comets, particularly those from the Jupiter family, may have compositions closer to Earth's water. The question of where Earth's oceans came from remains open. There is something deeply moving about the scientific story of comets. These small, frozen bodies, drifting in the darkness for billions of years, carrying within them the chemistry of the early solar system arrive in our skies as messengers from a time before the Earth existed. They are, in a very real sense, time capsules. Material that has been preserved, almost unchanged, since the solar system was new, suddenly exposed to sunlight, suddenly communicating its contents to the instruments of curious beings on a small planet. Every comet that passes through the inner solar system leaves a trail of debris behind it, a stream of dust and small particles scattered along its orbit. When the Earth crosses one of these debris streams, as it does regularly in its annual journey around the sun, those particles enter the atmosphere and burn up as meteors, the shooting stars we will explore in our next section. But the comet itself, if it survives its passage near the sun, heads back out into the cold dark of the outer solar system. Its outgassing slows as it recedes from the sun's warmth. Its coma shrinks. Its tails fade. The spectacle of light and vapor withdraws, and the comet becomes again what it always was at heart, a small, dark, frozen body returning to the cold. And it will be back, perhaps in 76 years, perhaps in 10,000, perhaps not for 1,000,000. But it will return because its orbit is bound to the sun. However wide and slow that orbit might be, it was always going to come back. From the very beginning of the solar system, its path was set, curving out into the dark and returning, like sleep, like breath, like every natural rhythm that carries us through the night, out into the darkness, and gently in time returning. Let your breathing follow that rhythm now. The long, slow arc outward on the exhale, the gentle return on the inhale, out into the dark and back again, over and over, soft and slow and faithful. There are certain nights of the year when the sky becomes generous, when lying on your back in the dark, eyes open and patient, you might see one, and then another, and then another, brief, bright scratches of light crossing the sky in the space of a second or less, appearing and vanishing so quickly that you are never quite sure, for a moment, whether you really saw it, or whether your tired and willing mind simply imagined it. another one comes, and you know. Meteor showers are among the most accessible wonders the night sky offers. No telescope required, no special equipment, no training or expertise, just darkness and patience and a willingness to lie still and look up, and the sky will do the rest. A meteor, what most people call a shooting star, though it has nothing to do with stars, is the streak of light produced when a small piece of space debris enters Earth's atmosphere at high speed and burns up through friction with the air. The debris itself, before it enters the atmosphere, is called a meteoroid. The streak of light it produces is the meteor. And if any fragment of it survives the fiery passage through the atmosphere and reaches the ground, that surviving fragment is called a meteorite. Most meteors are produced by extraordinarily small particles. A typical meteor visible to the naked eye is produced by a particle no larger than a grain of sand, or at most a small pebble. The light comes not from the particle itself burning, but from the air around it. The particle moves so fast, typically between 11 and 72 kilometers per second, depending on the geometry of its entry, that it compresses the air ahead of it into a superheated plasma that glows brilliantly. The particle itself is usually completely vaporized within seconds, leaving nothing behind but a briefly glowing trail of ionized air that fades in a second or two. The speed is almost impossible to intuit. At 70 kilometers per second, you could travel from one side of the continental United States to the other in approximately 60 seconds. A particle moving at this speed, striking the upper atmosphere, releases its kinetic energy almost instantaneously, converting the energy of motion into light and heat with an efficiency that produces a streak of light visible from hundreds of kilometers away on any given clear night. A careful observer under dark skies can expect to see between 5 and 10 meteors per hour. Random, sporadic meteors produced by dust and debris scattered through the inner solar system. The background noise of the cosmic environment through which Earth moves. These sporadic meteors come from all directions. The accumulated debris of countless comets and asteroid collisions spread through the solar system over billions of years. But several times a year, the rate increases dramatically when the Earth's orbit carries it through the debris trail left behind by a comet. The sky lights up. As we discussed in our section on comets, every comet that passes through the inner solar system sheds material along its orbit, dust and small particles released by outgassing, scattered along the comet's path over centuries and millennia. This material spreads into a broad stream following the comet's orbital path. When Earth crosses this stream, the particles enter the atmosphere in parallel paths, all moving in the same direction, producing many more meteors than usual, a meteor shower, because all the particles in a shower travel in parallel paths. They appear to radiate from a single point in the sky, the radiant. This is a perspective effect. The same reason parallel train tracks appear to converge at a point in the distance. The radiant is simply the direction from which the particles are approaching. Meteor showers are named for the constellation in which their radiant lies. The Perseids appear to radiate from the constellation Perseus. The Leonids radiate from Leo. The Geminids from Gemini. The Perseid meteor shower, which peaks every year around the 12th and 13th of August, is perhaps the most beloved meteor shower of the year in the northern hemisphere. It is produced by the debris trail of Comet 109P/Swift-Tuttle, a large comet that last passed through the inner solar system in 1992 and will not return until approximately 2130. At its peak, the Perseids can produce between 50 and 100 meteors per hour under dark skies, sometimes more, in particularly rich sections of the debris stream. The timing in the warm nights of late summer makes them accessible to many people who might not otherwise brave cold nights for astronomical observation. The Leonid meteor shower, peaking around the 17th of November each year, is associated with comet 55P/Tempel-Tuttle. In most years, the Leonids produce a modest display of perhaps 10 to 15 meteors per hour, but approximately every 33 years, when Earth passes through the densest part of the debris stream close to the comet's actual orbit. The Leonids can produce a meteor storm, a display of hundreds or even thousands of meteors per hour, so intense that observers have described the sky as appearing to rain fire. The Leonid meteor storm of 1833 was one of the most spectacular astronomical events in recorded American history. Observers described tens of thousands of meteors per hour at the peak, filling the sky so densely that people woke from sleep, believing the world was ending. The event was deeply significant in the history of meteor science. It led directly to the recognition that meteor showers have an annual periodicity and originate from specific points in the sky, laying the groundwork for our modern understanding of their cometary origin. The Geminid meteor shower, peaking around the 13th and 14th of December, is in several ways the most remarkable of the annual showers. It typically produces the highest rate of any annual shower, up to 120 or more meteors per hour under ideal conditions. Its meteors are relatively slow, bright, and often colorful. Many observers describe seeing yellow, green, and occasionally blue meteors in the Geminids. And unlike every other major annual shower, the Geminids are not produced by a comet. Their source is an asteroid, a rocky body designated 3209 Phaethon. Phaethon has a highly elliptical orbit that carries it closer to the Sun than any other named asteroid, bringing it within approximately 21 million kilometers of the Sun at perihelion, close enough that the Sun's heat causes rocky material to fracture and be expelled from its surface in a process that mimics, in a limited way, the outgassing of a comet. Over time, this material has spread along Phaethon's orbit, creating the debris stream that produces the Geminids. Why a rocky asteroid should produce such a prolific meteor shower is not fully understood. Phaethon may be the remnant of a comet that has exhausted its ices and now appears rocky, a dead or dying comet masquerading as an asteroid. or it may represent a category of object that blurs the traditional distinction between comets and asteroids. The solar system is not always as neatly categorized as our textbooks suggest. Other notable annual showers include the quadrantids, peaking in early January with a very brief but intense peak. Their source believed to be the asteroid 2003A1, itself thought to be a fragment of a larger comet that broke apart several centuries ago. The Eta Aquariids, peaking in early May, are produced by debris from Halley's Comet, as is the Orionid shower, peaking in late October. Earth crosses Halley's debris trail twice a year, in two different places, producing two separate annual showers: the Delta Aquariids, the Lyrids, the Draconids, the Taurids. The calendar of meteor showers is full, distributed through the months of the year in a pattern that reflects the geometry of Earth's orbit and the distribution of cometary debris streams in the inner solar system. Watching a meteor shower requires very little. A clear sky, a dark location away from city lights, a reclining position, a lawn chair, a blanket on the ground, anything that allows you to look comfortably upward for an extended period without straining your neck. It requires patience, because meteors do not arrive on schedule. They come in clusters and lulls, sometimes 3 in a minute, then a quiet spell of several minutes, then a bright one that surprises you just as your attention was beginning to drift. It requires letting your eyes relax and soften their focus, looking at the sky as a whole rather than fixing on any particular point. The peripheral vision, dominated by the rod cells we discussed in our first section, is more sensitive to the brief flash of a meteor than direct gaze. Looking slightly away from the area you most expect a meteor is, counterintuitively, the most effective way to see them. And it requires accepting that some of the best meteors will come when you are least ready for them. When you have looked away for a moment, or blinked, or turned to say something to the person beside you. This is part of the character of meteor watching. It rewards presence and attention, but it never quite gives you everything you ask for. It keeps something in reserve. There is an intimacy to watching meteors that other forms of astronomical observation do not quite have. A telescope creates distance as well as magnification. It mediates between you and the sky, turning observation into a technical act. But watching meteors requires nothing between you and the night, just your body lying still and the sky above, and the occasional brief miracle of a grain of ancient comet dust burning up in a flash of light kilometers above your head. That particle, that tiny fragment of frozen debris from the outer solar system, has been traveling since before the Earth existed. It left its parent comet millions of years ago, perhaps, or billions. It has been drifting in an orbit around the sun, gradually migrating through gravitational interactions, until tonight, on this particular orbit, Earth arrived at this particular place in space, and the particle entered the atmosphere at this particular moment, and you, lying on your back, looking up, saw it. The meeting of an ancient traveler and a pair of human eyes across 4.5 billion years of solar system history. It lasted less than a second. There is a Japanese concept that captures something of this quality. The word mono, no aware, sometimes translated as the pathos of things, or the gentle sadness of impermanence. It is the feeling evoked by something beautiful precisely because it is brief. The falling of cherry blossoms, the last light of a sunset, a meteor crossing the dark. The brevity is not a deficiency. It is the whole point. The flash of light is beautiful because it passes, because it is unrepeatable, because no other particle from that particular comet will enter the atmosphere at that particular angle, at that particular moment, ever again. Because in the entire history of the universe, this specific event will happen exactly once. And you were there for it. Whatever meteors you have seen in your life, whether you saw them as a child, lying in a garden on a summer night, or as an adult, pulled outside by the promise of a shower and rewarded beyond expectation. Those moments are uniquely yours, unique in all the history of the solar system. The ancient debris of ancient comets, choosing, in a sense, your eyes to burn out in front of. There is something in the meteor that mirrors the quality of attention itself. Brief, unrepeatable, arriving when least expected. Gone before you can fully register it, leaving only the faint memory of its passage, and the sky dark and deep and unchanged above you, as if it never happened at all, except that it did, and you can carry that with you into sleep tonight. The sense of having been briefly, perfectly present for something ancient and fleeting and beautiful. Close your eyes now, if you have not already. Imagine the sky above you, dark and clear and deep. And somewhere up there, in the high cold air, a grain of ancient comet dust is burning. Just for you, just for this moment. Everything you have ever seen was carried to your eyes by light. The color of a flower, the face of someone you love, the blue of the daytime sky, and the silver of the moon, and the brief, bright scratch of a meteor crossing the dark. All of it arrived at the surface of your eye as light, as electromagnetic radiation, translated by the biology of your retina and the extraordinary processing of your brain into the world. You experience as visual reality, but visible light, the narrow band of electromagnetic radiation that your eyes can detect is only a tiny fraction of the full spectrum of light that exists. The universe is broadcasting constantly in wavelengths and frequencies that stretch far beyond what human eyes were ever built to see, and it is only in the last century or so that we have built instruments capable of listening to those other channels, and in doing so revealed a universe far stranger, richer, and more beautiful than the one our eyes alone could ever have shown us. The electromagnetic spectrum is the full range of electromagnetic radiation, ordered by wavelength and frequency. Wavelength and frequency are inversely related. The shorter the wavelength, the higher the frequency, and the higher the frequency, the more energy each photon carries. At one end of the spectrum are radio waves with wavelengths that can be longer than a football field. At the other end are gamma rays, wavelengths smaller than the nucleus of an atom. In between, running from long wavelength to short, are microwaves, infrared radiation, visible light, ultraviolet radiation, and X-rays. Visible light, the thin band of wavelengths our eyes can detect, occupies a remarkably small slice of this full spectrum. If you stretched the entire electromagnetic spectrum out along a line running from one end of a continent to the other, the portion visible to human eyes would be less than a centimeter wide. We are, in terms of our natural sensory equipment, nearly blind to the universe. But we have built extensions to our senses, and what those extensions have revealed has transformed our understanding of the cosmos in ways that earlier generations of astronomers could not have imagined. Let us begin at the long wavelength end of the spectrum with radio waves. Radio astronomy was born by accident in the early 1930s when an American engineer named Carl Jansky was investigating sources of static interference in radio communications. He built a large antenna to survey the sources of radio noise in the sky. And among the various signals he detected was a persistent hiss that moved with the stars. That is, it came from a fixed direction in the sky rather than from any terrestrial source. Jansky traced this signal to the center of the Milky Way, making the first detection of radio emission from an astronomical source. The implications took time to be fully appreciated, but eventually radio astronomy grew into one of the most productive branches of observational science. Radio waves from space carry information about some of the universe's most energetic and exotic phenomena. Pulsars, those rapidly rotating neutron stars left behind by supernova explosions, were discovered through their radio pulses. The cosmic microwave background radiation, the faint afterglow of the Big Bang itself, filling the entire sky uniformly, was discovered accidentally in 1964 by radio astronomers at Bell Laboratories, who initially thought the signal was caused by pigeon droppings in their antenna. Radio telescopes can be enormous. The largest single-dish radio telescope in the world is the 500-meter aperture spherical telescope in China, known as FAST, built into a natural bowl-shaped valley. Its reflective surface, covering an area equivalent to approximately 30 football fields, but even larger effective apertures can be achieved by combining signals from multiple radio telescopes spread across vast distances. A technique called interferometry, the Event Horizon Telescope, which produced the first images of black holes in 2019 and 2022, is a network of radio telescopes distributed across the Earth, functioning together as a single instrument with an effective aperture the diameter of our planet, moving along the spectrum to shorter wavelengths. We encounter microwaves. The cosmic microwave background we just mentioned is, as its name suggests, microwave radiation, light with wavelengths of a few millimeters, stretched to these long wavelengths by the expansion of the universe from its original much shorter wavelengths at the time of emission, approximately 380,000 years after the Big Bang, mapping the cosmic microwave background in extraordinary detail, has revealed the seeds of all the structure in the universe. Tiny fluctuations in temperature of only 100,000th of a degree that represent the original variations in density from which galaxies, clusters, and the cosmic web eventually grew. Infrared radiation occupies the portion of the spectrum just beyond the red end of visible light, with wavelengths longer than our eyes can detect. Infrared astronomy is particularly valuable for two reasons. First, infrared light can penetrate dust clouds that block visible light, meaning that infrared telescopes can see through the dusty plain of the Milky Way and into regions that are completely opaque in visible light, including the galactic center. Second, objects that are too cool to emit significant visible light, such as protostars still embedded in their birth clouds, cool brown dwarf stars, and the planets of other solar systems, emit strongly in the infrared. The James Webb Space Telescope launched in December 2021 and operational from 2022, is primarily an infrared observatory. It is the largest and most powerful space telescope ever built, with a mere 6.5 meters across, composed of 18 hexagonal gold-coated beryllium segments deployed in space nearly 1.5 million kilometers from Earth. Webb has transformed our view of the universe in the infrared, revealing the earliest galaxies ever observed, peering into stellar nurseries with unprecedented clarity, and analyzing the atmospheres of planets orbiting other stars. Visible light, the thin band of wavelengths our eyes evolved to detect, corresponds to the peak of the sun's emission spectrum. Our eyes are tuned to the light that our star most abundantly produces, a consequence of billions of years of evolution under this particular sun. Visible light astronomy remains foundational, even as other wavelength bands have opened new windows on the universe. The Hubble Space Telescope, operating primarily in visible and ultraviolet light, has produced some of the most iconic and scientifically productive astronomical observations of the modern era. Ultraviolet light lies just beyond the violet end of visible light, with wavelengths shorter than our eyes can detect. Earth's atmosphere absorbs most incoming ultraviolet radiation, a fortunate circumstance for life on Earth, since high-energy ultraviolet light damages biological molecules, including DNA. The ozone layer in the upper atmosphere is particularly effective at absorbing the most damaging ultraviolet wavelengths. But this same protective absorption means that ultraviolet astronomy must be conducted from space, above the atmosphere, where ultraviolet telescopes can observe the hot, energetic phenomena. Massive young stars, stellar coronae, gas in galaxy halos that emit strongly in these wavelengths. X-rays are produced by some of the most energetic phenomena in the universe. The superheated gas in galaxy clusters, heated to temperatures of tens of millions of degrees by the gravitational energy of the cluster, glows brilliantly in X-rays, black hole accretion disks, where gas is heated to extreme temperatures as it spirals inward, are powerful X-ray sources. Neutron stars, pulsars, and the remnants of supernova explosions all produce significant X-ray emission. X-ray astronomy, conducted entirely from space. Since Earth's atmosphere is completely opaque to X-rays, has revealed the universe's most violent and energetic processes. The Chandra X-ray Observatory, launched in 1999 and still operational, has been one of the most scientifically productive space telescopes ever built. Its images of galaxy clusters, black holes, and supernova remnants in X-ray light reveal structures and processes completely invisible in any other wavelength. Gamma rays are the most energetic form of electromagnetic radiation, with wavelengths shorter than the nucleus of an atom, and photon energies millions of times greater than those of visible light. Gamma ray astronomy detects the universe's most extreme events, the explosions of massive stars, the mergers of neutron stars, the annihilation of matter and antimatter. Gamma ray bursts, brief, enormously energetic flashes of gamma radiation detected from billions of light years away, are the most powerful explosions known in the universe, releasing more energy in a few seconds than the sun will emit over its entire 10 billion year lifetime. The picture that emerges from combining observations across the full electromagnetic spectrum is of a universe that looks completely different at each wavelength. A galaxy cluster that appears as a faint smear of stars in visible light blazes brilliantly in X-rays, its hot gas filling the space between the visible galaxies with a luminosity that exceeds all its stars combined. A nearby star-forming region that appears dark and featureless in visible light, blocked by dust, glows with the warm light of nascent protostars in the infrared. The Milky Way, a pale band of stars in visible light, reveals in radio waves the sweeping structure of its spiral arms, outlined by the emission of cold hydrogen gas that pervades the disk. The universe speaks in many languages, We have spent most of human history hearing only one of them: the development of multi-wavelength astronomy, the ability to observe the universe across the full electromagnetic spectrum, is one of the greatest expansions of human perception in history. It is as if we spent millennia hearing only a single note, and then, in the space of a century, discovered the full range of sound. And there is still more, as we touched on in our section on black holes. Gravitational waves represent a completely new channel of astronomical observation, not electromagnetic radiation at all, but ripples in space-time itself, carrying information about events that produce little or no light. And neutrino astronomy, the detection of the nearly massless, barely interacting particles produced by nuclear reactions in stellar cores and supernova explosions, opens yet another window on processes invisible to any form of light. The universe has been broadcasting in all of these channels simultaneously for all of time. We are only now, in this brief and remarkable century, beginning to tune in. There is a gentle wonder in that, in knowing that right now, as you rest in the quiet dark, the room around you is filled with radio waves from distant pulsars, with the microwave afterglow of the Big Bang, with infrared radiation from warm objects, with gamma rays from distant explosions, all of it passing through you, carrying its ancient information in channels your body cannot detect and your mind cannot directly access. You are immersed in an invisible ocean of light, all of it real, all of it informative, all of it carrying the universe's long story in wavelengths, too long or too short or too energetic for your eyes to translate. You do not need to detect it. You do not need to measure it or interpret it. It is simply there, all around you and through you, the universe communicating with itself in every frequency at once. You are part of that communication. Your body emits infrared radiation, the warmth that a thermal camera would show as a soft glow in the dark. You are visible in the infrared, a warm shape in the cool of the room, radiating gently outward in wavelengths your eyes You are part of the spectrum, radiating gently, warm in the dark, resting in the invisible ocean. Let your awareness soften now. Let the visible world, the ceiling, the walls, the familiar shapes of the room become less distinct. Let your eyes rest behind closed lids and trust that the world is still there, even where you cannot see it, especially where you cannot see it. There is a particular kind of vertigo that comes from truly thinking about the scale of the universe, not the dizzying, unpleasant kind. Something gentler than that. A slow dissolving of the ordinary sense of proportion. The way the horizon seems to expand when you climb to the top of a hill and realize the world is so much larger than the valley you have been living in. A loosening of the tight, familiar boundaries of the everyday, replaced by something vast and open. And once you settle into it, surprisingly peaceful. The universe is very, very large, and the numbers we use to describe its size are so far beyond ordinary human experience that they require a different kind of engagement than arithmetic. They are not numbers to be calculated with. They are numbers to be felt, held loosely, approached with the same openness you might bring to a poem or a piece of music that moves you before you fully understand it. Let us begin small and work outward. The Earth is approximately 12,742 kilometers in diameter at the equator. If you could drive a car at highway speed without stopping, straight through the Earth from one side to the other, it would take you approximately 5 to 6 days. That feels manageable. That is a scale the body can almost intuit. The moon is approximately 384,000 kilometers from Earth. If you drove that same car at highway speed toward the moon without stopping, the journey would take approximately 5 to 6 months, still comprehensible if you have ever thought about a very long road trip. The sun is approximately 150 million kilometers from Earth. One astronomical unit. That car journey would take approximately 170 years. Your great-great-grandmother would need to have started driving the moment she was born for you to arrive today, the outermost planet, Neptune, orbits the Sun at approximately 30 astronomical units, approximately 4.5 billion kilometers. The car trip to Neptune would take approximately 5,000 years, roughly the span of recorded human history. The Voyager 1 spacecraft, launched in September 1977, is currently the most distant human-made object in existence. It is now well beyond the orbit of Neptune, in interstellar space, having crossed the boundary of the heliosphere, the bubble of solar wind that surrounds our solar system. In 2012, it has been traveling for approximately 49 years and is currently somewhere around 24 billion kilometers from the Sun. And yet, in the context of the galaxy, Voyager 1 has barely moved. The nearest star to our Sun, Proxima Centauri, is approximately 4.2 light years away. A light year is the distance light travels in 1 year. Light moves at approximately 299,792 kilometers per second. Let us simply say approximately 300,000 kilometers per second. In 1 year, light travels approximately 9.5 trillion kilometers. 4.2 light years is approximately 40 trillion kilometers. Voyager 1, traveling at approximately 61,000 kilometers per hour, the fastest speed any human-made object has ever achieved, would take approximately 73,000 years to reach Proxima Centauri if it were headed in that direction. It is not. But the figure gives a sense of the gulf between even our nearest stellar neighbor and ourselves. The light you see from Proxima Centauri tonight left that star approximately 4.2 years ago. You are not seeing it as it is now. You are seeing it as it was 4.2 years in the past. This is true of every star in the sky. You are never seeing any of them as they are in this moment. You are always seeing them as they were, the delay proportional to their distance. The North Star, Polaris, is approximately 433 light years away. The light reaching your eyes from Polaris tonight left that star approximately 433 years ago. Around the year 1693, during the time of Isaac Newton, several decades after the death of Galileo. Deneb, the bright star in the constellation Cygnus, is approximately 2,600 light years away. Its light left on its journey toward Earth approximately 2,600 years ago, around the time of the ancient Greek philosophers Socrates, Plato, Aristotle. The Orion Nebula, that glowing stellar nursery below the belt of Orion, is approximately 1,344 light years away. Its light has been traveling since approximately the 6th century, since the time of early medieval Europe and the Tang dynasty in China. The Andromeda galaxy, visible to the naked eye as a faint smudge of light on dark nights, is approximately 2.5 million light years away. The light you can see from it tonight set out on its journey approximately 2.5 million years ago, when our earliest human ancestors, the Australopithecines, were walking the plains of Africa, when no member of our genus Homo yet existed, when the ice ages had not yet begun. You are seeing Andromeda as it was before humanity existed. The most distant galaxies detected by the James Webb Space Telescope are approximately 13.4 billion light years away. We see them as they were approximately 400 million years after the Big Bang, when the universe was less than 3% of its current age. These are among the first galaxies that ever formed, their ancient light just now completing a journey of almost incomprehensible length to arrive at our telescopes. The observable universe, the sphere of space from which light has had time to reach us in the 13.8 billion years since the Big Bang, has a radius of approximately 46 billion light years. This number is larger than 13.8 billion light years because the universe has been expanding during the time that light has been traveling. Space itself has stretched, carrying distant objects farther from us, even as their light was in transit. The diameter of the observable universe is therefore approximately 93 billion light years. Beyond the observable universe, the universe almost certainly continues, perhaps infinitely, we simply cannot see it because its light has not had time to reach us. There may be regions of the universe that are forever beyond our ability to observe, not because they do not exist, but because the expansion of the universe is carrying them away faster than light can travel. The universe may be infinite. We genuinely do not know. Let that be a quiet and open thought rather than an unsettling one. The honest acknowledgement of a boundary to our knowledge, held without anxiety. Astronomers have developed various techniques for measuring cosmic distances, and the challenge of doing so accurately has driven some of the most creative and important developments in the history of astronomy. For relatively nearby stars, the method of parallax works beautifully. The tiny apparent shift in a star's position against the background of more distant stars, measured at different points in Earth's orbit, allows a precise geometric calculation of the star's distance. The European Space Agency's Gaia spacecraft, launched in 2013, has measured precise parallax distances for approximately 1.5 billion stars in our galaxy, for distances beyond the reach of parallax. Astronomers use a series of overlapping techniques called the cosmic distance ladder. Each rung of the ladder uses a different method, calibrated against the previous rung. Cepheid variable stars, whose period luminosity relationship we discussed in our section on galaxies, serve as one of the most important rungs. Type Ia supernovae, explosions of white dwarf stars that always reach approximately the same peak luminosity, serve as standard candles at even greater distances, visible across billions of light years. The accuracy of the cosmic distance ladder has improved enormously in recent decades, but it is still a subject of active refinement, a discrepancy known as the Hubble tension, a disagreement between different methods of measuring the rate of expansion of the universe, is one of the most important open problems in cosmology, suggesting that either our measurements have systematic errors, or our understanding of the universe's evolution is incomplete. even the most precise measurement of a vast distance is still, in some sense, an act of inference. We cannot travel to a distant galaxy and measure its distance directly. We use the logic of physics and the properties of light and the geometry of space to reason our way to a number. The number is our best current understanding, not a final truth. This is not a weakness of science. It is its character. Science is always provisional, always refining, always open to revision in the light of new evidence. The distances we assign to the stars and galaxies are the best answers we currently have, held with appropriate confidence and appropriate humility. There is a beautiful word in Japanese, yujin, that describes a profound awareness of the universe that triggers emotional responses too deep for words. Not the sharp, bright feeling of wonder at a specific discovery, but a deeper, quieter state. The feeling of standing at the edge of something limitless and feeling your own smallness not as diminishment, but as belonging, as being part of something that will never be fully mapped or fully understood, and finding peace rather than anxiety in that incompleteness. The scale of the universe can produce yujin if you let it, not the vertigo of being overwhelmed, but the stillness of being held inside something genuinely, irreducibly vast. You are here on a planet 12,700 kilometers across, orbiting a star 150 million kilometers away, in a galaxy 100,000 light years across, in a universe 93 billion light years wide, whose edges we cannot see, whose full extent we cannot know, whose age and depth carry a history we are only beginning to read. And in the middle of all of that, you are breathing, slowly, gently, in the warm dark of a room on a small planet, your body perfectly calibrated for this particular gravity, this particular temperature, this particular thin shell of breathable air. The distances are real. The scale is real. And so is this, the small, warm, immediate fact of your existence here now, at the center of your own observable universe. Everything you have ever seen, everyone you have ever loved, every sensation you have ever felt has occurred within a sphere of space, barely perceptible on the cosmic scale. And it has been enough. It has been more than enough. Let the distances recede now. Let the light years fold back into the dark. Let the universe be as large as it is, out there, beyond the walls and the night, while you remain here, small and warm and still. The scale of everything does not require your management. It only asks, very quietly, for your occasional attention. And then it lets you rest. Most of the universe is missing, not lost exactly, not gone anywhere, simply invisible to every instrument we have ever built, undetectable by any form of light across any wavelength of the electromagnetic spectrum, present only as an absence, a gravitational signature, a gap in our accounting, a shape defined not by what it is, but by what it does. This is one of the most extraordinary facts in all of modern science. When astronomers add up everything they can see, every star, every galaxy, every cloud of gas and dust, every planet, every black hole, every form of matter that interacts with light in any way, they find that it accounts for only approximately 5% of the total energy content of the universe. 5%. The remaining 95% is composed of two things we cannot directly see, cannot yet explain from first principles, and understand only in the broadest outline. They are called dark matter and dark energy, not because they are dark in any visual sense, but because they are unknown. Dark in the sense of opaque to our current understanding. Dark in the sense of a room you have not yet entered, whose contents you can only guess at from what you hear moving around inside. Let us begin with dark matter. The first serious evidence for dark matter came in the 1930s, when the Swiss-American astronomer Fritz Zwicky was studying the Coma cluster, a large cluster of galaxies, approximately 320 million light years from Earth. Zwicky measured the velocities of galaxies moving within the cluster and found something puzzling. The galaxies were moving too fast. If the cluster contained only the visible matter he could see, its gravitational pull would not be nearly strong enough hold the galaxies together at those speeds, they should have flown apart long ago. Zwicky proposed that the cluster must contain a large amount of invisible mass, matter, that contributed gravitational pull without emitting any light. He called it dunkel materie, dark matter. The suggestion was largely ignored for decades. The evidence became impossible to dismiss in the 1970s when the American astronomer Vera Rubin, working with her colleague Kent Ford, made a series of careful measurements of the rotation of spiral galaxies in a simple gravitational system. Objects farther from the center should orbit more slowly, just as the outer planets in our solar system orbit the sun more slowly than the inner ones. But Rubin and Ford found that the outer stars of spiral galaxies orbited at roughly the same speed as the inner stars, or even faster. The rotation curves of galaxies were flat when they should have been declining. The only way to explain flat rotation curves is if the mass of a galaxy does not end where its visible stars end. If galaxies are embedded in vast, extended halos of invisible matter that contributes gravitational pull throughout and beyond the visible disk of the galaxy, flattening the rotation curve by providing additional gravitational support at large distances from the center. Vera Rubin's work transformed the dark matter hypothesis from a fringe suggestion into a central pillar of cosmology. She spent her career measuring galaxy rotation curves, and her results were consistent. Galaxy after galaxy, the rotation curves were flat, and the invisible mass required to explain them was enormous. For most spiral galaxies, the dark matter halo appears to contain approximately 5 to 10 times as much mass as the visible stellar disk. Dark matter has since been confirmed by multiple independent lines of evidence: gravitational lensing, the bending of light from distant objects by the mass of intervening structures, reveals concentrations of mass that cannot be accounted for by the visible matter alone. In a particularly compelling case called the bullet cluster, two galaxy clusters that have recently passed through each other show a clear separation between the hot gas slowed down and piled up during the collision, visible in X-rays, and the dark matter, which passed through without interacting, its position revealed by gravitational lensing. This separation makes it very difficult to explain the observations without invoking dark matter as a real physical substance. The cosmic microwave background, mapped in exquisite detail by the Planck satellite, encodes information about the relative amounts of ordinary matter, dark matter, and dark energy in the universe. The pattern of temperature fluctuations in the cosmic microwave background fits precisely a universe composed of approximately 5% ordinary matter, approximately 27% dark matter, and approximately 68% dark energy. This concordance between completely independent lines of evidence makes the basic dark matter picture extremely compelling. But what is dark matter made of? This is where the mystery deepens, because we genuinely do not know. Dark matter does not emit light. It does not absorb light. It does not interact with ordinary matter through the electromagnetic force at all, which is why it is invisible. It interacts gravitationally, and it may interact through the weak nuclear force, one of the 4 fundamental forces of nature. But if so, those interactions are extremely rare. The leading theoretical candidate for dark matter particles is a class of hypothetical particles called WIMPs, weakly interacting massive particles. These are particles predicted by various extensions of the standard model of particle physics, with masses perhaps 10 to 1,000 times the mass of a proton, and interaction rates consistent with the gravitational properties of dark matter we observe. There have been decades of extremely sensitive experiments searching for WIMPs, deep underground detectors shielded from cosmic rays, looking for the tiny signal that would be produced if a WIMP occasionally collided with an atomic nucleus. So far, no confirmed WIMP detection has been made. Other candidates include axions, very light particles originally proposed to solve a different problem in particle physics, and sterile neutrinos, heavier cousins of the familiar neutrinos that interact even more weakly than ordinary neutrinos. There are also more exotic proposals, including primordial black holes and various forms of macroscopic dark objects. The honest answer is that we do not yet know what dark matter is. It could be one of the candidates already proposed. It could be something entirely new that nobody has yet imagined. The search continues with ever more sensitive instruments and ever more creative experimental approaches. And then there is dark energy, which is stranger still. In 1998, two independent teams of astronomers were using Type Ia supernovae as standard candles to measure the expansion history of the universe. The expectation was that they would find the expansion of the universe slowing down over time as the gravitational attraction of all the matter in the universe gradually pulled things back together. What they found instead astonished the entire scientific community. The expansion of the universe is not slowing down. It is speeding up. The universe is expanding, and the rate of that expansion is accelerating. Galaxies are not just moving apart. They are moving apart faster and faster as time goes on. Something is driving that acceleration. Something with a repulsive effect on the large-scale structure of the universe, pushing space itself apart with increasing vigor. This something is called dark energy, and it currently constitutes approximately 68% of the total energy content of the universe, the dominant component of everything that exists. The simplest explanation for dark energy is that it is a property of empty space itself. Even a perfect vacuum, completely empty of matter and radiation, carries an intrinsic energy density, what physicists call the cosmological constant, a term Einstein originally introduced into his equations of general relativity before observations of the expanding universe led him to consider it unnecessary. He called it his greatest blunder. It turns out he may have been premature in that judgment. The cosmological constant represents a kind of background energy woven into the fabric of space, unchanging as the universe expands. As space expands, total amount of cosmological constant energy increases, providing the repulsive pressure that drives the acceleration. The more space there is, the more dark energy there is, and the faster the expansion accelerates in a self-reinforcing process that will continue as far as current physics can tell forever. The very distant future implied by dark energy is one of extraordinary quiet. As the expansion of the universe accelerates, distant galaxies will recede from us faster and faster, their light increasingly redshifted, until eventually they cross the cosmic horizon and disappear from our observable universe entirely in the far future, trillions of years from now. The Milky Way and its gravitationally bound companions will be the only galaxies visible. The rest of the universe will have retreated beyond the horizon, invisible, inaccessible. Future astronomers, if any exist, will look out at a sky containing only the stars of their own galaxy, with no evidence that any other galaxy has ever existed. The cosmic microwave background will have faded to undetectable levels. The universe's history will have been erased from the observable sky. They will have no way of knowing what we know now. There is a strange poignancy in that thought. We happen to live at a time when the universe's history is still legible, when the other galaxies are still visible, when the cosmic microwave background is still detectable, when the evidence for dark matter and dark energy and the Big Bang is still available to patient observation and careful reasoning. We live in a fortunate cosmic moment. The mystery of dark matter and dark energy is not a failure of science. It is science working exactly as it should, acknowledging what it does not know, mapping the boundaries of its understanding, building experiments to push those boundaries outward, proposing hypotheses and testing them rigorously. The universe has always been larger and stranger than our current best understanding. Every generation of scientists has discovered that the universe is more complex, more varied, more surprising than their predecessors imagined. There is no reason to think this process has reached its end. 95% of the universe remains, in a meaningful sense, unknown. this is not a cause for anxiety. It is an invitation, the largest invitation ever extended by the universe itself to the curious minds that have somehow assembled themselves within it. Most of what exists is invisible. Most of what drives the universe's evolution is unknown. The night sky, which seems so open to our gaze, is hiding the vast majority of what is actually there in plain and permanent invisibility. And this is all right. You do not need to see everything to appreciate what you can see. You do not need to understand everything to rest comfortably inside the mystery. The dark matter is there, holding the galaxies in their shapes. Even though you cannot detect it, the dark energy is there, pushing space outward, even though it leaves no mark your senses can read. The invisible universe is holding you right now. The dark matter halo of the Milky Way surrounds you. The dark energy of the cosmological constant is woven into the fabric of the space around you. You are immersed in the invisible 95% at this very moment, as you have always been, as you always will be. And it is gentle, and it is steady, and it asks nothing of you. Simply rest inside the mystery. The universe does not require you to solve it. It only asks you to be here. Every story has a beginning, and the universe, as best as we can determine, is no different. Approximately 13.8 billion years ago, a number so large that it carries its own kind of silence. Everything that exists emerged from a state of extraordinary density and temperature, not an explosion in space, as the name might suggest. Not a firework going off in an existing void, but the beginning of space itself, the beginning of time itself, the moment before which the word before may not even have meaning. This is the Big Bang, and it is one of the most carefully supported and most profoundly strange ideas in all of human knowledge. Let us approach it slowly, the way you might approach a very still lake in the early morning, carefully, so as not to disturb it. The evidence for the Big Bang begins with the observation, first made systematically by Edwin Hubble in the 1920s, that the universe is expanding. every galaxy, in every direction we look, is moving away from us. The farther away a galaxy is, the faster it is receding. This is not because we are at the center of the universe. Any observer in any galaxy would see the same thing, because it is not the galaxies moving through space so much as space itself expanding, carrying the galaxies apart like raisins in a loaf of bread rising in the oven. Every raisin moves away from every other raisin as the bread expands, and no raisin is the center. If the universe is expanding now, then it was smaller in the past. Running the expansion backward in time, like rewinding a film, the universe becomes smaller and denser and hotter the further back you go, extrapolating backward far enough. You reach a moment when all the matter and energy in the observable universe was compressed into an unimaginably small, hot, dense state. This is the beginning, the initial singularity, or more precisely, the earliest moment that our current physics allows us to describe. The first fractions of a second after the Big Bang are the most exotic and the least well understood period in cosmic history. At the earliest times we can currently reason about, a period called the Planck epoch, corresponding to the first approximately 10 to the power of minus 43 seconds. The universe was so hot and dense that all four fundamental forces of nature may have been unified into a single force. The physics of this period requires a complete theory of quantum gravity that we do not yet possess. What we can describe begins slightly later. In the first fractions of a second, the universe was a seething plasma of elementary particles, quarks, leptons, bosons, interacting with extraordinary intensity at temperatures of trillions of degrees. In the first microseconds, quarks combined into protons and neutrons. The universe was still too hot for atomic nuclei to form. Any nucleus that assembled was immediately disrupted by the intense radiation. In the first 3 minutes, as the universe cooled through nuclear fusion temperatures, the lightest atomic nuclei formed. Protons and neutrons fused to produce helium nuclei. along with small amounts of deuterium and lithium. This process, called Big Bang nucleosynthesis, is one of the most powerful tests of the Big Bang model. The predicted abundances of hydrogen, helium, deuterium, and lithium from the theory match the observed abundances in the oldest, most primitive parts of the universe with extraordinary precision. Approximately 75% hydrogen and 25% helium by mass. Exactly what we find. For the next approximately 380,000 years, the universe remained a hot, opaque plasma. A fog of charged particles and radiation so dense that photons could not travel freely. The universe was like the interior of a star, bright everywhere, but impenetrable to light in the sense that no photon could travel very far before being scattered. And then, approximately 380,000 years after the Big Bang, the universe had cooled enough to approximately 3,000 degrees Celsius for electrons to combine with protons and helium nuclei to form neutral atoms. This event, called recombination, transformed the universe from an opaque plasma to a transparent gas in a cosmically brief period. For the first time, photons could travel freely through space without being scattered. The radiation released at this moment, the light of the universe becoming transparent, is still detectable today. It is the cosmic microwave background radiation we have discussed in earlier sections, stretched by nearly 14 billion years of cosmic expansion. From the visible light, it was at the moment of emission to the microwave radiation it is today. It fills the entire sky uniformly, a faint but measurable afterglow of the Big Bang itself, carrying in its tiny temperature fluctuations the seeds of all the structure the universe has since developed. The detection of the cosmic microwave background by Arno Penzias and Robert Wilson in 1964 was the decisive observational confirmation of the Big Bang model. For this discovery, they were awarded the Nobel Prize in Physics in 1978. After recombination, the universe entered a period called the Cosmic Dark Ages, a long, quiet epoch 200 million years, during which there were no stars and no galaxies. The universe was filled with neutral hydrogen and helium gas, slowly cooling, slowly being drawn together by gravity into the overdense regions that would eventually collapse into the first stars and galaxies. There was no light. The universe was dark in a way it has not been since. The end of the cosmic dark ages came with the birth of the first stars. Enormous, hot, massive objects formed from pure hydrogen and helium, with no heavier elements at all. These first stars are called population III stars. None have been directly observed. They formed so long ago, and any that remain would be so distant that detecting them directly is extraordinarily difficult, but their existence is inferred from theory and from the absence of heavier elements in the oldest observed stellar populations. The James Webb Space Telescope is searching for signs of these first stellar generations, peering back to within a few 100 million years of the Big Bang. The first stars lived brief, brilliant lives and died in supernovae, enriching the surrounding gas with the heavier elements their cores had forged. The second generation of stars formed from this enriched gas, and so on through successive stellar generations. The chemical complexity of the universe grew. Each generation of stars contributing new elements to the interstellar medium. Each generation making possible slightly more complex chemistry than the last. After perhaps 1 billion years, the first galaxies had assembled. The cosmic web, those vast filaments and sheets of matter, was taking shape. The universe was becoming recognizable, though still profoundly different from the relatively quiet, structured cosmos we inhabit today. And over the subsequent 12.8 billion years, the story we have been telling throughout this night unfolded. Stars and galaxies formed and evolved. Supernovae scattered heavy elements through the interstellar medium. Solar systems assembled around new stars. On at least one of those planets, and perhaps on many others, scattered through a universe of 2 trillion galaxies, chemistry organized itself into something that could replicate, and then into something that could sense, and then into something that could wonder. The Big Bang is often depicted as a violent, explosive event, a titanic release of energy, a catastrophic beginning. And in some senses it was. The temperatures and densities of the early universe were beyond anything that exists anywhere in the universe today. The processes that occurred in the first seconds were of extraordinary intensity. But think of it another way. The Big Bang was also an act of becoming, a transition from something we cannot describe, whatever preceded or accompanied the initial singularity, to something that would, over nearly 14 billion years of patient unfolding, produce galaxies and stars and worlds and life and awareness. Every atom in your body was present in some form in the first few minutes after the Big Bang. The hydrogen in the water molecules in every cell of your body was forged in Big Bang nucleosynthesis in the first 3 minutes of time. It has been part of stars, part of interstellar clouds, part of the ocean, part of rain, part of the bodies of other living things. And now it is here in you tonight as you rest. You are made of the oldest material in the universe. The hydrogen in you is as old as time itself. There are deep questions about the Big Bang that remain genuinely open. What caused it? What, if anything, came before it? Is our universe unique, or one of many, a member of a vast ensemble of universes, each with its own physical constants, its own history, its own character? These questions sit at the frontier of physics and philosophy, in a region where the tools of empirical science have not yet fully reached. The theory of cosmic inflation, proposed in the early 1980s by the physicist Alan Guth and refined by many others since, suggests that in the first tiny fractions of a second, the universe underwent a period of extraordinarily rapid exponential expansion, driven by a quantum field whose energy briefly dominated the universe's dynamics. Inflation explains several features of the universe that would otherwise be mysterious. Why the cosmic microwave background is so uniform in temperature in all directions, why the large-scale geometry of the universe appears flat rather than curved, but the detailed mechanism of inflation remains uncertain, and the predictions of different inflationary models are difficult to distinguish observationally. Some versions of inflationary theory predict that our universe is just one bubble in an eternally inflating multiverse, an infinite sea of space-time in which bubble universes are constantly nucleating, each one potentially with different physical constants, different laws, different possibilities for structure and complexity and life. This is a profound and somewhat vertiginous idea, one that lies at the very edge of what we can currently test or even meaningfully evaluate. We do not know if we are alone. We do not know if our universe is the only one. We do not know what came before the Big Bang, or whether the question even has meaning. These are among the deepest open questions in all of human knowledge. They may be answered in the coming centuries by instruments and theories not yet imagined. They may remain permanently beyond our reach. The honest answer is that we do not know. And there is a particular quality of peace that comes from sitting with that honesty, from recognizing the genuine boundary of current knowledge and resting at that boundary without anxiety. The universe began. We can trace its history with remarkable precision back to within fractions of a second of its beginning. Before that, the story becomes uncertain and then silent, like the moment before a piece of music begins. The silence that precedes the first note is not nothing. It is potential. It is the held breath before something extraordinary unfolds. The Big Bang was the first note, and everything since, every star, every galaxy, every nebula, every comet, every meteor, every planet, every moon, every creature that has ever looked up at the night sky and felt that nameless, quiet feeling has been the music that followed. You are part of that music. A brief, local, irreplaceable phrase in a composition that has been playing for 13.8 billion years. You do not need to understand the whole composition to appreciate the phrase you are in right now. this moment, this breath, this quiet. The universe began in a way we cannot fully imagine, and it has been unfolding ever since through all the long story of stars and galaxies and worlds toward this particular moment in which you are resting, breathing gently, at peace. Let the beginning be as distant and as soft as it truly is. Let the present be close and warm and immediate. You are here. That is enough. Of all the forces in nature, it is the gentlest and the most patient. It does not crackle or flash. It does not announce itself with any sound or light or sensation you can directly feel. It simply pulls quietly, constantly, without ever resting, without ever switching off across any distance, through any material, at any scale. Gravity. It is the force that holds you to the ground right now as you rest, the force that keeps the moon in its faithful orbit around the earth, and the earth in its orbit around the sun, and the sun in its long, slow arc around the center of the Milky Way. It is the force that gathered the first clouds of hydrogen gas into the first stars and shaped those stars into galaxies and arranged those galaxies into the vast cosmic web that spans the observable universe. Everything large-scale that exists in the universe has been shaped by gravity, and gravity, in turn, has been shaped by everything that exists. Because in Einstein's picture of the universe, gravity is not a force in the traditional sense at all. It is the geometry of space and time itself, curved and warped by the presence of mass and energy. And that curvature is what we experience as the pull toward massive objects. This is a beautiful and strange idea. Let us approach it gently. Before Einstein, the dominant understanding of gravity came from Isaac Newton, who formulated his law of universal gravitation in 1687. Newton's law was extraordinarily successful. It described the motions of planets, moons, comets, and tides with remarkable precision, and it remained the foundation of celestial mechanics for more than 2 centuries. Newton said that every object with mass attracts every other object with mass with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them. Double the distance, and the gravitational force drops to 1/4 of its previous value. Triple the distance, and it drops to 1/9. Newton's law worked beautifully for almost everything, but it had a gap that Newton himself acknowledged with characteristic honesty. He could describe how gravity behaved, how strong it was, how it varied with distance, but he could not explain what it was, or how it acted across the emptiness of space between objects that were not in contact with each other. He called this action at a distance, and he admitted he had no hypothesis about its mechanism. The answer came more than 2 centuries later, in the form of a young patent clerk in Bern, Switzerland, who spent his spare time thinking about the nature of space and time. Albert Einstein's special theory of relativity, published in 1905, established that space and time are not absolute and independent, as Newton had assumed. They are woven together into a single 4-dimensional fabric, space-time, and measurements of distance and time are relative to the motion of the observer. The speed of light is the same for all observers regardless of their motion, and this constancy has profound consequences for the nature of space and time themselves. But special relativity dealt only with objects moving at constant velocity. It took Einstein another 10 years of extraordinary intellectual effort to extend his ideas to include acceleration and gravity. The result, published in 1915, was the general theory of relativity, one of the most beautiful and far-reaching intellectual achievements in human history. Einstein's central insight was this: gravity is not a force. It is a curvature of space-time caused by the presence of mass and energy. When a massive object, a star, a planet, a galaxy, is present, it warps the space-time around it, creating a curved geometry. Other objects moving through this curved space-time follow the straightest possible paths, what mathematicians call geodesics. And those paths, in the curved geometry near a massive object, are what we experience as gravitational orbits and falls. A classic analogy is a rubber sheet stretched flat, with a heavy ball placed in the center. The ball creates a depression in the sheet, curving the surface downward around it. A smaller ball rolling across the sheet will follow a curved path around the depression, not because any force is pushing it sideways, but because the geometry of the surface has been curved. The smaller ball is simply following the straightest available path in a curved geometry. The actual geometry of space-time is four-dimensional and cannot be directly visualized in this way. The rubber sheet analogy has its limits, but it captures the essential idea. Mass tells space-time how to curve. Curved space-time tells matter how to move. This is the compact, poetic summary of general relativity expressed by the physicist John Wheeler. General relativity made several predictions that differed from Newton's theory, and in each case where the two theories differed, observation has confirmed Einstein's predictions. One of the first confirmations came in 1919, when the British astronomer Arthur Eddington led an expedition to observe a total solar eclipse. During the eclipse, stars near the edge of the sun's disk became visible, and Eddington measured their apparent positions. General relativity predicted that the sun's gravity would bend the paths of light rays passing near it, causing stars near the sun to appear slightly displaced from their true positions. The amount of bending predicted by Einstein was exactly twice what Newton's theory predicted. Eddington's measurements confirmed Einstein's prediction. The announcement made headlines around the world. Einstein became famous overnight. General relativity also predicted that gravity affects time. The stronger the gravitational field, the more slowly time passes. Gravitational time dilation. This is not a large effect in everyday life. The difference in the rate of time passing at sea level compared to the top of a mountain is tiny, but it is measurable. The GPS satellites in orbit around Earth experience slightly weaker gravity than objects on the surface, and therefore their clocks run slightly faster. If this effect were not corrected for, GPS navigation would accumulate errors of several kilometers per day. Every time you use GPS navigation in your car, on your phone, you are relying on a correction derived from Einstein's general theory of relativity. The most dramatic predictions of general relativity involve extreme gravitational fields, the region around black holes, and the behavior of the universe on the largest scales. Gravitational waves, ripples in the fabric of space-time produced by accelerating masses, were predicted by Einstein in 1916, but he believed they would be too small ever to detect a century later. The LIGO detectors proved him wrong, recording the space-time ripples produced by colliding black holes and neutron stars with instruments of extraordinary sensitivity on the largest scales. General relativity provides the framework for cosmology, the study of the universe as a whole. Einstein's equations relate the geometry of space-time to the distribution of matter and energy within it, applied to the universe on the largest scales. They predict that the universe should be dynamic, either expanding or contracting, rather than static. Einstein, troubled by this prediction, and believing the universe to be eternal and unchanging, introduced a term into his equations to hold the universe static when Hubble's observations revealed that the universe was in fact expanding. Einstein acknowledged the addition as unnecessary, famously calling it his greatest blunder. It is now understood that the cosmological constant Einstein introduced may represent dark energy, the mysterious component driving the accelerating expansion of the universe we discussed in our previous section. His greatest blunder may have been prescient after all. Gravity is also responsible for one of the most visually stunning phenomena in astronomy: gravitational lensing. When light from a distant galaxy passes near a massive object, another galaxy, or a galaxy cluster, the gravity of that object bends the light, just as a glass lens bends light passing through it. The result can be spectacular. A distant galaxy or quasar seen through a massive galaxy cluster can be distorted into arcs, rings, or multiple produces what is called an Einstein ring, a perfect circle of light around the lensing mass. The background source stretched into a complete ring by the symmetric bending of its light. Gravitational lensing is not merely beautiful, it is enormously useful. The amount of lensing reveals the total mass of the lensing object, including its dark matter, allowing astronomers to map the distribution of invisible mass in galaxy clusters and the large-scale structure of the universe on smaller scales. Microlensing, the brief brightening of a background star as a compact object passes in front of it, has been used to search for dark matter in the form of compact objects and to discover planets orbiting distant stars. Gravity is the architect of the universe's large-scale structure. It took the tiny density fluctuations of the early universe, those slight variations in the cosmic microwave background, and amplified them over billions of years, pulling slightly overdense regions into denser accumulations, gathering gas into the first stars, those stars into galaxies, galaxies into clusters, clusters into the vast filaments and sheets of the cosmic web. Without gravity, there would be no stars, no planets, no galaxies, no structure of any kind, only a perfectly smooth, cold, expanding fog of hydrogen and helium gas, thinning forever into the dark. Everything that has form and structure in the universe owes its existence to gravity's patient work. And on the scale of your life, the scale of your body and your world, gravity is the force that grounds you, that gives weight to your footsteps, that holds the atmosphere around the earth, the atmosphere you breathe, the blue sky you see, that keeps the moon in its orbit to pull the tides and mark the months, that keeps the earth in its orbit at just the right distance from the sun for liquid water to exist on its surface, for life to persist, for you to be here. Gravity is not merely a force. It is the condition of your existence. You feel it right now if you bring your attention to it. The gentle, constant pressure of the surface beneath you, pushing up against your body with exactly the force needed to counteract the pull of the Earth's gravity. You are not falling. even though gravity is always pulling you downward, you are held, balanced between the pull of the earth and the resistance of the surface beneath you. There is a metaphor in that, if you want it. You are always being pulled in some direction or another by demands, by worries, by the weight of the day. And yet, you are also always being held by the people and places and habits and routines that provide the surface you rest on, by the ordinary, reliable support that keeps you from falling, even when the pull is strong. Gravity pulls, the ground holds, and in that balance you rest. This is the shape of things, not just physically, but in some deeper sense that the body understands, even when the mind is not paying attention. The universe shaped itself through this force, patient, quiet, relentless, gentle, drawing matter together across billions of years, organizing the chaos of the early universe into the extraordinary complexity and beauty of the cosmos we inhabit. And right now, in this moment, gravity is doing what it has always done, holding you down, keeping you close to the earth that made you, letting you rest. For most of human history, the question was purely philosophical. Are there other worlds out there? Do other stars have planets orbiting them, as our sun has planets orbiting it? Is the solar system a unique arrangement, a rare and special circumstance? Or is it simply one example of something that happens everywhere, around every star, throughout the entire galaxy? Ancient Greek philosophers debated it, Giordano Bruno. The 16th century Italian friar and philosopher proposed that the stars were distant suns, each surrounded by their own planets, and was burned at the stake for a collection of heretical views that included this one. For centuries, the question remained in the realm of speculation, because no instrument existed that was sensitive enough to detect a planet orbiting another star. That changed in the 1990s, and what followed was one of the most extraordinary expansions of human knowledge in the history of science. We now know of more than 5,500 confirmed exoplanets, planets orbiting stars other than our sun. This number grows every month as new detections are confirmed, and the statistical analysis of the data suggests that virtually every star in the galaxy has at least one planet. The Milky Way alone may contain more than 1 trillion planets, 1 trillion worlds. The universe is not sparsely furnished. It is full of worlds in a variety of sizes and compositions and orbital arrangements that has surprised even the most optimistic planetary scientists. The solar system, it turns out, is not the only model for how planets arrange themselves around a star. The galaxy has been far more creative than anyone imagined. Let us talk about how we find these distant worlds, because the methods themselves are marvels of ingenuity and precision. The most productive method of exoplanet detection is called the transit method. When a planet orbits its star in a plane that happens to pass between the star and Earth, the planet crosses the face of the star, a transit, once per orbit. During the transit, the planet blocks a tiny fraction of the star's light, causing the star to dim very slightly, typically by less than 1%, and often by much less than that. By measuring this tiny dip in brightness with great precision and watching for it to repeat at regular intervals, astronomers can identify the presence of a planet, measure its orbital period, and calculate its size relative to its star. The Kepler Space Telescope, launched in 2009, was designed specifically to search for transiting exoplanets. It stared at a single patch of sky containing approximately 150,000 stars for 4 years, measuring their brightnesses with extraordinary precision. The result was a revolution. Kepler discovered more than 2,600 confirmed exoplanets and revealed that planets are extraordinarily common. Statistical analysis of Kepler data suggested that the Milky Way contains more planets than stars. The Transiting Exoplanet Survey Satellite, known as TESS, launched in 2018 as Kepler's successor. Rather than staring at one patch of sky, TESS surveys almost the entire sky, monitoring millions of stars for transits and identifying candidates for follow-up study. By the mid-2020s, TESS had identified thousands of exoplanet candidates and hundreds of confirmed planets. The transit method is most sensitive to large planets orbiting close to their stars, both because large planets block more light and because close-in planets orbit more frequently, producing more transits for the telescope to detect. This observational bias means that the earliest exoplanet surveys found many large, close-in planets, a class called hot Jupiters, that surprised astronomers who had assumed other solar systems would resemble ours. Hot Jupiters are gas giants comparable in size to Jupiter, but orbiting their stars at a fraction of the distance between Mercury and our Sun, completing their orbits in only a few days. On these worlds, the temperatures are extreme, thousands of degrees on the day side, with winds of extraordinary speed carrying heat from the permanent day side to the permanent night side. Some hot Jupiters are tidally locked to their stars, always presenting the same face to the heat, one hemisphere blazing and the other in permanent cold darkness. How did these enormous planets end up so close to their stars? The leading explanation involves planetary migration, the process by which planets can gradually move inward or outward from their original formation locations through gravitational interactions with the disk of gas and dust in which they formed, or through gravitational interactions with other planets, a gas giant forming in the cold outer region of a young solar system, where the raw materials for its formation were abundant, might migrate inward through the disk over millions of years, ending up in the searing proximity to its star that we observe. The second most productive method of exoplanet detection is the radial velocity method, also called Doppler spectroscopy. A planet orbiting a star does not simply orbit the star. The planet and the star orbit their common center of mass, a point that lies between them, closer to the star by the ratio of their masses. For a very massive planet orbiting a relatively light star, the stars wobble around this center of mass can be detectable. The star moves toward and away from us very slightly as it wobbles, and this motion produces a Doppler shift in its light. A tiny, periodic shift in the wavelengths of its spectral lines toward the blue as the star approaches, and toward the red as it recedes. By measuring these tiny Doppler shifts with spectrographs of extraordinary precision, astronomers can detect the presence of planets and measure their orbital periods and minimum masses. The radial velocity method was responsible for the very first confirmed exoplanet detections in the 1990s, including the discovery by Mitchell Mayer and Didier Queloz of a hot Jupiter orbiting the star 51 Pegasi, announced in 1995 and recognized with the Nobel Prize in Physics in 2019. Other methods include direct imaging, actually photographing a planet as a point of light separate from its star, possible only for large planets orbiting far from their stars, where the contrast is more favorable, and gravitational microlensing, which can detect planets at great distances from Earth and is sensitive to planets at orbital distances similar to those in our solar system. The diversity of exoplanets discovered through these methods has been astonishing. There are super-Earths, rocky planets larger than Earth, but smaller than Neptune, a size class with no example in our own solar system. But among the most common type of planet in the galaxy, there are mini-Neptunes, small gas, or ice-rich planets in the range of 2 to 4 times Earth's radius. There are ocean worlds, planets where a thick layer of water, perhaps thousands of kilometers deep, covers the entire surface under an atmosphere of steam, and exotic high-pressure ice forms below. There are lava worlds, their surfaces entirely molten, tidally locked with hemispheres of glowing rock. There are planets orbiting not one star, but 2 circumbinary planets, like the fictional Tatooine of science fiction, where 2 suns rise and set in complex patterns. There are planets in the habitable zone. The range of orbital distances from a star where liquid water could potentially exist on a rocky planet's surface, given the right atmospheric conditions. This zone is sometimes called the Goldilocks zone. Not too hot, not too cold, but just right. The TRAPPIST-1 system, discovered in 2017, caused considerable excitement when it was revealed that a small, cool red dwarf star, approximately 40 light years from Earth, hosts 7 rocky planets roughly Earth-sized, at least 3 of which orbit within the habitable zone, 7 rocky worlds around a single star, with potentially habitable conditions on at least some of them, and only 40 light years away. In cosmic terms, practically next door, the James Webb Space Telescope has begun studying the TRAPPIST-1 planets in detail, attempting to characterize their atmospheres or determine whether they have atmospheres at all. Red dwarf stars like TRAPPIST-1 are very active when young, bombarding their close-in planets with intense ultraviolet and X-ray radiation that might strip away thin atmospheres. The question of whether the TRAPPIST-1 planets have managed to retain their atmospheres, and what those atmospheres contain, is one of the most eagerly awaited results in current astronomy, the ultimate goal of exoplanet science, the holy grail that drives much of its research agenda, is the detection of biosignatures in the atmosphere of a habitable zone rocky planet. A biosignature is a chemical signature in a planet's atmosphere that could only be produced by biological activity. The presence of oxygen and methane together, for instance, which would rapidly react with each other chemically in the absence of a continuous biological source replenishing them, or the presence of complex organic molecules at concentrations that photochemistry alone could not produce. We have not yet detected a confirmed biosignature on any exoplanet. The instruments currently available, including the James Webb Space Telescope, are pushing toward this capability, but have not yet reached it for truly Earth-like planets. Future telescopes, both space-based and ground-based, are being designed with this goal specifically in mind. The question of whether any of these countless worlds harbor life is one of the deepest and most important questions human beings have ever asked, we will spend time with it in our next section. For now, let us simply dwell in the remarkable fact of the worlds themselves. Right now, as you rest, the TESS satellite is monitoring millions of stars, watching for the tiny dips of light that signal a world crossing the face of its sun. Ground-based spectrographs are measuring the Doppler wobbles of nearby stars, looking for the signatures of unseen companions. Data from the James Webb Space Telescope is being analyzed, revealing the compositions of atmospheres on worlds dozens of light years away. Every month, new planets are added to the catalog. New worlds, new arrangements of rock and gas and ice, and perhaps somewhere liquid water. There are more than 1 trillion planets in the Milky Way, and the Milky Way is one of 2 trillion galaxies. The number of planets in the observable universe is so large that expressing it in words becomes almost meaningless. But each one is real. Each one is a world, a specific arrangement of matter in a specific orbit around a specific star, with its own history of formation and evolution, its own geology and chemistry, its own cycle of days and nights and seasons, or the permanent blazing day and cold darkness of a tidally locked world somewhere among those trillions of worlds, on some of them right now. If our understanding of chemistry and biology is correct, something is living, growing, moving toward the light, unaware of our existence as we are unaware of theirs. And on at least one of those worlds, this one, something looked up at the night sky and asked, "Are there others?" The answer increasingly looks like yes. Let that be a gentle and companionable thought as you rest tonight, that somewhere in the dark, on a world perhaps very different from this one, under a sky perhaps very different from ours, something might also be resting, also breathing, also looking up, or perhaps no longer looking up, drifting slowly toward a sleep that feels, in whatever form it takes, something like this. The universe is full of worlds, and one of them is yours. Hold it gently tonight. It is perhaps the oldest question we have ever asked, older than astronomy, older than philosophy, older, perhaps, than language itself, encoded in the very act of looking up at the stars and feeling in the dark and the quiet, a wondering that goes beyond curiosity into something closer to longing. Are we alone? It is a question that carries within it everything we feel about our own existence, about whether this improbable arrangement of chemistry and awareness is a solitary accident in an otherwise empty universe, or whether it is, as some part of us has always quietly suspected, something the universe does regularly, wherever and whenever conditions allow. Science has been approaching this question with increasing seriousness and sophistication for the past several decades. And while the answer remains unknown, the tools and methods and understanding we bring to it have never been more powerful, and the possibilities have never seemed more numerous. Let us begin with what we know about life, the one example we have, and what it might tell us about life elsewhere. Life on Earth, in all its extraordinary diversity, shares certain fundamental characteristics. It uses liquid water as a solvent for its chemistry. It is based on carbon, a remarkably versatile element capable of forming the long, complex, stable molecules that life requires. It uses a genetic code based on DNA or RNA to store and transmit information. It obtains energy by exploiting chemical gradients, or in the case of photosynthetic organisms, by harvesting the energy of light. These commonalities suggest that the origin of life, at least on Earth, followed a particular chemical pathway, and that water and carbon were essential ingredients. Whether life elsewhere necessarily follows the same pathway, whether water and carbon are universal requirements, or whether other solvents and other elements could serve the same functions in different environments, is an open and fascinating question. The discovery that life on Earth exists in environments that would have seemed utterly hostile only a few decades ago has profoundly expanded our sense of what is possible. Extremophiles, organisms that thrive in extreme conditions, have been found in environments of extraordinary hostility. the superheated water of hydrothermal vents on the deep ocean floor, where temperatures exceed 100 degrees Celsius, and the pressure would crush a human body in the hyperacidic hot springs of volcanic regions at pH values of nearly 0, more acidic than battery acid. In the permanently frozen soils of Antarctica, in the highly alkaline waters of soda lakes, in the intensely radioactive environment of the cooling water of nuclear reactors. Each discovery of life in a new extreme environment expands the boundaries of what we consider habitable. Each extremophile is, in its own way, an argument that life is more resourceful, more tenacious, and more adaptable than we initially imagined. The study of life's potential beyond Earth is called astrobiology. It is a young science, formally recognized as a discipline only in the 1990s, but it has grown rapidly, drawing together astronomers, biologists, chemists, geologists, and planetary scientists in a shared investigation of one of the deepest questions in science within our own solar system. The most promising candidates for extraterrestrial life are not in the places that science fiction once imagined, not on the surface of Mars, under a breathable sky, not on the cloud-covered plains of Venus, but in environments far less visible and far more recently appreciated. Europa, the icy moon of Jupiter we touched on in our section about the solar system, is among the most compelling candidates for life in the solar system. Beneath its smooth, cracked shell of ice, estimated to be between 10 and 30 kilometers thick, lies a global ocean of liquid water, kept liquid by the tidal heating generated by Jupiter's enormous gravitational pull. This subsurface ocean has been in contact with a rocky seafloor for billions of years, and the conditions at the interface between the ocean water and the rocky floor may be similar to those at Earth's hydrothermal vents, where, on our planet, entire ecosystems thrive without any sunlight at all. NASA's Europa Clipper spacecraft, launched in October 2024, is currently en route to Jupiter and will arrive in 2030. It will conduct a series of close flybys of Europa, studying its ice shell, its ocean, and its plumes. Jets of water vapor that Europa appears to occasionally eject into space from cracks in its ice shell. If life exists in Europa's ocean, the plumes may carry chemical signatures of that life into space, where they could potentially be detected by the spacecraft's instruments. Enceladus, a small moon of Saturn, has also attracted enormous attention since the Cassini spacecraft discovered in 2005 that it was actively venting a plume of water vapor, ice particles, and organic molecules from a region of warm, cracked terrain near its south pole. Subsequent analysis revealed that this plume originates from a subsurface liquid water reservoir, possibly a global ocean, and contains hydrogen molecules, carbon dioxide, methane, and a range of organic compounds. The presence of hydrogen molecules in Enceladus's plume is particularly significant. On Earth, hydrogen produced by the reaction of hot water with rock, a process called serpentinization, is used as an energy source by certain microorganisms at hydrothermal vents. The detection of hydrogen in Enceladus's plume suggests that similar chemistry is occurring on its seafloor, potentially providing an energy source for life. Enceladus is small, only approximately 500 kilometers in diameter, but it has liquid water, chemical energy, and organic molecules. It has, in the assessment of many astrobiologists, everything life needs. Mars is the most intensely studied planetary body beyond Earth, and the question of whether it harbors or once harbored life has driven much of its exploration. We know that Mars once had liquid water on its surface, rivers, lakes, perhaps even an ocean covering much of its northern hemisphere billions of years ago. We know that it had a thicker atmosphere, a warmer climate, and conditions that may have been hospitable to life during its early history. Whether life actually arose on Mars during that early habitable period, and whether any traces of it remain, is unknown. The Mars rovers and landers that have explored the Martian surface have found organic molecules in ancient sedimentary rocks, complex chemistry, and environments that were once water-rich and potentially habitable, but they have not found definitive evidence of life, past or present. The most direct way to answer the Mars life question would be to return samples of Martian rock to Earth for analysis in laboratories far more sophisticated than anything that can be landed on Mars. The Mars Sample Return Mission, a joint project between NASA and the European Space Agency, aims to do exactly this, retrieving the samples collected by the Perseverance rover and returning them to Earth for detailed study. If ancient Martian life existed and left chemical or fossil traces in the rocks, this analysis may reveal them. Beyond our solar system, the search for life takes a different form. The most promising near-term approach is the spectroscopic analysis of exoplanet atmospheres, looking for the chemical signatures that life might leave in the air of a distant world, an atmosphere in chemical disequilibrium, containing gases that should react with each other, but are somehow maintained at elevated levels, is a potential biosignature. On Earth, the oxygen in our atmosphere is maintained by photosynthesis. Without life continuously replenishing it, the oxygen would react with rocks and other atmospheric gases and disappear within a few million years. The simultaneous presence of oxygen and methane, which react rapidly in the presence of ultraviolet light, would be particularly compelling evidence for biological activity, since maintaining both gases simultaneously requires a continuous biological source. The James Webb Space Telescope has already demonstrated the ability to detect carbon dioxide, water vapor, and other molecules in the atmospheres of transiting exoplanets. Future space telescopes, including the proposed Habitable Worlds Observatory, still in early planning stages, are being designed specifically to study the atmospheres of Earth-sized planets in the habitable zones of nearby stars, with biosignature detection as a primary science goal. There is also the matter of radio signals. Since the early 1960s, a small but dedicated community of scientists has been engaged in the search for extraterrestrial intelligence, SETI. The premise is straightforward. If technologically advanced civilizations exist elsewhere in the galaxy, they might produce radio emissions or other detectable signals that could be picked up by our telescopes. The search has grown in scope and sensitivity over the decades, with modern SETI programs monitoring millions of radio channels simultaneously across wide patches of sky. So far, no confirmed signal of extraterrestrial technological origin has been detected. The most famous candidate remains the WOW signal, a strong narrow-band radio signal detected by the Big Ear Radio Telescope at Ohio State University on August 15, 1977. It lasted 72 seconds, the full length of time the telescope's beam was pointed in that direction, and it had characteristics consistent with a signal of extraterrestrial origin. Astronomer Jerry Amen, reviewing the data printout, circled it in red ink and wrote the word WOW in the margin, giving the signal its name. Despite numerous subsequent searches in the same direction of the sky, the WOW signal has never been detected again. Its origin remains unknown. The silence of the universe to our radio searches is sometimes called the Fermi paradox, after the physicist Enrico Fermi, who reportedly asked over lunch one day, given the age and size of the galaxy and the apparent commonness of planets, where is everybody if intelligent life is common? Why have we not detected any evidence of it? Many possible answers have been proposed. Perhaps intelligent life is genuinely rare. Perhaps the development of complex, technologically capable life requires such an improbable sequence of events that it has happened only once or very few times in the galaxy. Perhaps civilizations tend to destroy themselves before they develop the technology for interstellar communication. Perhaps they communicate using methods we have not yet thought to look for. Perhaps they are so different from us that we would not recognize their signals as signals at all. Perhaps the distances are simply too great, and the galaxy too vast for signals to have reached us yet, or perhaps in the fullness of time, and with better instruments and broader searches, we will hear something. The question remains open, and open questions held with patience and curiosity are among the most alive and energizing things in science. What strikes me most, thinking about the search for life in the universe, is not the silence, though the silence is real and significant, but the extraordinary effort and creativity that human beings are investing in listening. We are building spacecraft to fly past icy moons and taste their plumes. We are landing robots on ancient lake beds, sifting through 3 billion-year-old sediments for chemical traces of ancient biology. We are pointing our most powerful telescopes at the atmospheres of worlds 40 light years away, looking for the breath of living things. We are trying very hard to not be alone, and there is something deeply moving in that, in the possibility that somewhere in this vast, ancient, star-filled universe, life is not a unique and solitary accident, but a recurring theme. Something the universe does whenever and wherever it can, in the oceans beneath icy shells and the warm shallows of ancient lakes and the thin atmospheres of rocky worlds circling distant suns. Life as a tendency of matter, given the right conditions. Life as something the universe reaches toward in its patient, multi-billion-year way. You are an example of that tendency, a temporary local arrangement of carbon and water and chemistry that found a way to be aware and to wonder and to reach outward into the dark with instruments and mathematics, asking the oldest question, are we alone? Perhaps the universe is already, in its own way, asking the same question back. Let that thought drift through you gently, like light through a clear, still atmosphere. You are here. You are alive. You are part of whatever answer the universe eventually gives. And right now, that is everything. There are people who have traveled to the far north in the middle of winter, standing in temperatures that make the air feel solid, in darkness that arrives in the early afternoon and stays until mid-morning. just for the possibility of seeing it. There are people who have set alarms for 2 in the morning, 3 in the morning, wrapped themselves in every layer of clothing they own, and stood in fields or on hillsides or at the edges of frozen lakes, necks craned upward, breath making small clouds in the cold air, waiting, and when it comes, if it comes, they invariably say the same thing. No photograph prepared them for it. The aurora borealis in the north, the aurora australis in the south, the northern lights and the southern lights, a phenomenon so beautiful, so dynamic, so utterly unlike anything else in the natural world, that it has inspired myth and reverence and wonder in every culture that has ever lived far enough toward the poles to witness it, and it is caused at its heart by the sun. To understand the aurora, we need to first understand that the sun does not simply sit quietly in the center of the solar system, providing warmth and light at a constant and steady rate. The sun is an active, dynamic star. Its surface, the photosphere, is in constant motion, churning with convective cells, threaded with magnetic fields of extraordinary complexity, punctuated by sunspots and solar flares and eruptions of such scale that they dwarf anything else in our solar system. The sun has a magnetic field generated by the motion of electrically charged plasma in its interior, a process similar to the dynamo that generates Earth's magnetic field, but on an incomparably larger scale. This magnetic field is not simple or uniform. It twists and loops and tangles as the sun rotates, with different latitudes rotating at slightly different speeds. The sun's equator rotates faster than its poles, a phenomenon called differential rotation. This differential rotation stretches and twists the magnetic field lines over time, building up stress and complexity until eventually the field lines snap and reconnect in violent events called solar flares and coronal mass ejections. A solar flare is an intense burst of electromagnetic radiation. X-rays, ultraviolet light, radio waves, released when magnetic field lines in the sun's atmosphere reconnect, the energy released in a large solar flare can be equivalent to billions of atomic bombs detonating simultaneously. Though spread over a large area and releasing most of its energy as radiation rather than explosive force, a coronal mass ejection, or CME, is something different and in many ways more consequential for Earth. It is the release of a large bubble of magnetized plasma, billions of tons of charged particles from the sun's outer atmosphere, the corona, hurled into space at speeds of several hundred to several thousand kilometers per second. If a CME is directed toward Earth, it arrives within 1 to 3 days, carrying with it a wave of magnetic disturbance. The sun also emits a continuous stream of charged particles, electrons and protons, at lower density and speed than a CME. This is called the solar wind, and it flows outward from the sun in all directions at approximately 400 to 800 kilometers per second, filling the entire solar system with a thin but continuous plasma. Earth is not defenseless against this constant bombardment of charged particles. Our planet has a magnetic field generated by the motion of molten iron in the outer core that forms a protective bubble around the Earth called the magnetosphere. The solar wind compresses this bubble on the side facing the sun and stretches it into a long tail on the night side. But it cannot easily penetrate the magnetosphere directly. The charged particles of the solar wind are deflected around the Earth, flowing around the magnetosphere rather than through it. But when a CME arrives, when that large, magnetized bubble of plasma slams into the magnetosphere, the interaction becomes more complex. If the magnetic field of the CME is oriented opposite to Earth's magnetic field at the point of contact, the two field lines can reconnect, a process similar to what happens in solar flares, but now occurring at the boundary of our magnetosphere. This reconnection allows energetic particles to funnel down along Earth's magnetic field lines toward the polar regions, where the field lines converge and descend into the atmosphere, the particles, mostly electrons, travel down the magnetic field lines and collide with the molecules and atoms of Earth's upper atmosphere at altitudes of approximately 100 to 300 kilometers. These collisions excite the atmospheric particles, boosting their electrons to higher energy levels. When those electrons return to their ground state, they release the excess energy as light. The same basic process that produces the light in a neon sign or the glow of a fluorescent tube, the color of the aurora, depends on which atmospheric particle is emitting the light and at what altitude. Atomic oxygen at high altitudes, above approximately 240 kilometers, produces the rare, beautiful red aurora, seen most often at the outermost fringes of the display, fading upward into the dark. Atomic oxygen at lower altitudes, between approximately 100 and 240 kilometers, produces the most common and most recognizable aurora color, a vivid green. When people picture the northern lights, the green shimmer is almost always what they imagine. Molecular nitrogen, the dominant component of our atmosphere, produces blue and purple hues, often seen at the lower edges of auroral displays, where the atmospheric density is higher, the result of all these different emissions occurring simultaneously at different altitudes, with different intensities varying moment by moment as the particle flux changes, is an ever-shifting canvas of color and form that has no equivalent in any other natural phenomenon. Auroras take many forms. The simplest is a quiet glow on the northern or southern horizon, a soft greenish shimmer that a casual observer might mistake for the lights of a distant city. More active displays develop into arcs, smooth, curved bands of light spanning large portions of the sky, their lower edges sharply defined, their upper edges fading into the dark as activity increases. Arcs can develop rays, vertical striations of light aligned with the magnetic field lines, giving the impression of curtains or draperies hanging from the sky. The most spectacular displays occurring during the most intense geomagnetic storms, can fill the entire sky with rapidly moving curtains and ribbons of light, dancing and folding and shifting in seconds, colors mixing and separating, the whole sky alive with movement. Observers describe watching the aurora as one of the most profoundly moving experiences of their lives. Not merely beautiful, but somehow alive, somehow responsive, as though the sky were breathing. The aurora has inspired stories and myths in the cultures of the Arctic and subarctic regions for thousands of years. The Norse saw it as the light reflected from the shields of the Valkyries, the warrior maidens riding across the sky. The Finnish word for the northern lights is revanchelit foxfires, from a myth of a cosmic fox running so swiftly across the northern fells that its tail brushed sparks from the snow, setting the sky alight. The Inuit of various regions interpreted auroras as the spirits of the dead playing games, or as torches carried by spirits, guiding souls to the afterlife, or as animals, seals, deer, beluga whales, dancing in the sky. These stories share a common quality. They see the aurora not as a physical phenomenon, but as a presence, something purposeful, something with agency. And while science tells us that the aurora is the result of solar particles interacting with atmospheric gas, there is something in the quality of its movement, its apparent spontaneity and responsiveness, that makes the intuition of presence feel understandable, even after you know the explanation. The aurora is also not confined to Earth. Any planet with both an atmosphere and a magnetic field can produce auroras, and we have detected them on several worlds in our solar system. Jupiter has the most powerful auroras in the solar system, driven by its enormously strong magnetic field, and fueled not only by the solar wind, but by particles thrown off by its volcanic moon, Io. Hubble Space Telescope images show Jupiter's auroras as bright, complex rings around its poles, glowing with the ultraviolet light of excited hydrogen molecules. Saturn II has auroras at its poles, rings of glowing light ultraviolet, visible to the Hubble Space Telescope. Even Mars, which no longer has a global magnetic field, produces localized auroras in regions where ancient magnetic fields are still frozen into the crust. A ghostly reminder of a time billions of years ago when Mars had a magnetic field, and perhaps a more clement environment. The sun's activity follows an approximately 11-year cycle, oscillating between periods of low activity, solar minimum, and high activity, solar maximum. At solar maximum, sunspots are numerous, solar flares are frequent, and coronal mass ejections occur more regularly, producing more and stronger geomagnetic storms, and therefore more auroras at lower latitudes than usual during extreme geomagnetic storms. The largest and rarest events, auroras, can be visible at latitudes far from the poles. The Carrington event of 1859 was the most powerful geomagnetic storm in recorded history, a coronal mass ejection of extraordinary intensity struck Earth, producing auroras visible as far south as Cuba, the Bahamas, and Hawaii in the northern hemisphere, and as far north as Santiago in Chile in the southern hemisphere. Telegraph systems across Europe and North America failed. Some telegraph operators reported receiving electric shocks from their equipment. Some telegraph stations continued to operate even after being disconnected from their power supplies, powered by the geomagnetically induced currents alone. If an event of Carrington scale were to occur today, the consequences for our technology-dependent civilization would be severe. Modern power grids, satellite systems, GPS navigation, and communications infrastructure are all vulnerable to geomagnetically induced currents and radiation from an extreme solar storm. The potential for widespread and prolonged disruption has led to serious efforts in space, weather forecasting, the prediction of solar activity, and its potential impact on Earth's technological systems, but on a quieter scale. The sun's ongoing activity and its interaction with Earth's magnetic field produces a continuous, gentle light show poles that has been a companion to human life in those latitudes for as long as people have lived there. Right now, in this moment, the solar wind is flowing outward from the sun and washing over the earth. Earth's magnetosphere is deflecting it, channeling it, funneling some fraction of its particles toward the polar regions above the Arctic and Antarctic circles. Electrons are descending along magnetic field lines and illuminating the upper atmosphere in colors that have no earthly equivalent, whether you can see it from where you are tonight or not. The aurora is happening. The sky is being painted at this very moment, somewhere above the polar ice, in green and gold and red and violet, in curtains and arcs and shimmering rivers of light. The sun and the earth are in conversation, as they always are. An ongoing exchange of particles and fields and light. A dialogue conducted in the language of plasma physics and magnetic reconnection, translated by the atmosphere into something the human eye reads as breathtaking beauty. You are part of that conversation. The same magnetic field that channels those particles toward the auroras is the field that protects you from the solar wind. The same atmosphere that glows with aurora light is the atmosphere you breathe. The same sun that drives the geomagnetic storms is the sun that warmed this day, that drives the weather, that has been powering the chemistry of life on this planet for 4.5 billion years. Everything is connected. Everything participates. And tonight, somewhere above the clean, cold ice at the top of the world, the sky is dancing. Let that image rest with you as you drift. The sky dancing in green and gold. The stars behind it, patient and still. The earth turning slowly beneath. And you, warm and quiet at the center of it all, breathing gently, resting, cared for by the same planet and the same magnetic field and the same patient sun that has been caring for life on this world for billions of years. You are well held tonight. There is a problem with looking at the universe from the bottom of a sea. We do not often think of it this way, but that is precisely where we are. The atmosphere of the earth, that thin, precious, life-sustaining layer of gas that wraps our planet is also, from an astronomer's perspective, an obstacle. It blurs, it absorbs, it scatters, it trembles with thermal currents that make stars appear to twinkle, beautiful to the naked eye, but maddening to a telescope trying to form a sharp, stable image. The atmosphere absorbs most wavelengths of electromagnetic radiation before they can reach the ground. Infrared, ultraviolet, X-ray, gamma ray, all largely or entirely blocked by the atmospheric layers above us, even in the visible spectrum, where the atmosphere is relatively transparent. The turbulence of the air limits the sharpness of images a ground-based telescope can achieve, regardless of how large or precisely built that telescope might be. The solution, which became possible only with the development of spaceflight in the second half of the 20th century, was to put the telescope above the atmosphere entirely, to lift it into space, where it could look out at the universe through no intervening gas at all, in any wavelength, with a steadiness and clarity impossible from the ground. The history of space telescopes is one of the most productive and most visually beautiful chapters in the history of science. These instruments have not merely gathered data. They have shown us the universe in ways that have permanently changed how we understand it, and permanently changed how we feel about it. The story of space telescopes begins well before the first one was launched. The American astronomer Lyman Spitzer proposed the idea of a large telescope in space as early as 1946, more than a decade before the first satellite was launched, more than 2 decades before the first moon landing. Spitzer understood the theoretical advantages of a space-based telescope clearly, and he spent much of his career advocating for the construction of what would eventually become the Hubble Space Telescope. The Hubble Space Telescope was launched aboard the Space Shuttle Discovery on April 24th, 1990. It was placed in a low Earth orbit at an altitude of approximately 540 kilometers, completing one orbit of the Earth every 95 minutes. Its primary mirror is 2.4 meters in diameter, large by the standards of space telescopes of its era, though modest compared to the largest ground-based telescopes. The early days of Hubble were marked by one of the most embarrassing and ultimately triumphant episodes in the history of NASA. Shortly after launch, testing revealed that Hubble's primary mirror had been ground to the wrong shape, a flaw of just over 2 micrometers, less than 1/50th the width of a human hair, but enough to cause the telescope to produce blurry images rather than the crisp, sharp views it had been designed to deliver. The cause was a tiny error in the testing equipment used during the mirror's fabrication. The problem seemed catastrophic. Years of effort, billions of dollars of investment, the promise of revolutionary science, all apparently undermined by a microscopic manufacturing error. But Hubble's orbit was low enough for astronauts to reach it aboard the space shuttle, and the telescope had been designed with servicing in mind. In December 1993, Space Shuttle Endeavour carried a crew of 7 astronauts to Hubble in what remains one of the most technically demanding and successful servicing missions in the history of human spaceflight. Over 5 spacewalks conducted over 5 consecutive days. The astronauts installed corrective optics, precisely shaped lenses that compensated for the mirror's flaw, along with new instruments and upgraded components. When Hubble's corrected images were released to the public, the impact was immediate and extraordinary. Images of galaxies, nebulae, and stellar nurseries of a sharpness and beauty never previously seen were suddenly available, not just to scientists, but to everyone. Hubble had become not merely a scientific instrument, but a cultural phenomenon, a window through which humanity could see its cosmic home with new eyes. Over the decades of its operation, Hubble has been serviced 4 more times by space shuttle crews, each servicing mission installing new instruments and replacing aging components. As of the mid-2020s, Hubble continues to operate and produce science more than 3 decades after its launch, a longevity that few anticipated when the original design was conceived. Among Hubble's most celebrated contributions are the Hubble Deep Field images, those long exposures of tiny patches of apparently empty sky that revealed thousands of distant galaxies, showing us the universe's history stretching back almost to its beginning. The ultra-deep field image, released in 2004, captured approximately 10,000 galaxies in a patch of sky smaller than 1/10 the diameter of the full moon. Some of those galaxies existed when the universe was less than 1 billion years old. Hubble has measured the expansion rate of the universe with unprecedented precision. It has confirmed the existence of supermassive black holes at the centers of galaxies. By observing the rapid motions of stars near galactic cores, it has observed the atmospheres of planets in our solar system. It has watched stars being born in nebulae and watched them die in supernovae. It has revealed the detailed structure of distant galaxies and the behavior of gravitational lenses. The scientific output of the Hubble Space Telescope is almost impossible to summarize. It has contributed to thousands of scientific papers across virtually every branch of astronomy, but Hubble was not designed to observe in the infrared, and it was not large enough to see the most distant and faintest objects in the universe. For this, a new telescope was needed. The James Webb Space Telescope, JWST, is Hubble's scientific successor, though it was conceived not as a replacement for Hubble, but as a complement to it. Webb was designed from the beginning as an infrared observatory, optimized to see the universe at wavelengths invisible to Hubble, and to do so with a mirror more than 6 times the collecting area of Hubble's. Webb's primary mirror is 6.5 meters in diameter, composed of 18 hexagonal gold-coated beryllium segments that fold up for launch and deploy in space. The mirror is so large that it could not fit inside any existing rocket fairing in its deployed configuration. Hence, the folding design, which required one of the most complex mechanical deployments ever attempted in space, involved involving approximately 344 individual mechanisms, each of which had to work correctly for the mission to succeed. Webb was launched on December 25th, 2021, on an Ariane 5 rocket from the Guiana Space Center in South America. Over the following month, it traveled approximately 1.5 million kilometers from Earth to a special gravitational equilibrium point called the second Lagrange point, or L2, where the gravitational pulls of the Earth and the Sun combine to keep the telescope in a stable orbit, synchronized with Earth's orbit around the Sun. At L2, Webb deployed its 5-layer sun shield, a tennis court-sized structure made of a specially coated polyimide film that blocks the heat and light of the Sun, Earth, and Moon, keeping Webb's mirror and instruments at the extremely cold temperatures required for sensitive infrared observation. The sun shield reduces the temperature on the cold side of the telescope to approximately -233 degrees Celsius, close to absolute zero. Webb's first full-color images were released to the public in July 2022, and they were immediately recognized as among the most beautiful and scientifically rich astronomical images ever produced. A deep field image showing thousands of galaxies, some of them among the most distant ever observed in breathtaking detail. The Carina Nebula, a vast stellar nursery revealed in infrared light, showing structures and young stars hidden behind dust that had been invisible to Hubble. The Stephens Quintet, a compact group of 5 galaxies shown in extraordinary detail, revealing the dynamics of galaxy interactions. The spectrum of an exoplanet atmosphere, detecting carbon dioxide, the first direct detection of this molecule in the atmosphere of a planet outside our solar system. In the years since its commissioning, Webb has transformed multiple areas of astronomy. It has detected the most distant galaxies ever observed, pushing back the frontier of the observable universe to within a few 100 million years of the Big Bang. It has revealed that these early galaxies were unexpectedly large and well structured for their age, challenging models of early galaxy formation that had gone unquestioned for decades. It has analyzed the atmospheres of exoplanets in detail impossible before its launch. It has peered into stellar nurseries and revealed the earliest stages of planetary system formation with unprecedented clarity. Beyond Hubble and Webb, the family of space telescopes is large and diverse. The Chandra X-ray Observatory, launched in 1999, has provided extraordinarily detailed views of the universe in X-ray light, revealing the superheated gas in galaxy clusters, the accretion disks of black holes, the remnants of supernova explosions. Its images in X-ray light show a universe of extreme temperatures and violent processes, completely invisible in visible light. The Fermi Gamma Ray Space Telescope, launched in 2008, monitors the sky for gamma ray bursts and maps the sources of high-energy gamma radiation across the sky. It has detected pulsars, supermassive black holes, and the annihilation of dark matter candidates in its years of operation. The Spitzer Space Telescope, launched in 2003 and retired in 2020, was a pioneering infrared observatory that blazed the trail Webb later followed, detecting the heat of cool stars, dusty galaxies, and planet-forming disks around young stars. The Gaia spacecraft, launched by the European Space Agency in 2013, has measured the precise positions, distances, and motions of approximately 1.5 billion stars in the Milky Way, creating the most detailed three-dimensional map of our galaxy ever made. A map that will inform astronomical research for generations. The Euclid mission, launched in 2023, is designed to map the large-scale structure of the universe with extraordinary precision, measuring the distribution of galaxies across billions of light years to probe the nature of dark matter and dark energy. And on the ground, a new generation of extremely large telescopes is under construction, including the extremely large telescope being built by the European Southern Observatory on a mountain Atacama Desert of Chile, with a primary mirror 39 meters in diameter. These giant ground-based telescopes, equipped with adaptive optics systems that compensate in real time for atmospheric turbulence, will work alongside space telescopes like Webb to probe the universe with unprecedented sensitivity and resolution. Each new telescope is a new set of eyes. Each one reveals something that was there all along, waiting to be seen, hidden not by cosmic shyness, but simply by the limits of our instruments. The universe has always been full of infrared glowing nebulae and X-ray blazing galaxy clusters and gamma-ray bursting black holes. We simply lacked the means to see them. There is something quietly humbling about that, about knowing that the universe has been going about its business in all these wavelengths, all these forms of light and radiation and gravitational ripple, entirely indifferent to whether we had the technology to observe it or not. Our observations do not change what the universe is. They only change what we know. And what we know now, with this extraordinary family of telescopes in space and on the ground, is richer and stranger and more beautiful than anything any astronomer in any previous century could have imagined. Right now, as you rest, Hubble is orbiting the Earth every 95 minutes, its gyroscopes holding it steady, its instruments gathering light. Webb is sitting at L2, shielded from the sun's warmth by its multi-layered sunshield, its golden mirror collecting the infrared light of the oldest galaxies. Chandra is in its highly elliptical orbit, monitoring the X-ray sky. Gaia continues its precise measurement of stellar positions. The universe is being observed right now in wavelengths from radio to gamma ray by instruments of extraordinary sensitivity and ingenuity, and the data they gather, the photons that have traveled for millions and billions of years to reach these detectors, will be analyzed by human beings who will learn things about the universe that no one has ever known before. We live in an age of remarkable seeing. Let that be a quiet comfort, that in this particular moment of cosmic history, we have built these extraordinary eyes and pointed them outward. And what we have seen has been more beautiful and more strange than we had any right to expect. Rest in the knowledge that the looking is being done, that the universe is being witnessed right now with care and precision and wonder. You can close your eyes. Others are watching. There is a generation of children growing up right now who have never seen the Milky Way, not because they live in cloudy climates or because they were born blind or because anything has happened to the galaxy itself. The Milky Way is still there, arching overhead on clear nights, exactly as it has been for the entirety of human history. But for more than 80% of people in North America and Europe, and for a rapidly growing proportion of people around the world, the artificial light of human civilization has overwhelmed the natural darkness of the night sky, washing out the stars and replacing the ancient, ink-deep black of true night with an amber and orange haze that never fully lifts. This is light pollution, and it is one of the most pervasive and least discussed forms of environmental change on Earth. The story of artificial light at night is, in one sense, a story of extraordinary human progress. Electric lighting transformed civilization in ways difficult to overstate. It extended the productive hours of the day. It made cities safer. It enabled the extraordinary complexity of modern urban life. The glow of city lights seen from space is one of the most striking images of human activity on our planet. A map of civilization drawn in light, tracing the coastlines and river valleys and population centers of the inhabited world. But that glow comes at a cost. And the cost is borne not only by astronomers and stargazers, but by ecosystems, by wildlife, by human biology, and by something less tangible, but no less real. The deep human connection to the night sky that has nurtured curiosity, art, philosophy, navigation, and wonder for the entirety of our species' existence. Let us understand what light pollution is and how it works. Artificial light becomes light pollution when it falls where it is not needed or intended. A street lamp designed to illuminate the pavement directly below. It also sends light sideways and upward into neighboring windows, into the eyes of drivers, and into the sky. An illuminated billboard sends most of its light toward viewers, but scatters a significant fraction upward and to the sides. Security lights, parking lot lights, sports field lights, illuminated signs, all of them contribute to the upward glow that, when scattered by the molecules and aerosols of the atmosphere, produces the sky glow that obscures the stars above our cities. The sky above a large city can be thousands of times brighter at night than the natural, unpolluted night sky would be. In such a sky, only the brightest stars are visible, perhaps a few hundred, compared to the several thousand visible from a truly dark location. The Milky Way is invisible. The Andromeda galaxy, faintly perceptible to the naked eye from a dark site, is completely lost. The delicate detail of the night sky, the nebulae, the star clusters, the variable stars, the subtle color differences between stars, all disappear into the orange haze. The loss is not merely aesthetic, though it is profoundly aesthetic. It is also scientific, ecological, and deeply human. Ecologically, artificial light at night disrupts biological systems in ways that research is only now beginning to fully document. Many insects, including moths and other pollinators, are attracted to artificial lights and spend their nights circling light sources rather than feeding or reproducing, exhausting themselves and dying before completing their life cycles. This may be a contributing factor to the dramatic declines in insect populations documented in many parts of the world in recent decades. Migratory birds navigate using the stars, using the pattern of the night sky, particularly the rotation of stars around the celestial pole, to determine direction during their nighttime migrations in brightly lit urban areas. This navigation system breaks down. Birds become disoriented, attracted to the glow of illuminated buildings, and collisions with lit windows kill an estimated 1 billion birds annually in North America alone. See turtle hatchlings emerge from their nests on dark beaches and instinctively move toward the brightest horizon. In nature, the sea, which reflects the light of the moon and stars, and is therefore brighter than the dark interior of the beach on developed coastlines. The brightest horizon is often inland, toward the artificial lights of buildings and roads, and hatchlings by the thousands walk away from the sea and die. Marine ecosystems near the surface of the ocean, particularly coral reefs, depend on the natural cycle of moonlight for synchronizing their spawning events. The mass, simultaneous release of eggs and sperm that ensures fertilization. Artificial light disrupts this synchronization, with potential consequences for reef reproduction and resilience. These ecological effects extend to the human body. We are, like all other animals on Earth, fundamentally shaped by the natural cycle of light and dark. The circadian rhythm, the approximately 24-hour internal clock that regulates sleep and wakefulness, hormone cycles, body temperature, immune function, and dozens of other physiological processes evolved over millions of years in a world where nights were dark. The primary environmental signal that sets the circadian clock is light. Specifically, the presence and absence of blue wavelength light that tells the brain whether it is day or night. Exposure to artificial light at night, particularly the blue-rich light of LED screens and modern LED streetlights, suppresses the production of melatonin, the hormone that signals darkness to the body and promotes sleep. This suppression contributes to the widespread sleep deficits of modern life, and epidemiological research has associated chronic exposure to artificial light at night with increased risks of a range of health conditions, including disrupted sleep quality, metabolic disorders, and certain cancers. The science of light pollution has grown enormously in the past 2 decades. The first comprehensive atlas of light pollution, mapping the brightness of the night sky across the entire world, was published in 2000 and won by the Italian astronomer Fabio Falce and colleagues. It revealed that more than a third of the world's population could no longer see the Milky Way from their homes. A revised and updated atlas published in 2016 showed that the situation had worsened significantly, with light pollution increasing globally at a rate of approximately 2% per year. More recent measurements suggest that the night sky is brightening even faster than satellite data alone would suggest, because satellites measuring light pollution were calibrated for older types of lighting and may underestimate the contribution of newer, bluer LED lighting, which is more disruptive to human vision and ecosystems, even at equivalent brightness levels. The spread of LED technology has been a double-edged development for the night sky. On one hand, LEDs are far more energy efficient than the sodium vapor and incandescent lights they replace, offering the potential for significant reductions in total light output if the efficiency gains are used to reduce brightness rather than simply to illuminate more. On the other hand, many communities have used the transition to LED lighting as an opportunity to install more lights, brighter lights, and lights in previously unlit areas, counteracting the potential energy savings and exacerbating light pollution. The color of LED lighting matters enormously. White LED lights with high color temperatures, the cool blue-white light common in many modern installations, scatter more efficiently in the atmosphere and disrupt circadian rhythms and wildlife more severely than warmer, amber-toned LED lights with lower color temperatures. The transition to warm LED lighting with appropriate shielding to direct light downward rather than sideways and upward could dramatically reduce the ecological and astronomical impacts of outdoor lighting without sacrificing safety or visibility. This is the central message of the dark sky movement, an international advocacy effort led by organizations such as the International Dark Sky Association, founded in 1988, which works to reduce unnecessary artificial light at night through education, policy advocacy, and the certification of dark sky places. Dark sky places designated areas where outdoor lighting is strictly controlled to preserve the natural darkness of the night sky now exist in more than 20 countries. They include dark sky parks, dark sky communities, dark sky reserves, and dark sky sanctuaries. The most pristine and remote sites on Earth. These designations recognize both the scientific and cultural value of dark night skies and provide frameworks for protecting them from the encroachment of artificial light. In the United States, dark sky parks include places like Capitol Reef National Park and Natural Bridges National Monument in Utah, Chaco Culture National Historical Park in New Mexico. One of the most significant archaeological sites in North America, where ancient peoples aligned their buildings with astronomical events, and where the dark sky is an integral part of the cultural heritage, and many others in the United Kingdom. The Galloway Forest Park in Scotland, the Exmoor National Park in England, the Brecon Beacons in Wales, and the South Downs National Park have all received dark sky status in the Southern Hemisphere. Sites in New Zealand's Mackenzie Basin region and the Atacama Desert in Chile, already home to many of the world's great observatories, offer some of the darkest skies accessible to travelers. Perhaps the most moving aspect of the dark sky movement is the recognition that what is being protected is not merely a scientific resource, but a cultural and psychological one. The connection between human beings and the night sky is ancient and deep. It predates science. It predates civilization. It reaches back to before language, to the earliest recognizable humans, sitting in firelight and tilting their heads upward, feeling what we still feel when we finally escape the glow of the towns and cities and see the sky as it truly is. There is a term for it in the conservation literature, the concept of a shifting baseline. Each generation grows up accepting the environment as it finds it as the normal state of things. Children growing up in cities accept a sky with a few dozen visible stars as the night sky. They have no experience of what has been lost, no baseline against which to measure the degradation. The loss becomes invisible, normalized, assumed. But for those who have seen a truly dark sky, who have lain on their backs in the desert, or the mountains, or the open ocean, and watched the Milky Way blaze overhead, who have seen the Andromeda galaxy with their naked eyes, who have watched a meteor shower against a sky so dark that the meteors cast faint shadows. The contrast is profound and irreversible. You cannot unsee it. You cannot go back to accepting the orange haze as adequate once you know what it is hiding. The good news is that light pollution, unlike most forms of environmental damage, is immediately and completely reversible. If every artificial light were switched off tonight, the darkness would return instantly. Not a decade of recovery, not a century of restoration, just the immediate return of the ancient sky, exactly as it was before the first electric light was ever switched on. The stars are still there. The Milky Way is still there. The Andromeda galaxy is still there. They are simply waiting behind the light. This reversibility makes light pollution both more tragic, because it persists through choice rather than necessity, and more hopeful, because the solution is available to us at any moment we decide to use it. Many communities around the world have already taken significant steps to reduce their light pollution, replacing poorly shielded fixtures with fully shielded ones that direct light downward, transitioning to warmer LED lighting, implementing curfews on non-essential lighting after midnight, and educating residents about the benefits of dark skies for ecology, human health, and quality of life. And for individuals, the solution is wonderfully simple. On any clear night, with a car and an hour of time, it is possible to drive away from the center of almost any city and find skies dark enough to see the Milky Way, dark enough for the stars to stop being points and become a presence, dark enough to feel, however briefly, the connection to the ancient sky that is the birthright of every human being who has ever lived. Wherever you are tonight, that sky is out there, perhaps just beyond the reach of the light, perhaps an hour's drive away. Perhaps, if you are fortunate enough to be somewhere already dark, directly above you. It is patient. It has been waiting for all of human history. faithful wait a little longer. The stars do not mind the delay. They have time, and so do you. Every generation of astronomers has stood at the edge of what they know and looked outward into what they do not. Every generation has inherited instruments and ideas from those who came before, built upon them, pushed them further, and arrived at a horizon their predecessors could not have imagined, and then handed what they found to the generation that followed. This is the long conversation of science, not a march toward a destination, but an ongoing exploration of a territory that reveals itself, step by patient step, to be larger and stranger and richer than the last map suggested. We are at such a moment now. The tools we have built, the observations we have made, the understanding we have assembled over the past century of modern astronomy have transformed our picture of the universe from something local and static and relatively simple into something vast and dynamic and almost incomprehensibly complex. We know that the universe had a beginning. We know it is expanding and accelerating. We know it is composed mostly of dark matter and dark energy we cannot yet explain. We know it contains 2 trillion galaxies, more planets than stars, and at least one world where chemistry organized itself into something alive and aware and wondering. And we know that there is vastly more to learn. The future of astronomy is being built right now. In laboratories and workshops and computer clusters around the world, the next generation of instruments is being designed and fabricated and tested in universities and research institutes. The next generation of ideas is being debated and refined. In the minds of students who have not yet made their most important discoveries, the questions that will drive the field for the next century are quietly forming. Let us look forward gently into what lies ahead. On the ground, the next decade will see the completion of what astronomers call the extremely large telescope era. A new generation of ground-based observatories with mirrors of unprecedented size, equipped with sophisticated adaptive optics systems that correct in real time for the blurring on Cerro Armazones in the Atacama Desert of Chile at an altitude of approximately 3,046 meters will have a segmented primary mirror 39 meters in diameter, the largest optical and infrared telescope ever built when it begins operations, expected in the late 2020s. It will be able to collect approximately 100 times more light than any existing ground-based telescope. It will be able to take direct images of Earth-sized planets around nearby stars, analyze their atmospheres for biosignatures, and study the most distant galaxies in the universe with a resolution and sensitivity that currently exists only in the theoretical plans of those designing it. The giant Magellan telescope being built at Las Campanas Observatory in Chile will use 7 circular mirror segments, each 8.4 meters in diameter, to create an effective collecting area equivalent to a mirror approximately 25 meters across. It is designed to be particularly powerful for spectroscopy. The analysis of the light from stars and galaxies to determine their chemical compositions, temperatures, velocities, and other properties. The 30-meter telescope, proposed for a site in either Hawaii or the Canary Islands, a process that has involved extended and important discussions about the relationship between scientific endeavor and indigenous cultural heritage, will similarly push the boundaries of what ground-based astronomy can achieve. Together, these extremely large telescopes will work alongside space observatories in a complementary relationship, each contributing what the other cannot. The space telescopes operate above the atmosphere, able to observe in wavelengths the atmosphere blocks, with a stability and clarity unavailable from the ground. The extremely large telescopes operate within the atmosphere, but benefit from their enormous light-gathering power and the logistical advantages of ground-based operation. Easier maintenance, upgradability, and the ability to build instruments of a size and complexity that cannot be launched into space. In space, the next major observatory after James Webb is the Nancy Grace Roman Space Telescope, Nancy Roman, NASA's first chief of astronomy, and one of the key figures behind the Hubble Space Telescope. Roman is designed primarily as a wide-field survey instrument, covering areas of sky roughly 100 times larger than Hubble's field of view in a single exposure. It will conduct surveys of dark energy and dark matter by measuring the shapes of hundreds of millions of galaxies across billions of light years, searching for the subtle statistical signatures of dark energy's influence on the large-scale structure of the universe. It will also search for exoplanets using gravitational microlensing and carry a coronagraph, an instrument that blocks the light of a star to allow direct imaging of its planets. Further into the future, the Habitable Worlds Observatory, still in its planning and design phase as of the mid-2020s, is being developed with the explicit goal of directly imaging Earth-sized planets in the habitable zones of nearby stars and searching for biosignatures in their atmospheres. This is the telescope that could, if it discovers what it is designed to look for, provide the first evidence of life beyond Earth. The technical challenges are formidable. Imaging an Earth-sized planet next to a star is like trying to see a firefly hovering next to a searchlight from thousands of kilometers away. But the principles are understood, and the path forward, while long, is visible. Gravitational wave astronomy, born with LIGO's first detection in 2015, is expanding rapidly. Ground-based detectors, including LIGO, Virgo in Italy, and KAGRA in Japan, are being upgraded to increasing sensitivity, and a network of detectors around the world is enabling increasingly precise localization of gravitational wave sources in the sky. But ground-based gravitational wave detectors are limited in the frequencies they can detect by the seismic noise of the Earth itself. In space, this limitation disappears. The Laser Interferometer Space Antenna, known as LISA, is a planned European Space Agency mission that will consist of 3 spacecraft arranged in an equilateral triangle with sides approximately 2.5 million kilometers long, maintaining their formation as they orbit the sun. Laser beams between the spacecraft will measure changes in the distances between them with extraordinary precision, allowing LISA to detect gravitational waves at much lower frequencies than any ground-based detector can reach. At these lower frequencies, LISA will be sensitive to gravitational waves from a completely different population of sources. The mergers of supermassive black holes at the centers of distant galaxies, the inspiral of stellar mass compact objects into supermassive black holes, and the gravitational wave background produced by the enormous number of merging binary star systems throughout the Milky Way. LISA will open an entirely new frequency band of gravitational wave astronomy, revealing sources and events invisible to any ground-based detector. Pulsar timing arrays offer yet another window into gravitational waves at even lower frequencies. An array of millisecond pulsars, the most precise natural clocks in the universe, spinning hundreds of times per second with extraordinary regularity, distributed across the galaxy, can function collectively as a gravitational wave detector of galactic scale. Very low frequency gravitational waves, such as those produced by pairs of supermassive black holes in the final stages before their merger, will cause tiny but correlated shifts in the arrival times of pulses from pulsars in different directions of the sky. In 2023, multiple pulsar timing array collaborations around the world announced the first evidence for a gravitational wave background. A hum of gravitational waves pervading the universe, likely produced by the population of supermassive black hole pairs throughout the cosmos. This was a landmark detection, opening a new observational window at the lowest gravitational wave frequencies. Neutrino astronomy is another expanding field. The Ice Cube Neutrino Observatory, buried deep in the Antarctic ice at the South Pole, detects high-energy neutrinos from astrophysical sources using an array of sensors distributed through approximately 1 cubic kilometer of ice. Neutrinos interact so weakly with matter that they pass through almost everything, through the entire Earth, through dense stellar cores, carrying information from environments utterly opaque to light. IceCube has detected neutrinos from distant active galactic nuclei and made the first identification of a high-energy neutrino source. Future neutrino detectors of even larger volume will expand this capability dramatically. The future of planetary science within our own solar system is also rich with planned and anticipated missions. The Europa Clipper, launched in 2024, will study Jupiter's moon Europa in detail from 2030 onward. ESA's JUICE mission, the Jupiter Icy Moons Explorer, launched in 2023, will study multiple icy moons of Jupiter, including Ganymede, Callisto, and Europa. Dragonfly, a NASA mission approved for development, will send a rotorcraft lander to explore the surface of Saturn's moon Titan, a world with rivers and lakes of liquid methane, a thick nitrogen atmosphere, and complex organic chemistry that some scientists believe may be relevant to questions about the origin of life. Mars sample return. Despite facing various programmatic challenges, as of the mid-2020s, remains one of the highest scientific priorities in planetary science. The return of carefully selected rock samples from Mars to Earth's laboratories would provide the most definitive possible answer to the question of whether life ever existed on Mars. And in the broader context of scientific progress, the field of computational astronomy is transforming what is possible. Modern sky surveys generate data at rates that make human inspection of individual images completely impractical. The Vera C. Rubin Observatory in Chile, whose legacy survey of space and time will generate approximately 15 terabytes of data every single night for 10 years, will use artificial intelligence and machine learning algorithms to identify transient events, classify objects, and detect changes across the sky that would be completely impossible to find through human effort alone. The Rubin Observatory is expected to discover millions of new solar system objects, detect thousands of supernovae, and produce a map of the large-scale structure of the universe of unprecedented completeness. The interplay between artificial intelligence and astronomy is one of the most dynamic areas of current development. Machine learning algorithms trained on existing observational data are discovering patterns, identifying objects, and making connections that human astronomers working alone could not find in many lifetimes of effort. They are being used to search for biosignatures in exoplanet spectra, to identify gravitational wave signals in noisy detector data, to classify the morphologies of hundreds of millions of galaxies in survey images, and to simulate the evolution of the universe at scales of resolution and volume previously out of reach. Beyond instrumentation, there are theoretical frontiers of extraordinary depth waiting to be explored. The unification of quantum mechanics and general relativity, a problem that has resisted the efforts of physicists for a century, remains one of the greatest challenges in science. A successful theory of quantum gravity would transform our understanding of black holes, the Big Bang, and the fundamental nature of space-time. The nature of dark matter and dark energy, the dominant components of the universe's energy content, is one of the deepest mysteries in physics, with implications not just for cosmology, but for our fundamental understanding of matter and force, the origin of life, the transition from chemistry to biology, is a question that sits at the intersection of astronomy, chemistry, and biology, and whose answer has profound implications for the distribution of life in the universe. These are not questions at the edge of human knowledge, in the sense of being almost answered. They are questions at the edge of human knowledge, in the sense of being genuinely open. Problems for which the solution is not yet in sight, for which the key insight has not yet been had, for which the observations that will change everything have not yet been made. They are waiting for someone, perhaps someone who is young right now, perhaps someone who is a child lying awake on a clear night, looking out a window at a sky too few stars, feeling something they cannot name, a restlessness, a reaching, a sense that there is something out there beyond what they can see that is worth spending a lifetime trying to understand. The history of astronomy is full of such people. People who looked at what everyone else was looking at and saw something different, who asked the question nobody else thought to ask, who built the instrument that turned one window of the universe into 100, whose single insight about the nature of starlight or the motion of galaxies or the behavior of quantum fields changed forever the story we tell about where we are and what we are made of, and how all of this came to be. That work is not finished. It has barely begun. The universe is 13.8 billion years old, and 100,000 light years across just in our own galaxy, and 2 trillion galaxies wide in the observable sphere, and possibly infinite beyond that. We have been looking at it carefully with scientific instruments for less than 400 years. We understand, in even our most generous accounting, a small fraction of what there is to understand. The dark ahead is full of gravitational waves not yet detected, full of exoplanet atmospheres not yet analyzed, full of early galaxies not yet imaged, full of the chemical signatures of life, perhaps, on worlds we have not yet found the means to study, full of answers to questions we have not yet thought of asking, and full of nights like this one, clear nights on a small blue world when someone somewhere stops and looks up and feels what human beings have always felt in the presence of the night sky, that particular, wordless, ancient peace. The future of astronomy is not only built in laboratories and launched on rockets. It is also built in moments like this one, in the quiet accumulation of wonder, in the feeling that the universe is worth understanding, worth studying, worth giving a lifetime to. You carry that feeling right now, perhaps without knowing it. It is what brought you here, to this night, to this voice, to this long and patient journey through the science of the sky, and it will still be here tomorrow, and the night after, and in all the nights to come, when new instruments and new minds and new questions will push the horizon a little further back, and the universe will reveal itself to be, once again, more beautiful and more strange, and more full of wonder than anyone expected. The dark ahead is full, and we are going toward it